is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science. I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science. I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science. I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science. I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
I also will try to be brief. So good morning, everyone. Oh, come on. I was waiting an AI generative. Good morning, right? So it's really an honor for me to it's really an honor for me to welcome you to this 2026 Science Time AI Summit. And thank you, every one of you, for being here. We have very distinguished scientists, industry pioneer, community partner, and student. Thank you for dedicating your time and expertise to be here with us today. I want also to extend a heartfelt thank you to the co-organizers of the event, the Center for Experimental Cosmology and Instrumentation here at UCR. We design-enable technology to explore the frontier of astroparticle physics and the cosmos. And certainly the Global Foundation for Science and AI Research, which accelerate basic science with AI while applying rigorous scientific principles to AI development. Without doubt, AI has become ubiquitous in higher education, and we still need to learn the best way to utilize and adapt this powerful tool to all of our activities. Here at UCI, we recently founded the RACE Institute, the Riverside Artificial Intelligence Research and Education Institute, which beautifully exemplify our campus collaborative spirit, uniting over 85 interdisciplinary faculty members across all 7 of our colleges to pioneer in cutting-edge machine learning and develop ethical, transparent, and AI solutions for real-world applications. UC Riverside is uniquely positioned to host this vital dialogue. As the only Research One and AU research university in the region, UCR anchors inland Southern California, one of the nation's fastest growing areas. Our region serves as a living laboratory where technology, agricultural legacy, climate pressures, and global logistics uniquely intersect. We actively leverage UCR top-tier research power to address this shifting dynamical enterprise. In doing so, we never lose sight of the profound importance of fundamental research, more necessary than ever at this current time. Curiosity-driven foundational science is the bedrock upon which practical technological leaps are built. Without deep fundamental inquiries into physics, mathematics, and the nature of intelligence itself, we cannot hope to build the robust next-generation AI system that will research our world. I always like to say that applied or translational research build very powerful keys to open particular door, while fundamental research is more at developing the master key, a key that will open many doors, even some that we don't still need, that we need to be open. That is why the core topics of this summit, the intersection of AI, science, and your upcoming panel on innovation and entrepreneurship merge perfectly with our institution DNA. At UCR, our mission does not end in the laboratory. We are deeply committed to workforce training and economic development for inland Southern California. This commitment is best epitomized by our initiative, the Southern California Oasis, which stands for Opportunity to Advance Sustainability, Innovation, and Social Inclusion. We'll soon open our new innovation hub, Through this signature regional economic initiative and the Southern California Oasis Park, we are actively bridging the gap between university breakthrough and the marketplace in clean tech, sustainable transportation, and precision agriculture, just to name a few areas. By building this ecosystem, we are creating a resilient local economy and training the next generation of the tech workforce right here in our community. In fact, we have already attracted several high-tech companies to our region, which are currently providing invaluable internship and job opportunities for our students and graduates. The integration of science and AI represent the next great frontier of human capability. I hope today's conversation spark bold ideas, forge lasting partnerships, and drive impactful innovation. So thank you again for being here, and one more time, welcome to Riverside.
Thank you for that. And for our next speaker, if you will, Chuck Ng, welcome him on.
Well, thank you, Peter. Good morning, everyone, and welcome to the Science and AI Summit at UC Riverside. I'm Chuck Ng, co-founder of SEER Foundation. A few thank yous before we begin today. To our organizers, Ceci and UC Riverside, thank you for making today possible. And please stand up when I call out your name. Thank you, first of all, to Physics Chair Shan Wensai. Shan, there's. Thank you, Shan. Ceci leaders, Haibo Yu. Where's Haibo? Haibo. Oh. Sean Watersdale. Sean, right there. Yep. John Richardson. Where's John? Yep. Yes. Steve Choi. Where's Steve? Steve? Yes, right there. Steve Choi. And the team, the entire team who worked tirelessly behind the scene to put this together. I also want to acknowledge Scott Clark, the team at Terraria Scientific. Scott. Thank you for sponsoring our event today, and to all of you, both in person and remotely, thank you for being here today. I'm grateful to be doing this alongside my co-founders, Terrence Tao. Terry, please. And Barry Barish. There is actually something particularly special about being here at UC Riverside, because that is Barry's scientific home. And on top of that, we have 3 generations of the Barish family in this room today. Barry, his son, Ken, where are you, Ken? Yes, Ken, thank you very much. Who will join us as a panel later, and his grandson, Milo, who is part of the SEER team. Milo, where are you? Right there in the back, working hard. Yes. Well, that means a lot to us. SEER was founded on a simple conviction that the science and AI need to be in the same room, which is all of you having joined, having here today with us, with the same seriousness, working on the same problems. We're building neutral ground, science first, and having all the incredible people in this room with us today. That is something we don't take for granted. I also want to say that personally, this one means something to me. Southern California is one of the most extraordinary concentrations of scientific talent, research institutions, and emerging technology in the world. The Inland Empire is part of the story today, and I do not think it gets talked about enough. So today, we go deep across 3 tracks: how AI is changing the way we design and operate detectors, how we use it to simulate and analyze scientific data at scale and speed that was not possible before, and how we use it to build theory, not just to compute faster, but to help science think differently. And best of all, we have some of the leading researchers across physics, mathematics, computer science, and guiding those conversations. Later today, I would also moderate a panel on innovation and entrepreneurship. The ecosystem here is alive. The talent, of course, is here. The ambition is here, and I couldn't be more excited for the day ahead. So I hope all of you guys could use the day well find the conversation you did not know that you needed, find the collaborator, and let us have a fantastic day together. Let me now welcome my co-founder, Barry, to share a few words and talk a bit about the agenda today. Barry?
There's a few slides if they can be. Does that? Let's see. Well, I'll just talk while he's doing that. First, welcome everybody from the host institution, UCR, which you just heard. And I'm going to tell you just a few minutes who the co-sponsor is, a little bit about that, which is on the physics side. I'll just reflect for a minute. Chuck, I've known for quite a while. And when this foundation was being formed, it seemed to me that having a kind of marriage of a foundation that was working on the problems that can help us optimize how to take this growing field of AI and apply it to scientific problems, in our case, physical sciences, was a really good thing to do, and to do it in a way that we work together in a foundation to create it and support the most effective things seemed like the way to go. Here, which I'm going to show you the people, I've been part-time here at Riverside since 2018. And in that time, we've created a new effort here, which is working in the area between physics and astronomy. When I came, I was asked to look at the physics department and tell them what they might do to make it better. And I identified this as an area that they should make appointments in and develop for a couple of reasons. One is that there's a physics and astronomy department, yet the physics and astronomy in most places are hard to kind of bring together. Yet in science, there's a whole stream of problems now that lie between physics and astronomy. We call it parts of it cosmology, which is looking at the early universe, which is a combination of physicists that look at that and astronomers that look at early times. And then there's a whole series of problems, whether it's LIGO, like I did, which is somewhere in between physics and astronomy and what it does, or looking for dark matter, which is another area, or exploring the sky, looking at the cosmic microwave background, or many other areas in physics are exploring these areas. These don't tend to fit into what is done in the big physics labs like Fermilab or SLAC, the big ones that have a lot of infrastructure, a lot of engineering, a lot of, and so that it's left to physicists in the universities, more or less, to develop the technologies that we need to move forward in these fields. And they can be very, very technically ambitious, like LIGO or dark matter searches, which use the forefront of technologies, including software, data analysis, and hopefully more and more AI to help us design the right instruments to make them work best and to analyze the data. So bringing these together is really something that we have worked toward here as we've developed a set of experiments. I'm just going to show you one of the slides I was going to show if he ever gets this up. He's one of the guys we hired in this area. Anyway, there's a meeting for the rest of this week, which is on the technical side, not the AI side. And so we have a lot of technical issues to solve and to optimize how we search best for dark matter, how we make the best viewing devices for the cosmic microwave background, how we design and build a next generation gravitational wave detector. And as I said, this is done in universities. Universities tend to want to hire physicists that are doing the science, quote, which means hiring the people that analyze the data and present a scientific result. And so there's been a big gap, I think, in universities developing the tools and the techniques and the laboratory expertise that we need to explore this huge field of science that's becoming more and more important. So we've been developing that kind of effort technically here. There's a meeting, as I say, the next few days to talk about the technologies. And hopefully more and more will also integrate with the AI world, which is where I've tried to bring this merger together. You got it, almost. It's on his screen now, so we're partway. It's everywhere. Now it's big on his screen. You can see we need to develop our technology skills on campus. I would skip my slides, but we can't go on to the next speaker anyway without the slides, I think. Yeah. Do we have a next speaker that doesn't need slides? Yeah, why don't we move on? You want to make the introduction or whatever? Terry will talk. Might as well. So we don't waste too much time.
Right, so unfortunately, it seems that technical difficulties are all upon us today, but the next speaker here will be our Professor Terence Tao. Unfortunately, I'm pretty sure he needs his slides too, but better to get the introduction out the way. Now, Professor Terence Tao has been with us for some time now, and he is a Fields Medalist. He is a professor of mathematics at UCLA and a member of the National Academy of Sciences and the co-founder of SARE Foundation. If you will, please welcome him on. I'm sorry, the slides won't be here for a while, probably.
It's okay. 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 Well, I will. I can probably describe my talk without the slides. It will help. But anyway, so thank you all for coming. I'm very excited to. This is the third SARE event. I've been involved in SARE for about 6 months now, a bit more than that. Okay. So, yeah. So at SARE, we've been trying to sort of figure out ways to support, integrate AI into and other modern technologies into scientific research, and in particular in my home field of mathematics. So mathematicians are very, very traditional. It's a very traditional community in many ways. The way we do mathematics in many ways has not fundamentally changed in centuries. We still use blackboards. We're almost the last profession in academia to cling onto our chalk. In fact, we prize certain special Japanese Korean chalk. You know, the textbooks, you can read a textbook from 200 years ago, and it looks almost identical to the ones we use today. I mean, the typesetting is a bit better, but And we work in very small groups, one-on-one, or we work with one postdoc and 2 students or something. We do sort of handcrafted, we work on one problem at a time, and sort of slowly map out a mathematical landscape. And this has worked for centuries, but it doesn't really scale. We have this long process of we work on problems, and then we produce solutions, and then we slowly verify the solutions. We write them up, and then we try to communicate them to the rest of the community. And eventually the end goal is to sort of digest them and have them appear in textbooks and teach them to the next generation of humans, and also increasingly AI now. And then once that's digested, then that's what leads to all the applications, in sciences and engineering, and to generate new mathematics. So there's this whole life cycle of mathematics, which has been very slow and steady. And now we have AI, and now we have all these other amazing tools, and it's accelerating some of this process, but not all of it. Yeah, the slide sort of helped, but so AI can now generate many solutions. Oh, all right. Okay. Okay. All right. So we're getting there. Okay. So yeah. So AI is allowing massive generation of new proposed solutions to mathematical problems, which is great. And in some cases, they can even automatically verify that. Oh, okay. Oh, great. All right. Okay. So the whole theme of my talk is mathematics is entering the 21st century. So this is actually very apropos. All right. Yeah. So as I said, we have worked in much the same way for centuries. On the left is a picture of a textbook from 200 years ago. And it's a bit hard to see this resolution, and it's written in French too. But if you're a mathematician, you'll recognize the format of the equations. Things have really not changed that much in 200 years. I mean, we had LaTeX and a couple other minor things, but yeah, the blackboards are so ubiquitous. In fact, they're even an art form. Jessica Wynn, who is a friend of mine, actually, she actually photographs. Well, she's a professional photographer. She photographed a whole bunch of mathematical blackboards as works of art and made it into a nice coffee table book. Yeah, and here's the life cycle, as I said, of mathematical problems. How problems get you generate proofs, and you generate. Whoops. Uh-oh. Okay, that wasn't. Okay, I might need some help here. I accidentally did something which I need to get back to. Okay, that was easy. Okay. Right, so there's a whole life cycle where proofs of slowly get generated, understood, digested, and eventually end up in textbooks, and also in now the training data of AI and whatever. Yeah, so what AI has been doing is sort of accelerating proof generation, creating solutions, and to some extent proof verification, but not so much the rest of the digestion process. And so this has started creating what I call proof indigestion, or traffic jams in mathematics. And I think the same thing is happening in the other sciences too now. Yeah, so journals, for example, we're receiving floods of AI-generated papers, which actually, many of them are actually very low quality, but some actually have some value, but we don't have the human resources to referee all of these all these new advances. And so all these new bottlenecks are emerging. There are sites devoted to solving problems where suddenly solutions are piling up, and people are not able to verify them. And so what this tells me is that traditional frameworks for doing research in mathematics, journals and conferences and whatever, they can't handle unrestricted AI use. And in fact, adding more and more AI to these sort of infrastructures it can actually be quite harmful. They can crowd out human contributions. As an analogy, I like to think of AI as sort of like the invention of the automobile. And in the 19th century, when in the end of the 19th century, early 20th century, when automobiles came out, the only infrastructure available were the streets that were built in the 19th century, these very narrow cobblestone streets. And so they had to drive in these streets, and there was no rules for traffic, or there was, and it was all mingled together, humans and automobiles, and it was pretty chaotic. Making the cars, the technology got better, they got faster and safer and more energy efficient and whatever, but still that doesn't solve this congestion problem. So that's kind of where mathematics and probably the sciences more broadly stand today with regards to AI. So what we need is to redesign our infrastructure and create new ways to do scientific research that can accommodate AI use safely. So with the automobile, we figured this out. We have, we have roads that are specifically for automobiles or for trains or monorails or whatever. And then we have pedestrian walkways for which no cars are allowed. And then there's a very small number of hybrid roads where you have both. And we figured out ways to have them coexist. Now, it's not perfect. Some cities may overweight their infrastructure towards cars. This is it's still a work in progress, but it is much better than the 19th century model of having everything pass through the same infrastructures. So we should keep our infrastructures of journals and all the traditional ways of producing research are still valuable, but we should also create new ones. So that's what I've been interested in at SARE. And so one of the venues for this are the SARE competitions, which I'm going to talk about. So with AI, there's a lot of new possibilities so in particular, in mathematics, mathematics has been kind of a fairly highly gate-kept operation until recently. You needed a math PhD often to even understand the problems that we work on, let alone contribute to them. But now we have the capability to really accept for certain types of math problems, you can take in contributions from the broader community of math adjacent people who may not have PhDs in mathematics. Some do, some don't, but they have these new tools, AIs and whatever, and they can contribute. But the key is that we need to design the right problems for them to work on, for which we can safely incorporate hundreds or thousands of contributions from the public. In the past, this has not worked because we couldn't verify all the contributions that come in, and many are very low quality. But we've started to figure out some ways to do this, and the competitions that we're talking about are an example of this. So right now we have 3 competitions ongoing. None have completely finished yet, but they have all produced nice intermediate results. The first competition is what we called a distillation challenge. We launched it on Pi Day, March 14th. So it built upon a previous crowdsourced project that I ran about 2 years ago called the Equational Theories Project. So this was an experiment to see whether we could really do mathematics at scale with modern technologies. So we created 22 million problems in algebra. Now, this is not a math talk, so okay, the questions I think is like, does the commutative law imply the associative law, if you know what these things are? And in this, but the exact problems are not important. Let's just say we generated this big sort of test set of 22 million questions, each of which were, most of which are not too hard. Like you get a graduate student in algebra working it for an hour, they can solve any given one of these questions. But we have 22 million of these questions. And the question is whether we could automate 3. Okay. Whether we could automatically solve them. So about 2. All right, I'm not sure what's going on here. It's still visible here. Okay. So anyway, so 2 years ago, we completed this project. Many people contributed with many tools, AIs and other and more traditional computational tools. And we managed to settle this all 22 million questions. So we have 22 million true-false questions, yes or no. And so we have this nice little data set of math in algebra. But it's a very complicated data set. And any individual question with modern AI, you could feed any given one of these 22 million data points to a frontier model, and it will think for 30 minutes and spend a few dollars of compute, and it will answer almost like 99% of these questions yes or no correctly, which is fine. But but this doesn't sort of tell you what the structure is. What are the features of this data set? Is there a way to sort of describe all these answers in a condensed way? So we set up what we call a distillation challenge. So if you, instead of using a premium, fancy, expensive model, if you use a very cheap open source model that just runs for pennies, then it's terrible on these problems currently. You give it one of these problems and it has a 51% chance of getting the answer right, like barely better than random chance. But it turns out that if you give these open source models a good prompt, like a one-page set of tips on how to solve algebra problems, it turns out that they can do a lot better. Just like a very weak student taking an algebra midterm may do very badly unless they are given a one-page sheet of lots of helpful things to do, and they can do a lot better. So the distillation challenge that we set up the competition was to submit a one-page cheat sheet to help these very weak AI models do well at sort of this midterm of solving these 22 million true-false questions. So contestants would submit a cheat sheet. We would test them against a test set of carefully selected sample problems, and they get a grade, and they have to try to find cheat sheets that performed as well as possible. And these are cheat sheets that AIs can read, but humans can read too. So the idea is whether you can sort of distill this entire knowledge of 22 million true-false questions down to like a single page that kind of explains the essence, or can explain as much of this data set as possible. So that challenge has is still ongoing. We have the results so far are quite promising. So with the best cheat sheets currently, the success rate of these weak AIs has increased by 20-30 percentage points, from 50% to like 80% accuracy. And the next stage is to which is still ongoing, is to get these weak models to not just produce yes, no, true, false answers, but actually write proofs and actually give more detailed explanations. And I'll be very interested to see how that goes. That's a much more challenging task. Okay, you can't really read it, but this is what one of these cheat sheets actually looks like. It's very terse because it has to fit on one page, but it is actually you can see that it's encoding a lot of information about the problems we're solving. Okay, we're running short on time, so I think I'll skip one of the competitions. I'll talk about the final competition that we are running right now, and it's actually quite exciting. We're checking it every day, the latest results. So this is a more mainstream mathematical challenge. This challenge was created in cooperation with the LMFDB, the L function set modular forms database, which is a major database of mathematical objects of interest in number theory, cryptography, many other fields of mathematics. And they were interested in something called the inverse Galois problem, which, okay, the exact technical details of this are, again, maybe not in the scope of this conference, but you can think of it like an Easter egg hunt. So we're looking for polynomials, so think of them like eggs. Okay, so we have these polynomials, and each egg has a certain property, like a certain color, if you wish. Okay, so it's called a Galois group. And we're interested in collecting eggs of various colors. Okay, so there are some colors that are very common, and some are very rare. If you collected baseball cards or other trading cards, you may have, that some cards are common, some cards are rare, and there are people who try to collect the entire set of all the cards of a certain type. And so this is roughly speaking what we are trying to do. It turns out that in this particular problem, there are 160,000 colors, if you wish, or types of polynomials, and we want to collect one of each. So this collection game, or Easter egg hunt, if you wish. All right, yeah. So the thing about this challenge is that once you find, you can type in a polynomial. A polynomial is just these are polynomials of 224. You just have to type in 24 integers, and it's very easy with modern computer software to take this polynomial and just work out its color. Okay, like okay, this polynomial has a Gower group which is 24T146. Okay, that's one of the colors that you can get. And so it's very easy once you write down a polynomial to see which egg you have gotten. But we want to collect all of them. And so for the common ones, that's very easy. But there's some ultra rare ones. In fact, there may be some for which no Easter eggs exist. We don't know. In fact, the whole inverse Galois problem is whether every single possible color is actually attainable. That's a major open question in Galois theory. So we decided to make this a competition. And so yeah, so we've been contestants can submit polynomials and we verify them. We don't reveal, so we have two stages of this competition. We have a competitive stage, which is ongoing right now, and then there'll be a cooperative stage afterwards that hasn't started yet. In the competitive stage, we don't reveal the polynomials. Each team has their own secret stash of polynomials. They submit them, and if they're the first to get, if they're the only ones who have a certain color, then they get 1 point. If many teams have submitted, have found the same color, then the points are shared in a somewhat complicated formula. So we want to encourage people finding very difficult, hard to find Easter eggs. And part of the reason why we do this experiment is because we don't know in advance which ones are hard, which ones are easy. And so we're hoping this competition will actually uncover, kind of by market forces, if you wish, which of these Gower groups are actually very rare and which ones are common. We have very little empirical data about this. Mathematics traditionally has not been an experimental science, but now we can do kind of experimental studies of mathematical objects, and this is really exciting, a new capability that these tools are offering. Yeah, so there are many teams. So this is a graph of team progress in the last week or two. There are some teams that have clearly using a lot of AI, and it's sort of scooting ahead for now. But you know, the lead is not guaranteed. You know, if somebody else can also replicate and find the similar other eggs of the same colors as the leading teams, they can steal these guys' points, and so we expect the lead to fluctuate. Yeah, and actually, I don't have this graph is from 3 days ago, but it's been changed. Yeah, it's not quite as monotonic as yeah, there's been some recent upsets. So this has been quite exciting. The organizers have been reporting that at math conferences in algebra, people all know about this competition, that some people are organizing their own private teams, and they're all very excited, which is in contrast. So many of the other AI contributions to mathematics, they have a mixed reception in mathematics. Some people welcome them, and some people are afraid that they're going to take away they'll compete directly with what mathematicians do. But this is an orthogonal capability to what traditional mathematicians do, and I think it's a very good place to direct these AI these new AI capabilities. Okay, just like we have roads for humans and roads for AI, we will have competitions with heavy AI assistance, but we also have traditional math workflows. So this is still ongoing. I hope to report more about it in the future meeting, how these things go. But so far, it's been very popular, and yeah, the leaderboards, and I mean, there's a little community sharing tips and so forth. Okay, so I think I'll skip the slides. We are trying to scale these up, so we are running 3 competitions on a fairly minimal budget right now. We have just a few engineers and some compute resources. Eventually, we wanted to scale up to do much larger competitions, with much more compute and with some high-profile prizes and things. All of the competitions right now are in mathematics, partly because that's the easiest, where you can verify the submissions, you can score very quickly, easily. But in principle, there could be other scientific competitions that you could run. If there's some big data set that someone wants to collect, and there's some way to do it in a crowdsourced fashion, come talk to us. We might be able to set up a competition. We do hope to set up a formal call for proposals in the near future, but that's still having board meetings and lots of internal emails about how best to do this.
Okay, so I think I will, in the interest of time, I will stop here. So thank you very much. All right. So I'm sure you've heard from Professor Terence Tao already a little bit, but there is a vision that we're going for here at SARE. We want to make a platform that is for open science and AI research. This is not working. I'm just gonna use the laptop. I don't think that's working either. It's not. All right, I'll use the arrow keys here. Okay. So I'm sure a lot of these people are very familiar to you, but we have some very, very important individuals with us. We have, of course, Professor Terence Tao, we have Professor Barry Barish, and we have Chuck Ng as our co-founders. And for our advisory board, we have Randy Scheckman, we have Lenore Blum, and we have Manuel Blum, as well as Jeffrey Oldman. So what do we aim to do as a platform? We want SARE to be a space where we can turn science and AI into some sort of open collaboration platform. We want to use AI for science, where AI can expand the scale, speed, and reach of scientific exploration. We want there to be science for AI, where scientific tasks can create practical tests for reasoning, reliability, interpretability, and evaluation. And with all this, we want to create an open research infrastructure that allows data, tools, models, benchmarks, and citations to become reusable. And how do we do this, right? We want to connect 4 verticals together to make this possible. We want to connect the science, of course. We want to connect the industry. We want to connect the builders, and we want to connect capital. Already, we have an open community that is focused on distribution and education. We want the world to grow together, and to do that, we have an online community of over 650,000 members, where we have podcasts, live events, and interviews with some of the world's leading scientists. We have a global network that connects every part of the world with our SARE events. And like we do now, we have summits and events that really need to connect the community in person because, well, being online doesn't really get the point across all the time, in my opinion. And so how does a research loop work? We want to go from an open problem to an open artifact. And to do that, we first take the open problem or data. We form competitions around those problems. Through playgrounds, we'll find solutions. And with those solutions, we'll create an open benchmark for people to compare their works and see what has improved and what has not. To host this, like Professor Terence Tao introduced earlier, we have the SARE API. And with that, we'll create a contributor network that can help people find each other to work together because science really is a cooperative effort. So let's talk a bit more about competitions, right? We have public problems and statements, data sets, etc. We have runnable tasks with reproducible evaluation. And the goal is that we want submissions to become reusable research artifacts, not just results. And this is not just for the key fields where AI is most prevalent right now. We want to make it applicable to other fields as well. And so we have a playground to help with this. It's a shared environment for testing ideas, inspecting outputs, comparing methods, and such, where we can run solvers and baselines. You can inspect logs, proofs, lean certificates, and failures. And then in it all, the point is to compare outputs in a common evaluation frame against other results. Thus, we turn experiments into reusable artifacts. And so, open benchmarks, right? The point is to make progress measurable. We want there to be comparable results across models, setups, and teams. We want there to be comparisons to see what the community can improve on and what fails. And again, the point of this is to go back and iterate because you're not guaranteed success the first time around, right? To help with this, we've come up with the process of SARE-ID and SARE-Connect, where SARE-ID is a persistent research identity where verified contribution, record, portable credit, and continuity across competitions, events, and such are recorded. And then we have SARE-Connect, which allows for people to interact with each other and to allow for problem-based discovery based on your past work rather than just generic profiles, which is very important. And so with this, we will create an open model. And that is our goal, to create an open model for global science that is accessible to every scientist everywhere. Now, SARE builds frontier scientific models trained on community data. Reasoning traces from top labs are used to fuel this, and we have open weights and open evaluation. Now, I think one of the biggest questions when it comes to science discovery is who gets access, right? For us, we want to make sure that it's accessible to every scientist globally. We want it to be accessible to universities of every size. We want it to be accessible to researchers of every emerging country. And we want it to be accessible to the next generation of builders. And the reason this matters so much is because science and scientific discovery multiplies when you have all of this information that is openly accessible to everyone. And with that, we're able to accelerate the rate at which we can make discoveries. So our plan is to make one platform that can cover many scientific frontiers. We want to create open challenges, open data, open tools, open models, open benchmarks, and of course, an open community. We want this to be applicable to mathematics, physics, biology, materials, energy, robotics, chemistry, and other fields as well. So, if you don't mind, I would love for all of us to participate in this together. You can participate in challenges, you can contribute to our infrastructure, you can join our network, and you can help us create programs. One sec. Well, thank you, and I hope you'll join us on our journey. Now, with that, we're going to have a small break of about 10 minutes. We are running very rushed time, but 10 minutes break. Let's just take a break for now, use the restroom, and we'll be back. Thank you.
Your area. If you don't understand anything about a specific subject in math, you can ask it. Give me the pointers. Where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SARE, I'm very happy to announce our first SARE competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for maritime science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for maritime science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
With smart enough models. And so we'll continue that discussion now. So we have with us a few leaders of this field. So first of all, we have Rana Adhikari rejoining us, who we just heard from. We also have Daniel Ratner, who is a senior scientist at Jefferson Lab and the Jefferson Professor at Old Dominion University. We have Huantong Li, an Associate Professor of Physics. An Assistant Professor of Physics here at UC Riverside in Electrical and Computing Engineering. And Javier Duarte, an Associate Professor of Physics at UC San Diego. So welcome to all of you. Before we get into the questions, I would just like to ask the three new panelists joining us to just briefly, in about 1 minute, give us a quick introduction to your field of expertise. We'll start with Javier.
Great. Yeah, so thanks for the invitation.
To help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math.
Data is located, right? So for us, we'll name it in-memory computing, right? This is where the data is stored, and then uncensored computing. This is where the data is generated. So I hope to share some experiences with you.
Next is Daniel Ratner.
Hi, yes, my name's Dan Ratner. My background's in accelerator and X-ray physics. I spent most of my career at SLAC working on X-ray lasers and just moved to JLab, so getting more into the high-energy physics, nuclear physics world. The last 10 years or so, I've been working primarily on AI applications for accelerators and science broadly, so how to operate them, how to design new ones. And then now I'm also a part of the Genesis mission, so I know it's not part of this discussion, but I know if you want to throw tomatoes or if you have questions, I also can talk about that later. I guess we know you already.
And we all know Rana. Okay, the first round of discussion is AI-driven experimental design. So exploring the opportunities for design and for operation of these very complex detectors. And so I wanted to give the first question to Rana, which is to follow up on some work he highlighted on using reinforcement learning to actually control some of the servo systems within the LIGO detectors to stabilize the main mirrors. So my question, Rana, is I believe in this paper which I think appeared in Science. It replaced some of the angular sensing and control, if I remember. And so the question is, imagine in a future upgrade of LIGO or Cosmic Explorer, we wanted to replace every coupled length and angular servo in the entire system with a reinforcement learning approach. What are the main bottlenecks? What are the challenges of actually doing that at full scale?
I think usually the way that people think about the experiment is that it's this hardware, and basically that's the main thing. And then on top of that, there's some software which is incidental, or that the feedback controls are not important. But I think it's a little bit of a 20th century view. Now, we're putting quantum states into the system. And so you have to do coherent quantum control if you want to get the most out of your system. So even though the detector itself is classical and mostly linear, we know that the primary reason we have controls is because the detector is nonlinear if you don't control it. So we're always trying to put it into its linear regime. But there's places where you can get more sensitivity if you operate it in a place where a sane person might not do it. But in the LIGO case, there's hundreds of feedback control systems that have to run in real time. And we've never been able to wrap our heads around what that means or how these things work together. And the beauty of reinforcement learning is you don't have to. Is if you can simulate the system well enough, and that's a kind of just a compute-driven problem, but you can then design these things. So for that particular thing that I showed you, in the year 2024, that took something like 36 hours of compute to generate something like that. So that's unscalable to what we're talking about. And the reason we need to do that is for what I said, that if you do this design where you build an experiment and then stick this on later, that's never going to work for you. So I think the future is co-optimization, where you optimize the detector and take into account the fact that you have all these controls. I just don't know how to get there because, as I said, it's 36 hours a couple of years ago. It might still be a 10-hour optimization. GPUs are not that much better. So I don't know how to get there from where we are, except we're going to have to figure out better ways to cheat, I think, and do approximations.
Okay, thanks. Would you like to follow up, Daniel?
No,
You have the
I was just
microphone.
ready for it. Although I totally agree that the co-design, I think, is actually for next generation of facilities is going to allow us to do completely new things. Yeah. Anyway, we can talk about it later.
Yeah. So I'll give the next question to Daniel on a related topic. So your work in this new paradigm of multi-point Bayesian algorithm execution has actually been demonstrated in real particle accelerators at SLAC to better control the particle beams in those experiments than the hand-tuned settings of human operators. And so the question is, how widely can these same approaches translate to other architectures of accelerator experiments and even more broadly beyond particle accelerator experiments?
Yeah, so just for people who are not aware, this idea of BAX or Bayesian algorithm execution is, if you know about Bayesian optimization, you can think of this as a generalization of Bayesian optimization where you're separating out the thing that you're modeling from your objective function. And why I find that exciting is now you're able to have, rather than having a Gaussian process with small number of points modeling a one-off objective function, you're actually using this now to really learn some physics. So your surrogate model is now an underlying physics model of your system. So in that sense, it's very general and very flexible. And we've used this already for a wide range of topics, different types of accelerators, both control. That was originally what we were working on, was control, but now increasingly working on design with it. And then also in other fields. So we also work in materials science and people using it for drug design, et cetera. So it's very general. I'll just end and say the message I try to get across to new students is to think about. I think the sort of philosophical way to think about it is that we're working not just to select a point that optimizes some design or some task, but really to actually design this underlying model. And because now this underlying model can be a big neural network, we actually, that can be the outcome indeed of BAX. So we have sort of loosely calling this idea of foundation BAX, the idea of basically the surrogate model actually being a foundation model. So really thinking about this as a way of fine-tuning or training a new foundation model for the task that you care about. So that's both so in a material science case where we're actually taking a foundation model as the starting point and then we fine-tune for some particular task. But also you can think about having a community using these tools to build their own foundation model. So in the materials world or in the Future Circular Collider, you have all of your design team all sharing, putting simulations into one central model that can support everyone. So in that sense, I think actually it is really designed to be flexible and to transition to new applications.
Yeah, I'll just note we have hopes of aspirations, I would say, of doing the same thing for Cosmic Explorer, the next generation gravitational wave observatory.
Yeah. So yeah, and if you have ideas and you want to try this out, please come reach out. Yep.
Okay. So I was it was interesting to see, and one of the examples, and I noticed in Rana's slides was highlighting the fact that the Large Hadron Collider detector now is triggered. The triggering that actually records events when two protons collide is now being run by AI. And in fact, one of the leaders of that implementation in the LHC is here with us today, Javier. So the question is just, can you explain a little more about how the incredible low latency of this triggering algorithm, which I believe is less than 1 microsecond, how does has this low latency impacted science of the LHC, and what are the remaining bottlenecks? Are there more science returns from making the latency even lower, or are there other limitations?
Yeah, good. Yeah, so as you said, one of the big challenges at the LHC is just how rare the events that we're looking for are. Mean you need to collide a ton of protons in order to actually, have any chance of seeing, double Higgs boson production or something. And so that means that we are flooded with data. We collide protons 40 million times a second. So every 25 nanoseconds, there's another collision. And we can't possibly record and analyze all that data. There's just not enough compute budget in the world, basically. And so we have to down select immediately, filter that down to something manageable. And the first stage of that, as you said, has to operate in about a microsecond. It's a big FPGA farm with some custom electronics, and reduce it, basically has to reject something like 99.8% of the collisions, like right off the bat. And so if those, if the precious, new physics signal is there and you discard it in that step, you're never going to see it. So it is a really, of crucial importance. And traditionally we would do pretty simple algorithms because of how quick the latency was, basically just count up interesting particles that are like muons that are rare, or measure the total amount of energy in the collision and then save it if it's above some threshold. And what sort of my work and the work of my collaborators has enabled us to do is to replace that with sort of much more, these multivariate neural network, decisions that are based on not just, one specific aspect of the event, but actually like looking at, the topology of the different particles in the event, how likely it is that one of the particles might be like a bottom quark with which the Higgs boson decays to. So it really has helped sort of increase the acceptance to like these rare, signal events that we're looking for. But beyond that, it's actually enabled kind of a new thing that maybe was unexpected initially, which is, we're interested not just in looking for what we know is there, like the Higgs boson. We're interested in like, is there anything unexpected in the data, right? So we design these trigger algorithms based on the signature that we know, but there might be some new physics that doesn't map on to our expectation. And so one of the exciting new things that this has enabled is doing like unsupervised anomaly detection. So this is, classically this is done with like training an autoencoder or a variational autoencoder, and then using the loss function from that, the reconstruction loss. So basically how poorly the model can reconstruct, the input as a proxy for how anomalous it is. If you train it on a bunch of standard model events and it basically can't compress this new event well, that could be a sign that it's kind of new physics or something anomalous. And so that has been just recently deployed for the first time in the CMS experiment, and Atlas has done something similar. And so we now have like a year or a few years of data recorded with this kind of trigger. And so the next step is really kind of analyzing that and seeing what comes out. And then your question about bottlenecks, I would say there is still a bottleneck in terms of designing the best algorithm given the hardware constraints. And I think people have brought this up already a couple of times, this idea of co-design. So we really want to sort of automate that co-design loop where you're not just optimizing for performance of a machine learning algorithm, but also simultaneously trying to make it as small and as fast as possible. And we have sort of new tools that we're using for this now, like a lot relying on like Bayesian optimization or genetic algorithms. And so that's kind of an exciting new thing that we're hoping to, that will make it even easier for people to deploy these ML algorithms in hardware.
Thanks. And just to follow up on that, I think we heard from Daniel and Rana already, this, as you say, this idea of co-design and the fact that some of these approaches may actually translate pretty broadly to experimental design at large. Do you agree? Do you see that as the case for the methods being employed at the LHC?
Yeah, absolutely. So yeah, a lot of the one of the things we did is we built this like compiler framework, HLS for ML, and it definitely has applications far beyond particle physics. People use it for neuroscience applications, material science, and yeah, I think this idea of co-design is really important. Qubit readout, there's a lot of different applications. And actually, if people are interested in this topic, we have the Fast Machine Learning for Science conference, sorry for the plug, is coming up at UC San Diego at the end of August. So if people are interested in hearing more about this, it's a big topic.
Okay, thanks. So Wantong, along the same same theme, there are many experiments that rely on reconstructing a science signal, essentially extracting it from information from a distributed network of many sensors. And some of your recent work for experimental direct dark matter detection has proposed a new type of AI-driven algorithm for actually reconstructing the science signal from the detector, which is much more robust even in situations where traditional methods can suffer near 100% data loss. So could you explain first a bit more about how these advances work, how they are accelerating the search for dark matter?
Yeah, sure. So I think, first of all, to be clear, it's a project where we are trying to integrate AI. That one has not been completed yet. We have been trying to integrate some conventional approaches to on-detector sensing, right? So I think regardless of AI or conventional processing, it's important to note that the type of work we are doing are very close to the sensors or detectors, right? It's not going to be after you stream out the data. So, and the motivation there is to try to solve the data problem right at the source, right? So if we talk about distance, we are probably looking at micrometer up to maybe millimeter away of putting logic and transistors next to the detectors. So one project I'm working on with Sean actually is on to optimize the dark matter search, right? So setup is that we have this liquid argon TPC, and then we are trying to find dark matter through the scattering. And within this setup, there are actually several distinct signal profiles, right? I think the terminology is the S1, S2 signals. S1 is one where you have a very sharp rise of signals, probably as short as several nanoseconds. And then there will be followed by a S2 phase where will be a burst of photons. So then, the goal there is to cleanly and hopefully carry all of the data off the detectors, right, in a clean manner, right, against the background noise. So for us, because I come from the computer architecture and then microelectronics background, so we actually identified a lot of bottleneck to be conventional engineering challenges, right? One of them is, for example, analog versus digital. So, for example, in conventional detectors, people tend to try to aggregate all of the analog signals and then try to stream out everything at the end of the detector, right? So that will rely on very high bit width, high precision amplifiers, and then ADCs. And then there's also a challenge of bandwidth, right, which is basically the mismatch of how much information you are trying to collect versus how much you can actually stream out, right? For example, in our scenario, if you look at a LVDS kind of cable, right, that one can only probably carry several gigabit per second of data. But then the photons we are looking at maybe up to 10 billion, right, 10 to the 10th photons per second. And for each photon, we actually have to assign multiple bits to that, right? So then there is that mismatch of what information you are trying to carry versus how much you can stream out. And then, with all of that, we have to work within our budget, right, in terms of the hardware, right, the power, thermal, and then, if you need latency, you also have to be fast. So then with all of these challenges, we identify the problem to be a data flow problem, right, which is a term that we borrow from the computing systems, right? Data flow, basically how to stream data and route data efficiently. So that's where, to answer your question, where the algorithms and the architecture that we propose rely on, right? So we try to make our detectors, which is large scale, but then make them into smaller groups and try to have finer controls for the local sensings. For us, it's the SPADs, right? So single photon avalanche diodes, right? So have finer controls at hopefully smaller granularities, and also try to digitize as early as possible. And the reason for us is because we want to give tags of temporal and spatial information to all of these photons. So after you digitize early, then you can work with these signals a lot easier than if you have to work with analog signals. And finally, on the topic of AI, right? So I think right now we have not fully integrated AI to the detector just because we have to find a reason to do that, right? Because AI, even a small model like MLP or LSTM, if you put it next to a detector, the thermal will go up a lot, right? In our scenario, any increase in the power will likely boil the liquid argon, right? So we have to be very careful with anything we put on there, right? Probably sub hundreds of milliwatt of power budget, right? So that's why for our first attempt here, we are trying to use conventional approaches of buffering using logic transistors, and then try to have lightweight control and logic on our detectors. But the next step is definitely to look at, actually, we're also looking at autoencoders to see whether we can even better compress some of the data so that we can stream out all of them reliably.
Okay, thanks. So I'd like to turn now to the question of designing the next generation of very large scale scientific experiments. There are many examples across different fields of physics, particle physics, major astronomical telescope plans, gravitational wave detectors. To take one example, there is a US concept for a next generation gravitational wave observatory that has 10 times the size and sensitivity of LIGO. There are major design decisions now starting to be being considered for this. And I believe the case is similar across other fields more broadly. And so the question for the panel is, in your fields, where do you see the big opportunities for AI approaches to actually accelerate or maybe even make possible at all truly optimal next generation facilities? And that question is open to Daniel. Would like to go?
Yeah, I mean, so as you had mentioned at the beginning, so I started in operations, but I am very convinced at this point that the bigger opportunity is in design, right? Operations, maybe we'll do things 10% cheaper or something like that. We'll do 10% better performance, but the real opportunity is in design. And I think in co-design, right? In how we are able to design new facilities, greenfield facilities that are AI first, letting us do it really completely novel things. Like I love what you were showing about all the different configurations for interferometers. We have something similar in the accelerator world. So like the accelerator world and photon facilities in particular were swept by this idea of the multi-band achromat. So until 10 years ago, everyone just used these basic bend magnets and X-ray sources, and all of a sudden someone came up with this idea like, I could put these quadrupole magnets in there, and it turns out you can get much lower emittance, much brighter beams, and that's completely swept the world. Now all of a sudden you have an enormous number of possibilities, a tiny fraction of which have been sampled by a small number of people sitting down and scratching their heads and thinking about what kind of magnets they could put together. There's another great example of, I think, we will see with AI just completely novel ideas coming up in the next couple of years. So yeah, I'm very excited about it.
Anyone else like to weigh in? Rana?
Everywhere I go, I make the same political speech. So I'll just make it here. I think making bigger detectors is always great. I love that idea, but there's a lot of room at the bottom. And I just want to say, like in astronomy, you see people who make a lot of the greatest discoveries, they might only have a 2-meter dish, but the secret is in the cleverness. And I always wonder what we can do at the small scale. And typically we're using normal scaling arguments, and that's why we make bigger detectors. But down at the bottom, there's still a lot of room. If you look, for example, at gravitational waves, the signal to noise ratio for a gravitational wave, if you just consider the noise of space-time, it's something like 10 to the 11. But then when we detect it, the signal to noise is only 10. And so I would say, I would give us an F- grade on transducing that signal. And why is it so bad? It's because of our materials physics, really. So we're all sort of talking about optimizing things that we know how to simulate, but the real problem is at the materials level. So you look at all of these fields, so many people are stopped by the fact that we have too many two-level systems. And we have two-level systems and thin films all over the place, and it leads to 1/f noise and cryogenic detectors and microwave detectors and the LIGO mirrors and superconducting qubits. And why can't we solve this problem? And it's probably because we don't have a simulation good enough to tell us how to generate a macroscopic thin film which doesn't have any two-level tunneling systems. And that's a kind of problem I don't know how to solve, because the machine that makes those things is sort of mysterious. I don't understand how it goes from the deposition chamber to a little microscopic film. It seems to be different all the time. And we don't really know how to model it because we don't have a full quantum simulation of the thin film. So we're using, density functional theory and other, what I would call cheats and heuristics to do it. But where are we, how far are we from the point where we can write down the requirements for a bespoke new kind of detector material and then just have it atom by atom fabricated? If we could make nuclear clocks that had a stability of 10 to the minus 21, we'd be able to detect all kinds of things. It's like Archimedes said about the lever. If you had an oscillator good enough, you could detect everything. But we're limited by materials, really. Like, we calculate all we want, but we don't know how to make the ultimate devices that we need for the future. And so that's my feeling. We can scale up another factor of 10, but then what are you going to do? You're not going to make a particle accelerator that goes to the moon and back or something like that. Not with my budget. Anyway, there's a proposal. There's always proposals, but I think we've got to work small first, and then we can scale up those futuristic devices. That's my political point.
Okay. Anyone else like to weigh in?
So because again, my background is more on the circuit design architecture, right? So I'll talk a little bit about opportunities to maybe integrate AI to the sensor front end and readout, right? So again, I've mentioned this in the previous replies that a lot of bottleneck is in the data, right? So I also work, besides SIPMs and SPATs, I also work in ultrasound and also CMOS image sensors. So I think the common problems I see is that people want to see all the data, or let's say the physicist or a scientist want to see all the data, but then the engineering sometimes cannot afford to supply all of that, right? Because of the constraints that I mentioned. So I think one opportunity to integrate AI to the sensor front end is basically to intelligently compress and filter out some of the unwanted signals or unwanted data right at the source, right? So that we can still supply the scientists with the data they need, right? So I think a lot of the directions that Javier mentioned with FPGA farms, we also need that word of co-design, right? To make sure that any AI we put to compress or to filter signals at the source can be let's say executed for the inference, right? Within the power budget and thermal budget. So that's why for my field, for example, the type of design that I shared with you, right? We call it the ASIC, right? So application specific integrated circuits. So that is basically the extreme end of specificity, right? So this chip can only do one thing, but it does it really well in terms of energy efficiency, throughput. So of course, it's hard to program, but then if you want to integrate any AI to sensors or detectors, I believe that's the way to go, right? In terms of finding the right AI model, which probably has to be small, right? We are looking at maybe several megabytes of model capacity at most, and then run it on a dedicated ASIC.
Okay, thanks. Anything to add, Javier?
Maybe I'll just I think I agree with everything everyone said. Maybe I'll add one thing, which is, yeah, I think there is this really cool opportunity. There's actually like a AI for muon collider workshop happening at the same, like right now. I think there is a really cool opportunity to use AI to help us overcome a lot of challenges, like people said, for magnet design, which is one of the big bottlenecks for how do we build the next collider. And I think AI will help us find creative solutions to a lot of like the challenges, because as Rana was saying, we're not going to get the money we need to build the next collider, if we do everything the same way we've been doing it forever. So we really have to get clever. And I think AI is going to be a really useful tool in that, in finding clever solutions.
Okay. So we still have a few minutes left in the panel that we would like to open up for questions from the audience. If you do have a question, please just come up to the front and I'll hand you the microphone. Sure. Walk over to the aisle and I'll give you the microphone, Rich.
So this question is for Rana from a non-expert. So one of the crucial things is you take a discrete problem and you make it continuous so that you can do some optimization, right? And so the question I have, and you had different designs, right? So the question is, it seems like the simulation of the model is crucial to making this work. How do you get that to a point where you know you're getting the right answer?
Yeah, that's I would say in 2025, it was sort of hopeless because it was half hallucination. And I mean, everyone's got their own answer for it, but I have a bunch of trusted sources that I use. So we have a lot of analytical limits that we have to use for sanity checks. It's like, I think when you do any kind of, when I did finite element modeling 20 years ago or something, it was like 50% garbage, I would say. Things wouldn't converge and things like that. So we always had to use analytical truths to base it on. And now we have a different chain of logic where we have tools like, let's say, ANSYS, and there's good mechanical engineering benchmarks, and people do real robustness tests because they use it for things like building bridges, which matters, not like detecting gravitational waves. And so we just compare against all of those things. Now, when you're in a strange regime, like how does that black hole vibrate when it hits something like this? We don't have any kind of ground truth, but I think that's why we do experiments. So I get the sense of your question, though. If you're doing a really expensive optimization and then you want to make a bet and design an experiment on that, you really have to have a lot of cross-checks. So I think the only way I know how to do it is to use a bunch of classical tools, which maybe take a lot longer to run, but you can run some 24-hour, really expensive runs to verify all of your cheap AI runs. That's so far what I'm doing.
You all discussed at great length using AI in order to find creative solutions to our problems, for example, lack of funding in certain areas. Given that creativity is a muscle that must be exercised, I'm curious how you manage in your own work and in thinking about the field as a whole, just being a director of AI's creativity versus continuing to find ways to exercise your own and improve it.
So again, maybe I'll speak from the engineering perspective, right? So again, maybe I'll take the problem setup that I mentioned earlier as an example, where we have all of these trade-offs. Because engineering is all about trade-offs, we have to make that decision. So I think eventually, even if we have AI to help us, humans should be still in the loop to make that final decision. And again, let's say, given the examples that I provided earlier, let's say analog versus digital, power, thermal, latency, all of these trade-offs. I think AI is good at finding the optimal solution if you give it this set of technologies. But I think AI at the current stage is still not very good to find that push of technologies that will push the parietal front further, right? So that means at least at this stage, I think for engineers, AI is very good to help us find the optimal with, let's say, design space exploration. But we really need the human creativity, right, to push further and to invent new technologies.
Here, I have
follow-up comments and questions. So one of the things, it's clear that AI becomes more and more powerful. It will provide you, muon colliders or even FCC in terms of designing, reducing cost and things, which will be very, very important. But I'm concerned about students and postdocs, and both for high-level PIs, you can use those things as a very powerful tool. But for students and postdocs, they may feel they are not adequate to make any more creative ideas because AI is doing all the jobs. It's so powerful. So how do we maintain students to be motivated to think differently, come up with creative ideas, and then essentially you have to fight against AI. So how do we deal with that as a? I mean, I'm the chair of the department, so I have to worry about these things. I don't know. I don't have any answers, so I just say I agree with you that it's a worry for me. I also feel like some of these tools are so powerful, it feels almost addictive. Every hour you spend with it, it's so productive. You can write brand new papers and things like that. But it also, I feel like it erodes my brain somewhat. That if you're just sitting there and on your screen, you're not spending enough time with your mind thinking about a particular problem. And just for me, the way it works is I have to sit and meditate about a problem for a year or something like that before I really grasp it. And I feel like because these tools are so powerful, they're removing that feature. I would have said it was a bug before, but now that it's gone, I feel like it's a feature. And we've all seen that phenomenon, I think, where you're talking to your students and they can't seem to answer anything unless they have their phone in their hand. And I'm afraid of that world where we can't just stand around a chalkboard and think about physics. But, on the other hand, I feel like that's one of those generational things. And people used to tell me these things. How would you possibly know everything if you could just download any paper that you want and you don't have to trudge to the library and spend your time in a journal? But we got over that fact, and the fact that you can download papers is just fine. It doesn't bother us. We write a lot of code. We don't have to go to the compiler level anymore, but that still feels okay. I haven't opened up numerical recipes in a few years. I still feel okay about that. I think some of these things will go away, but I think the creativity thing and what about training the brain? I think that's a serious problem, and we're not going to be very happy with ourselves if in a decade we've completely undermined that whole educational process. We'll be left with people who can't design new instruments, and then we'll just be waiting for things to fall out of the cloud. And I think that's a major mistake if we allow that to happen.
I can say something maybe from my perspective. If you have another question, we can move on. Yeah.
So I definitely agree. For the engineer, AI can speed up for the engineer process. But for science, I mean, how you think about the data will, especially some specific domain, will face the really challenging time to get the data. So what's the suggestion about the collaboration for the how to get more data, especially the medical or the biotech?
Sorry, really quickly, for time's sake, that's going to be the last question for this panel.
So the question is how do you actually acquire the data sets? Is that?
I mean, how your opinion regarding for the biotech and the medical field, the data permission, or I mean, if we want to change something, we need the data. We want to build some new idea, want to verify this idea can apply for it's working. So how you think about the opportunity or some way to solve that problem? Yeah.
Well, I don't know much about the bio world, but I will say this. I mean, I think we've thought a lot in the DOE system about what our role is going to be in this AI revolution. I know academia has done the same. And at least on the DOE side, the answer is exactly this, is that providing the data. So if we're going to train the next generation of scientific AI models, that only happens with the data, right? So the reason that we have AlphaFold is because we have the protein data bank. And if we're going to generate any of these new breakthroughs, it's because we need that data. And so I see our role, at least I'm speaking with my DOE hat on, is our role in building these big facilities. Sorry, not our role broadly, but our role within this AI revolution is going to be how we generate this data. And I think the most exciting opportunity for us is actually generating this data hand in hand with the people who are training the models. So this is getting back to the stuff I was talking about with BACS before, but it's not that we want to just go out and randomly collect data, as we did with the PDB, where we just had thousands of people effectively randomly collecting protein structures over 60 years. If we want to do this more efficiently, we really need the models working hand in hand with the facilities, collecting the most important data. As you go to these very high dimensional systems, I think that random is not going to cut it. So we really need this hand in hand collection of the data, training the models that are tackling the problems that we care about.
Okay, I think we have exhausted our time, so we'll have to leave the questions there. Let's thank all of our panelists one more time. And I believe we now have a 10-minute break scheduled. 5 minutes. Hi, good to
where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answer.
Several trustees of UC Riverside had a reception, so he joined us. Within a short time, I think we have bonded quite well. So thank you for your friendship. Thank you for your vision in supporting science and supporting AI. Thank you to the co-organizers at the Center for Experimental Cosmology and Instrumentation here for co-organizing this symposium. Accelerating basic science with AI, advancing AI through fundamental research. That is a beautiful message. So thank you for crafting that message. For those of you who are less familiar with UC Riverside, I want to use this opportunity to explain the UC Riverside and my priorities. So I won't talk about AI and science, but I want to talk about our priorities. So UC Riverside, we're one of the 10 campuses of the University of California, but we're the only research one university in inland Southern California. So Southern California, inland Southern California. So what that means? So that's 2 counties usually. So Riverside and San Bernardino. The 2 counties together, we have about 5 million people. If you look at population and consider the 2 counties as a state, we rank number 25. So right in the middle of the 50 states. Of course, we're not a state. We're just a small region of California, but it's a big, big region, 5 million people. It's one of America's fastest growing and most diverse region in California and in the country. Much of the nation's supplies go through our region. If you drove here, you will know 3 highways all merge at the corner of our downtown. Highway 215, 91, and then California 60. So that's where our goods get moved around. From the port in Los Angeles, they come here and then they get redistributed. I told Chuck a joke last night when I was either in Michigan or the University of Georgia. If you order something from Amazon, usually it took 2.5 days to get to your home. But here, if you order something in the morning, you get that in the afternoon. But the region is increasingly shaped by logistics, healthcare, biotechnology, advanced manufacturing, and clean transportation. Yet, despite of its significance economically, the region has historically received less investment in higher education, research and innovation, and healthcare than any other parts of California. But that is changing. And UC Riverside is at the center of that transformation. UC Riverside is a member of the Association of American Universities. So that's 71 leading research universities in the country and also Canada. As chancellor, I got to sit together with leaders from other top institutions like Harvard, Stanford, Berkeley, Michigan, UCLA, and so on. talk about important things that is important to our higher education industry. Federal funding, support for students, free speech, and all those are important things that are impacting all of us. But we're the only AAU institution that is simultaneously a Hispanic serving institution and also an Asian American, Native American, and Pacific Islander serving institution. Our undergraduate student body consists of 37% Hispanic Americans or Hispanic citizens and 33% Asian, Pacific Islander, and Native Americans. The two groups together is 70% of our undergraduate students. More than 40% of our students receive Pell Grant, and close to half of our undergrad are first generation. Yet our Pell Grant recipients and non-Pell recipients graduate essentially at the same rate. Thank you. So that combination in terms of supporting students who are first gen or Pell recipient, but being in the AAU is very, very rare. It reflects a simple but powerful truth, that is, excellence and access are not competing goals, but they can support each other. For the last 5 out of 7 years, US News and World Report ranked UC Riverside #1 in social mobility. So what that means is students coming in from an economically disadvantaged background, but they graduate here with our support academically and student life and university culture and everything together. They graduate and get great jobs, and then the salary compared with what they would make if they only have a high school degree is significant. So the story of UC Riverside is not a story of excellence or access. It's a story of UC Riverside achieving excellence and access at scale. So we are doing this with thousands of students each year, right? Graduating between 7,000 and 8,000 students each year. We do so while serving one of the most dynamic and diverse regions of our country. When I joined UC Riverside last year, I outlined several priorities that will continue to guide our trajectory. First, we're deepening our commitment to our students, academic success, and social mobility. We want every student to experience the full power of a world-class research university, not only through classroom learning, but through transformative experience that shape their lives and careers. Second, we're accelerating mission-driven research, innovation, and entrepreneurship. We're investing in faculty across the different disciplines. We're strengthening interdisciplinary research, expanding research infrastructure, and elevating faculty distinction. We invested in a campus-wide AI institute that support research, workforce development, and deployment of AI in all things we do. We are launching a Center for Entrepreneurship and Innovation, supported through a philanthropic gift of $6.2 million. The center will help students move ideas from the laboratories or classrooms to communities through ventures, startups, and new jobs. We're also creating the infrastructure to accelerate the translation from research into impact. Chancellor Torres mentioned about the Oasis Innovation Park. It is designed to be more than a research park. We envision it as a destination where ideas move more rapidly from discovery to the marketplace, where innovation translates into economic and social impact. It will be a place where students, faculty, entrepreneurs, startups, established companies, government agencies, and communities partner together, work side by side to develop solutions and create opportunities. Third, we're expanding UCR Health to improve healthcare throughout our region. We're investing in additional clinics. We're developing a plan for a specialty ambulatory clinic. Finally, we're strengthening partnerships that will support increased college attainment, workforce development, economic growth, and regional investment. Industry partnerships are essential as we expand research, accelerate innovation, create internships, support capstone projects, and broaden career pathways. So those of you who represent companies, we look forward to working with you. We also just launched a K-16 engagement council to coordinate our work with schools, community colleges, and regional universities. I know many of you are from the Bay Area or have ties to that area. We all know that many of the technologies and companies and industry that have transformed the world were built in Northern California. But I believe the next chapter of California's innovation will continue to be written there, but increasingly, it will also be written in Southern California. We believe UC Riverside can serve as a bridge to connect the North and the South of California, to connect Los Angeles to inland Southern California and the Coachella Valley, that is the Palm Desert area. Linking talent, research, entrepreneurship, venture capital, and economic opportunities across those regions. I look forward to exploring ways to work together to make this a reality. Thanks again to everyone for being here.
All right, next up will be Hartmut Neven. If you're still here, please come up.
The panel, yes. Does this microphone work? Yeah, it seems like it's. Bring the. So yeah, while the slides are being brought up, I wanted to thank the organizers for having me, and I have to say I'm from the very west of LA. That's where we live, and it's the first time I'm here in Riverside, and I'm rather impressed by the high caliber of the conversations, the attendees, and also the facilities. I should have come earlier. Okay, I'm trying to bridge the time here while we are working on the slides. So I wanted to give you a little overview of what the Google Quantum AI Lab has been up to. And I only have 20 minutes, so it will just be a little smattering of the different areas we work on. We are what people know as a full stack operation. So we build the hardware. So we have hardware labs and fabs in Santa Barbara, but then we build the operating system as well as cloud interfaces and applications for quantum computers. And yeah, okay, let's not touch anything. Okay, I keep continuing. So maybe you saw this just showing up there for a second. The mission of the Google Quantum AI team is to build quantum computing for otherwise unsolvable problems. And the way we achieve this, we formulated a roadmap how to get there. It has three components. There's a hardware, there's a software, and there is an access component. So I start with explaining you the system, the hardware. So imagine some snazzy pictures of our hardware. So the main message here on the hardware track is that quantum computing is happening, and it's going to happen rather soon. So we originally had a roadmap that had 6 milestones to get us what we consider to be a useful machine, which a few years ago we thought, okay, we need to do useful algorithms, like running some of the famous algorithms, you know, like Shor's algorithm, or do some work with quantum simulation. We thought we would need about 1,000. I think it's working now. Okay, because these are pretty pictures. I want to show you this. So yeah, we're now looking at the hardware track of our roadmap. And yeah, a few years ago, we thought to run the famous quantum algorithms, we would need about 1,000 logical qubits that can do about 10 to the 12 operations. But due to advances in algorithms and error correction, and also hardware architecture, computer architecture, these numbers have come down. So initially, we thought we would need 1 million physical qubits to realize such good logical qubits. But due to architecture, we think 100,000 is already enough. That's also because on the algorithm side, we have made progress. So 10 to the 12 operations are not really needed anymore. It's now less than 10 to the 10 operations. So with these improvements, we think our roadmap can stop at milestone 5, which is a commercially relevant quantum computer. And I should say we are already, out of these 5 milestones, we already did the first 2. So our team was the first to show computations that could run much faster on quantum computers than on any classical computer. We were also the first team to show that quantum error correction, an important technique to build logical qubits out of physical qubits, works in practice. And hopefully, knock on wood, later this year we will achieve milestone 3, which is essentially a module within a modular architecture that will make up milestone 5. And if everything goes roughly according to plan, by the end of this decade, we will have milestone 5. So in our own slogan is that milestone 5 is a new milestone 6. That's all we need, 100,000 qubit physical qubit machine. And let me walk you through some of the improvements that has happened that enable this acceleration. So one is computer architecture. So originally, we thought our computer would essentially be a large sheet of silicon with transmon, superconducting transmon qubits imprinted on it in a square lattice nearest neighbor connectivity architecture. But since then, this has evolved to a modular architecture where sort of each module will have several hundred physical qubits. And then those modules are connected in a higher degree than the nearest neighbor checkerboard surface code architecture to other modules. And that allows for more potent error correcting codes than the plain vanilla or the standard technique, which is surface code. So while with surface code to make qubits that can participate in 10 to the 10 operations, you need about an encoding ratio of 1,000 to 1, meaning you need 1,000 physical qubits to make one really good logical qubit. With these modular or codes that can live on a modular architecture, you only need 50 to 1. So that's over an order of magnitude improvement. And also we start to differentiate these modules. So there will be modules that are good for compute, then some that are for hot storage, think RAM, and then for cold storage. So even though the von Neumann architecture of quantum computers hasn't been developed, you see the emergence of that. Then the raw hardware has improved quite a bit. So initially our team sort of was known for good system architecture. We never had the best qubits or best of anything. There are companies that have more qubits, companies that have better qubits, but the overall system, and ultimately quantum computing is a system challenge. You need to run complex algorithms, and the overall system needs to provide good quality. But that has changed. So while originally the coherence times, essentially the key metric of the quality of your qubit, the coherence time measuring how long does a superposition state stay alive, these times have come down, or sorry, have come up recently by over a factor of 10. So we are now what used to be 20 microseconds. So now we are in 300 microsecond coherence times, and we are actually having first prototypes of qubits that are approaching a millisecond of coherence time. So more coherence time than our roadmap will need for completion. And what we keep checking on is how our error correction, how well it is working. I earlier bragged that we were the first team that showed, actually, the idea of quantum error corrections, of course, you orchestrate, you introduce redundancy, so you have more physical qubits than a single one orchestrated to one better performing logical qubit. And then the idea is the more physical qubits you have, the more redundancy, the better your logical qubit would become. And in 23, we showed this for the first time. But the community wasn't that impressed because we just improved it by a few percent, even though it was the break-even point. But then, since then, we did better. So now we can, as you go larger in the code distance, it improves by over a factor of 2. That made many quantum startups rich because, I don't know, you watch the stock market for quantum or for listed quantum companies went up after this 24 results significantly. But since then, it hasn't stopped. It's not published yet, but now the factor, the error suppression factor that shows how the error rates come down as you increase the number of qubits has now gotten up to, we call it lambda 4. And our milestone 3, which we hope to achieve, as I said, later this year, would require a lambda of 6, according to our own goals that we set out for ourselves. But I earlier said our milestone 3 is not just a memory qubit, it's a complete module in modular architecture. So you don't only want to show that it acts as a memory qubit, but you also want to show you have a complete gate set, including one gate that is very difficult to make. It's a T gate that is made in a protocol called magic state injection. And for this, you need to make magic states. And it used to be that making magic states in a quantum computer used to be very expensive. You used the process called T-state distillation. But member of our team, Craig Gidney, had developed a new protocol called magic state cultivation, not distillation, which is better by orders of magnitude. And we can actually, we just had a paper for the first time showing experimentally that T-states were made in a quantum computer. So you see all the pieces you need to build a large useful quantum computer are falling into place rather rapidly. And one mistake that I want you to prevent from making is if you just look at, oh, show me, let's say, on some algorithmic benchmark, how well are you doing? What's the largest number you have factored? And then you find, oh, it's still not even 21, so I have time. Or we have time, or you can wait. It will take us another decade to get to a useful machine. But that's not correct, because once you have a single module, that's like sort of laying the first mile of a freeway, then the next ones will follow rather quickly. And the single modules have improved in quality dramatically. They're kind of almost ready to click together as a large machine. So the progress will not be smooth, but go through rather steep jump. We also recently, so our team used to do superconducting quantum computing, or use this as a modality because this is a rather complete technology. But another modality, neutral atom computing, has recently made some good progress as well. And we didn't want to beaten sort of last on the final stretch to use for quantum computer. So to not take any risk, we decided we go dual thread and we'll do neutral atom computing as well. And if you look sort of at the scorecards of these two approaches to quantum computing, you see that superconducting are very fast. Now the physical gate times are measured in nanoseconds versus microseconds for neutral atoms. We also have shown already deep circuits with millions of cycles, because microwave control is very stable and the superconducting qubits don't go anywhere, versus the superpowers for neutral atom computing is that they have a flexible connectivity grid. The atoms are held, the atoms that realize their qubits are held in laser tweezers, and you can move them such that any two qubits that want to talk to each other can be brought into proximity, and a gate can be executed there. That's, of course, a rather valuable resource in computing. But the challenge for neutral atoms, as I said, the overall architecture is much slower. So it's an interesting computer science question. What is the more valuable resource? An all-to-all or virtually all-to-all connectivity graph, or much faster prefactor times? We will find out. And this graphic here shows what both modalities still need to do to become useful. So for neutral atoms, it's easier, or I should teach you a term in case you're not familiar with it. In quantum computing, we often talk about the computational volume of a computation the chip or the computer can support. It has a space direction, it's a number of qubits, and it has a time dimension, how many cycles can you run. So it's a space-time volume of a quantum computation. So for neutral atoms, it's easier to scale in the space direction. So they're already working with arrays of 10,000, order of 10,000 qubits, while quantum computing, superconducting quantum computing is more in the 1,000 order of magnitude. But in the cycle depths, the depth of the circuits, computations have been run with 10 to the 10 cycles, so very deep in the time direction, while neutral atom architectures, the record-holding circuits are only 100 cycles long, so not long enough for complex algorithms. So now the question is it easier for neutral atoms to scale in the time direction, or is it easier for superconducting to scale in the space direction? Again, we'll find out. So with this, I want to say a few words of applications, but let me check. Okay, I have 5 minutes left. It was a hardware piece. Let me maybe just go through a few selected topics on the algorithm side. So since the topic here is AI, let me focus on quantum algorithms that have a bearing on AI. So another point of pride for our team is that last year we had on the cover of Nature an article which was about the first verifiable quantum algorithm, or rather the first practical algorithm. This algorithm is called, or we nicknamed it, quantum echoes, and the technical term is an out-of-time order correlator. So this is an observable that you can either measure on a system like an NMR machine. And how this works is that basically you run your circuit forward for some time. For example, initialize all your qubits in the 0 state, and then you evolve your qubits under a Hamiltonian that describes a molecule. And then you stop and you run this circuit in reverse. So if you had no noise in your quantum processor, now you would come back to the start state. So that in itself would be boring. To make it more interesting, in the middle of the circuit, when you're in a deeply entangled state, you sort of tickle one of your qubits. We call this a butterfly operator because it's related to chaos. So essentially, this effect of the butterfly operator will then spread through your system. You won't come back exactly to the start state. And this is measured by an out-of-time autocorrelator. Now, what you can do is you can use a nuclear magnetic resonance machine and run this protocol there. And you can run this protocol on your quantum processor. And then this would allow you, for example, on the quantum processor, you make ansatz. You think, oh, I know the molecule I have in my NMR machine. I may not know it perfectly. So you leave a few free parameters. And then like traditional machine learning, you will just do gradient descent to make it such that the OTOC you measure on your quantum processor matches the OTOC you see in your NMR machine. And when these two match, then you say, okay, I know what my free parameters should be like. So this is an example for quantum machine learning. And we are actually starting to tackle proper open chemistry questions with this. Another example is we are often being asked, how does AI relate to quantum computing and how will quantum computing enhance AI? It was mentioned earlier, and this is actually an example I like to give, is a marvelous success of AlphaFold rested on essentially 50 years of collection of data. The protein database that was used in AlphaFold was started in the 1970s. It's very expensive to make such data. So with quantum processors, you can accelerate making high quality data sets. For example, it's often said, oh, AI can help us hasten nuclear fusion. But today, to create experimentally the conditions in plasma that are conducive to fusion reactions, this 1 second worth of fusion data would cost you $1 trillion to produce. But you can try to simulate these conditions in a quantum computer. And we did a little bit of this recently for material science, where we essentially we simulate magnon systems, and we simulate on our machine measurement methods such as neutron scattering spectroscopy. And essentially, we're able to make data sets of that high quality that we now feel emboldened to hand those to our colleagues at Google DeepMind. We have an AI for materials research group and say, hey, can you experiment with this? Maybe tell us whether this data has reached the quality where if you train a foundational model with it will be better than if you didn't have access to this beyond classical data, because all these algorithms I'm showing you could not be run anymore on classical machines. Okay, so I'm out of 20 minutes. I think I brought sort of some of the main ideas across. I have other fun pieces to talk about, but I will, oh no, this piece here maybe because it's fun I end with, and since I see Anima sitting here, this is something I had talked to her in the past. So the idea here is another way or an example how quantum computing could enhance AI. And the area we picked is diffusion neural networks. You may know that a product like NanoBanana, so they used diffusion neural networks to generate images. Yeah, and even how this works essentially is you start with a noise tensor, a noise image, and then these neural networks have been trained to sculpt a pretty image from this noise. And typically this noise is just classical Gaussian noise. So every pixel is picked from a Gaussian distribution. But we asked the question, look, in nature, there are many patterns we see, and here earlier we were talking about cosmology. When you look at the W map, the picture of the largest object we know, the universe as a whole, and look at this microwave background radiation picture, there's structure in there. And then if you go to an astronomer or a cosmologist and say, why are these structures in there? They will say, oh, these are frozen out quantum fluctuations from the early universe. But this process, that there are quantum fluctuations that get amplified from the microscopic to macroscopic scale happens often. For example, in weather, the butterfly effect was famously discovered when studying weather patterns. So we asked ourselves, hey, can we reproduce this? Instead of giving our quantum diffusion neural networks noise that is classical, let's produce noise patterns with a quantum circuit and see whether something changes. Again, I told you this is a fun note to end. We did this again for image generation. So here you see the comparison. You have a classical diffusion network or seeded, sorry, I should say the network was the same. Just on the left side, it's seeded with classical noise, and on the right side, it's seeded with quantum noise. And now you can judge which ones you like better. But the thing I wanted to maybe convince Anima of that if you do a multi-scale fluid dynamics simulation, maybe having quantum circuits as a subroutine under the hood from which you can take samples may not only improve the quality of images, but also improves the quality of simulations. Okay, with this, I will stop.
Thank you for that. And now we have our second panel. Chuck, if you would come up along with the other speakers.
If I could ask all my panelists to come up to the stage, please, I think that'd be great. Please. Yes. Yep, please, Ken. Wait, yep. All right. And we can turn on the lights so we can see us better. So that was a really interesting conversation and a presentation. I love those pictures, by the way. This really highlights, really so cool. Thank you, everyone. I know that we're running a little bit late, but we're gonna catch up a bit because originally we're scheduled for about 45 minutes. I think we can get it done in about 30 some minutes or so. We've already actually, during the break, we also already kind of had a bit of prep work before this. So anyways, really excited, to have this industry and sort of like the panel about, I know Chancellor Fu mentioned about economic development, how UC Riverside is so important to the Inland Empire. But certainly, as I said before, I think Southern California is so important. I think that a lot of the efforts that I myself have been involved in Silicon Valley, we want to really replicate the success of Silicon Valley to Southern California. And UC Riverside, it's a very important role to play in this region. So that being said, I do want to, I'm so honored to have Xia Wen, which is a chair of Professor of Physics and Astronomy at UC Riverside, with Ken, right, sitting right next to me, the three generations of Barish, right? Ken is Professor of Physics, but also a chair of the Academic Senate here at UC Riverside, with Wei Wang, which is the chair of Computer Science at UCLA, ACM Fellow, which actually I just participated not too long ago. And then Ryan was president of Acipus Enterprise, mentor himself, involved with a number of industry and Angels Network. So welcome, all of you. So, let's get started. What does Southern California innovation landscape look like from where you sit, from your perspective? Ken?
Well, from where I sit in the Inland Empire, I see it as a rapidly accelerating an opportunity to further expand with a lot of opportunities that are really complementary to other parts of Southern California, where we have different challenges and different opportunities.
Wait.
Yeah, completely agree, right? We are usually at the other end of Los Angeles, around the west side, right? So I would say that there's a lot of opportunity and actually very diverse opportunities, right? So compared to now. Northern California.
So I also sit in Riverside, UCR. What I see here is a place that is rich in untapped potential. So things like what SASE is doing, fundamental science is what will bring new technology, and already brings together engineers and people from different fields. And the landscape for me here, echoing what was said before, is that we are positioned to be the next innovation hub for Southern California.
Great, right?
I'd echo the comments of the other panelists. I think it's been an exceptional performer, Southern California innovation, but a lot of untapped potential. The socioeconomic diversity, the diversity of businesses, and the talent of research and academia. I think it's probably 3 to 10x under its potential, at least. But exceptionally in performance.
I love that what you just said, 3 to 10x that potential. And you, of course, mentor a lot of founders. As an investor, what are the ingredients you keep seeing Southern California founders, who go through breakthroughs, right? What do you see them in common?
Yeah, so in Southern California, it's interesting. When I grew up in Southern California and the San Fernando Valley, and then I moved to the Bay and lived in New York. And when I lived in, when I came back to Southern California, I've admittedly griped a little bit, saying, "Oh my gosh, I'm back in Southern California, back to social media and things of that nature, and not really business building." But then I talked to entrepreneurs again, and business is built differently. I think here, I think that businesses, they're built more on cash flows. They're built more as a traditional businesses than the Bay Area, where it's, oh, here's my next financing, here's my next financing. And it's not uncommon in the Bay that there are founders that created billion-dollar businesses that own 0.5% of the company because they've diluted themselves so much, versus companies in Los Angeles or Southern California that have created multi-billion-dollar companies that have raised $20 million. And I think that's because they grow differently. I think that Southern California businesses, it's growing by solving real problems that have real willingnesses to pay and can grow more traditionally. But I think also some of the exceptional founders that are more venture capital backed, the ones that I've seen that come out of academia, which is more so, I'd say, for this sort of audience, to me, the ones that have been successful are the ones that are able to step back from needing control. I found a lot of, mentoring a lot of founders, chairs of departments at, UCLA or Stanford and such, to be able to not say, I want 80% of the company. I want to control every aspect of the company. To attract the talent you need to grow the business, you need to kind of step back and let your technology mold into the market.
I love what you said, cash flow business. I mean, I think inherently, and of course, Scott, you can talk about that later because you're from Silicon Valley, and I know there's a panel and you share some insights on that. But I love what you said, that inherently companies here are very unique, cash flow, but really have their own uniqueness on that. But actually, on that related note, Shanwan, I mean, we're in an empire, and obviously location that shape the kind of research that gets done here. Can share with some of your insights that you see it from your perspective?
So being part of Inland Empire definitely shapes UCR campus and our identity. So the campus started in 1907 as an agricultural station, played a crucial role in the citrus industry, was an experimental citrus station. Agriculture is still a strength on campus and a priority. The unique vast geography and a diverse environment shapes opportunities and strengths. So we heard from Chancellor Hu yesterday about the term comparative agriculture.
Yes,
so
comparative agriculture. What a wonderful word.
We have a big laboratory right here.
Yes.
But I would like to say, so air quality, water quality, health services. But for the transformative technology, we really need basics research, basic science, and this has been demonstrated many times how basic research is what brings the next major shift, as opposed to simply following what is the fashion or the next problem to solve. So So what shapes the needs of this region, I think, is major what the basic research we have here and the development. There's a real need for transforming the region and having economic development, and the population here needs the high-tech workforce training that the UCR is playing and will play more of a role as we go.
Very good. Well, obviously you chair the physics department. I'm passing on the chair of the computer science department, right, at UCLA. And Wei, obviously you see, obviously you drive a lot of the talent pipeline in the heart of LA. What do you see it from your perspective, and how can they kind of, echoing sort of the regional aspect from your perspective?
Yeah, that's an excellent question, right? So at UCLA, we see that actually there's a great strength and coverage, right, for UCLA education, right? Especially like, for example, in science and engineering, and in medical, in medicine, and in entertainment business. So there's a lot of strengths, actually quite complement with UC Riverside, right? So, and also lately we have been talking about how AI fundamentally transform education, right? So how do we prepare for the next generation workforce, not just in computer science? I'm from computer science, but for all the disciplines. Yes. Actually, at UCLA, we actually have an active engagement in that discussion to see how do we sit down and change how professors and the TAs, right, should think differently, right? How students should learn things differently. So I think that is one area that I think that's going to deeply impact the field moving forward.
Yep, very good. Now, and from Ken's perspective as the academic senate, really looking at it from the entire institutional perspective, Ken, what's the honest answer from how things are moving, how quickly, and of course you see Riverside, as Chancellor Fu said, it's one of the fastest growing universities. What are some of those real opportunities that you're seeing?
Yeah, I mean, a university is a very large enterprise. So understanding opportunities in AI and how it's used and how it's not used really varies depending on what you're asking. I think in research, faculty, at least good faculty, recognize that advances come from technological advances, and AI is that, and we take advantage in our fields, in our local contexts. So I think that's pretty rapid. Faculty really jump on board, as well as our students. From a teaching and learning point, it's much more complex, because I think we do not have agreement. We don't really know how, we have lots of ideas, but different faculty approach differently, how to integrate, how to take advantage of AI, but also how to make sure that that we're not losing the fundamental core instruction that we teach. And it also varies very much by discipline and faculty by faculty. So each faculty has control of their own classroom teaching. And the third is the institution as a whole. And I think the institution can improve its large enterprise, supporting the academic enterprise. And there I think, can take advantage of many of the tools, but that's something that also is somewhat slow moving, because universities can only take so much risk in adopting technologies. So
I see. Actually, on that note, right, because you did mention that UC campuses carry a public mandate that private universities don't. How does that change? What's possible when you're trying to build something at the intersection of research and commercial impact, right?
Yeah, I think it depends in your local context, what your institution does try to serve multiple ways. First, we're as a anchor institution in the Inland Empire and economic engine, just bringing higher wage jobs to the Inland Empire is itself a public service. In terms of problem solving, there's problems in things like healthcare and healthcare equity, especially UCR expanding our medical enterprise. It's excellent opportunities, probably unique in the way that we're growing and underserved in the Inland Empire. agriculture, precision agriculture, in building sensors and using AI to optimize and understand crops, are two examples. So I think these are ones that can really have a partnership between researchers who are interested in these problems with industrial partners. And that's kind of the idea of this SoCal Oasis project itself.
What a beautiful name, Oasis Project, right? But actually, in terms of bridging, and one of the serious foundations is really bridging the gap between academia, like institutions, great institutions like UC Riverside, UCLA, we have like leaders here, as well as industry and capital, right? And of course, everyone says they need to all work together, but it rarely goes deep. And I want Brian to chime in. What does it actually take to make that collaboration real? And has anyone, how have you seen it done in a way that makes sense?
Yeah, so I'd say when I was at UCLA helping them bring a biodesign program up and running, for anyone not familiar, that came out of Stanford, and it's very much involved in taking industry and bringing it to the academics and bringing it to, the computer science, the bioengineering, the School of Medicine. And I think the core is you bring all the people at the same table and you listen and you try to solve a problem. So when you bring the biodesign program works where you have these fellowships, but a lot of them are focused in particular areas. So the example is it's not just intellectual solution making, but it's based on a problem area that industry is facing. It's based on a problem area, and industry is guilty of building solutions and trying to then take it and apply it to a problem. You want to actually be more problem driven and say, okay, we're going to solve this problem. So you have doctors bringing their problems to the industry, and then you have capital. Capital, we always want efficient use of capital, and we want ROIs often in some form or fashion. So to see that more clearly is always a de-risked element when you're investing in a company. And so to see when you bring all those players to the same table, as a capital player, you're saying, okay, well, this is de-risked because Terumo's in the, X company of billions in market cap is in the room. They're interested. It's technically feasible. You have the technical diligence here, and you have someone, the other is kind of the operator to then operate it. Who's going to actually operate it? And is there that, so I'd say bringing those stakeholders to that same table with events like this or through programming. Which, Riverside and other groups, it's also there in the MBA programs. It's there in a lot of different programs. So that's kind of the key.
I love that. I love what you said, which is addressing the specific problems of each region. In this case, I know that we're really big, into the agriculture, right? That's why Shanwan mentioned, and Chancellor rightly put it, the relative, relative agriculture or industry, right? Right. Yes. And so actually on that front, and more to come on that note, by the way, I do want to ask Shanwan, what is one thing, and the same thing for you as well, Wei, what is one thing that would actually accelerate this in this region, right, respectively in Southern California?
That's a difficult question. There are many things. This is such a complex problem and so many factors. I'm going to say one, which as we and this is a bit from the perspective of physics and astronomy chair, as we have faculty working on developing the instrumentation to detect the faintest signals, the most fundamental questions. We have faculty developing new quantum materials and spintronics materials, bio-inspired quantum materials. All these, we really need, I would say, one thing that will accelerate is investment in a top-of-the-line infrastructure. If we have the best labs, then that can be an incubator for new ideas. We can have industry being part at the same time in which scientists are answering these most fundamental questions. So I would say there's a need for a top-of-the-line lab here.
Yeah, and by the way, I think on that note, I you know, talking to Barry, and of course, you know, Barry's been amazing, you know, leading the team, and I have to say, my first visit ever to UC Riverside is thanks to Barry, your team, that really introduced, and thanks to Shanwen, you for hosting what a fantastic visit, and I encourage all of you who have not, and a number of you are here for the first time. Can I have a raise of hand? How many of you guys are visiting UC Riverside for the first time? Raise your hand if you. Decent amount, you know, probably like 25% of you, which is, you know, I'm so happy that we're actually able to get 25% of you visiting for the first time. This is amazing. And so I've seen what an amazing place this is and what an amazing job under your leadership, you know, Chancellor Hu. Thank you for your work there. But on that note, Wei, please, from your perspective, what is one thing that you want to comment on? You know,
because I'm from computer science AI perspective, right? So I know I'm personally aware there's many great ideas coming out of students, coming out of our young faculty, right? So, but you know, AI is moving very fast, right? So how do we quickly make sure there's you know, support to do the technology transfer, right? So, and without like the faculty, let's say, resign from being a professor and going to the Bay Area to do that. So that would be great, right? So then them stay as a faculty at, you know, UCLA, and then still have the opportunity to realize their dream of having a great tech transfer.
Right, that's a great setup, by the way. I love that. You really wet my mind, right? Because I want to, you know, like bring this to, you know, something concrete. Sierra is, you know, working with you and the UCLA team to build the AI Innovation Center anchored out of UCLA. But our ambition is really to extend across the UC system, including UC Riverside. What does Southern California actually need from a center like this, right? And what does it like? What does it look like with UCLA, UC Riverside building that together? What does success look like? Say, you know, Wei, from your perspective, for like in 5 years for the center and for the region.
Well, I would like to see that actually the center actually nurture and also support a lot of technology innovation and transfer, right? So from faculty and the student across the Southern California area, right? So of course, in the first anchored at UCLA, right? Because otherwise, I think because AI is moving so fast, right? So timing is so critical, right? If like half years later, you know, something like, you know, maybe already like lose its value, right? So that's why we want to have that opportunity so that, you know, anyone who have a brilliant idea would be able to have the opportunity to see that happen, right?
Yes. So great. People, brilliant ideas could be, you know, we can actually do it out of the center. Yes.
Yes.
Okay, very good. Shanwen or Ken, what would success look like? Either one of you can comment. Oh, Shanwen, go ahead.
How the success look like in 5 years?
Say 5 years, yes.
It would definitely include us having more partnership with industry and our students having startups, and we'll see transforming the lives here in the Inland Empire and seeing UCR playing continuing a bigger role in the economic development in the Inland Empire.
Very good, very good. And then 2 more questions real quickly. 1 minute each is Ryan. What's one thing that you're most excited about in Southern California's future that isn't getting enough attention yet?
I'd say the money from the growth capital from Silicon Valley coming down here more and taking advantage of all the resources that that Southern California has. Talk about agriculture, the hub here. There's an aerospace hub. Talked about biotech.
Yes.
I still think from a capital allocation perspective, compared to the untapped talent and research, is enormously a gap. And to see the capital follow that and create those companies, and then create the inertia where the exited founders then build new companies down here, and those exited first employees build new companies, and there's more of a snowball like there is in, you know, the decades that Silicon Valley has been built, for it to continue to happen here.
Right. Great. Wei, and then Ken can represent Riverside to comment on that one. Yep.
Yeah, so I think what I hope to see is that actually we are, we create like actually very diverse and balanced culture here, right? So for innovation and entrepreneurship, right?
Yeah.
So that actually that's, as Ken mentioned, that like, there's a local strength of like science, technology, right? Aerospace,
Yes.
biotech,
Yes.
entertainment
Yes.
business. So
Yes.
there's a lot of things that actually is very diverse, right? So I think these are untapped territory that we need to move into.
Yes.
And then also last thing last but not least is the education business, because
Yes.
we have so many universities
That's
in
right.
Southern California.
That's right.
So that I think many UC campus
Yes.
and other universities as
Yes.
well. So
Yep.
so I think together we should do something amazing.
Untapped talent, definitely on the count. And Ken?
Yeah, what's already been said, underappreciated is UCR and the Inland Empire, and
Yep.
really the opportunities and potential of this area.
Right. And my last question, and Ken, it's it's the one message I want you to share with people. Certainly, a lot of people are listening online because Serve Network, we actually have close to 700,000 subscribers. So we want you to share a message, one message to a researcher or a student, either at UC Riverside or UCLA or this whole region trying to figure out their place in the AI economy. What would you tell them?
Yeah, this is a unique and exciting time, and enjoy the ride and be confident and go full in. Students are better at this than we are.
All right, great.
Yeah, I think this is indeed an exciting time, right? So we're here to make the history.
Making history, great.
I would say exciting time and exciting and special place.
Yes.
Sorry, I just blanked. I would say you have the tools, and you are also agents of change. So not just following the fashion. So can't wait for what the future brings. Yep.
Yes.
I'd say experiment crazily and remember that your limits are only limited by the laws of physics. So go wherever, do whatever you want and just keep experimenting. People can't think of the world. They can't. If you showed someone a smartphone 40 years ago, nobody would think of it.
Yes.
So remember that. Really, let your imagination run wild with the tools that you have or can create.
Yeah. And in closing, I want to actually, as I was researching and kind of preparing for this panel, I mean, there's so many industries here in this region that has really yet been fully explored. And let me read that out, including entertainment, digital media, aerospace, defense, space exploration, wireless communication, semiconductor, healthcare, life science, energy, logistics, supply chain, hospitality, agriculture, and more. You can see there's so much potential here in Southern California. So I make my case. Thank you, everyone.
Thank you.
So we can maybe take a quick picture with the panel. I guess if I can, YC, can you help us to take a picture here? All right. Thank you so much. We're going to take a break, and then lunch will be until 2 o'clock, right? So we'll come back at 2 o'clock. So thank you. Enjoy lunch and do lots of networking, please.
One thing to add before we leave for lunch is yeah, thanks. That we have a bunch of students who have set up and postdocs who have set up posters on the patio out there. You may have seen some of them during the coffee breaks. So our poster session is during lunch. So if you grab a quick lunch and you have time to come back, there's a chance to speak to some of the students about the posters that are showing.
Good. Good. All right.
And mathematicians to work together I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SARE, I'm very happy to announce our first SARE competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SARE, I'm very happy to announce our first SARE competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SARE, I'm very happy to announce our first SARE competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SARE, I'm very happy to announce our first SARE competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
Evangelos Papadakis.
All right, that's a little too much, but thank you, Milo. Thank you so much. Thank you to the organizers. Thank you, everybody, for being here. I'm really happy to see a lot of people in here, also non-UCR people, and so welcome. And I hope you get something really useful out of this day. Maybe from my talk, maybe not, who knows, right? So what I'm going to do today, was planning to do, is to talk a little bit about kind of, as I've been reflecting on how AI interplays with my classical training, quote unquote, where does my kind of field of kind of knowledge discovery from data or data mining stand in the era of AI, and how does this help accelerate scientific discovery? And so this is the journey that I'm hoping to take you, if you are so inclined and not falling asleep after lunch. And so we'll see where that takes us. And so for now, let me just ground what I'm saying with just giving a short introduction to what I mean by sort of knowledge discovery from data. And so obviously on the one side, we have data. We can have pictures, very randomly selected pictures of coffee, of the beach in Las Vegas, very random selection. We can have online content, or we can have scientific data, which is kind of the talk of the day, right? And the common thing they have is that they are complex, they are huge, and they have interesting stuff inside. And so we have algorithms that hopefully do something smart, and those algorithms give us insights, right? That's kind of the life cycle of knowledge discovery from data, and those insights have to have some kind of properties, right? So for one, they need to be novel. Tell me something that I don't know about, right? And they have to be interesting, right? I don't care to know something that I already know. They also have to be scarce, right? There's known limitations of how many things a human can hold in their working memory. And so if our end customer is a scientist, let's say, then we would have to kind of adhere by the scarcity of the insights, right? And broadly, they fall under one of those three categories. So more traditionally, they can be descriptive. Say, okay, you give me a bunch of data, and I'm telling you, hey, there's K different things, 3 different things in your data. I don't know what they are, but they're distinct, right? They can be predictive. They can help you kind of anticipate and predict a target. Or, and even more excitingly, they can be prescriptive, which is they can tell you which action to take next, right? Which experiment to run next, which design of a instrument to test next, and so on and so forth, right? So this is kind of the picture, I would say the more traditional picture of knowledge discovery from data. And AI has a big role to play in advancing that and help us then advance our insights in science and scientific discovery. With that come a lot of challenges and requirements, right? And so off the bat, we have no idea what's interesting, right? Interesting itself is also a very subjective term. And so this lack of supervision that otherwise we would enjoy having and we would let us kind of do traditional sort of supervised machine learning is not there yet, right? A big challenge is to how do we integrate known theory, known physics into what we want to do, right? And how do we kind of do that gently in the model, in the thing, whatever the process is that we're doing, so that it takes advantage of this without biasing things towards a certain outcome, right? Explainability and interpretability is a big challenge and requirement, especially when you're dealing with not an automated process, but with, let's say, a scientist collaborator to whom you need to explain why the model is saying what it's saying, right? And so having a sort of way of connecting a decision, an insight to the data and to the model and to something that your stakeholder can understand is of paramount importance. And last but not least, sort of having your expert, your domain expert, opine on your models, giving feedback, being in the loop, around the loop, on the loop, whatever position you want them in the loop is also very important. Having engagement of the domain expert, right? And kind of as a side note, we wrote this book chapter a couple of years ago, Barry and John, two of my great co-authors, on sort of the deep learning revolution for AI for science, where we kind of outline some of those challenges in a little bit more kind of detail. But these are sort of a little bit the TLDR, if you will, of those challenges, right? The current state of things is that, classical methods, and by that I mean recently kind of revolutionized AI methods, are great. They can take us far, but they can take us so far. And challenges remain, and they're big. But with the use and the kind of the integration of modern AI tools, and by that I mean sort of large language models and the like, right, generative AI, we stand a chance in overcoming, or at least making a lot of progress in a lot of those challenges. And that's what I'm going to try to kind of showcase today by kind of taking us through a journey first on kind of purely classical methods and how they work and what insights they can give us and their potential, but then where they're limited and how, let's say, when we add AI into the equation, we can actually do much more, all right? And so the first stop has to do, it's an application. So first I'm going to try to ground all of us into what I mean by latent structure and latent space and so on and so forth, using my favorite definition. It's my talk, right? So then, and then we're going to take a few stops of some really exciting and important applications that I would like to share with you. And so first, let's ground what I mean by latent structure. So the simplest way of explaining it is showing this picture here, which is we have a lot of data points in this two-dimensional space, but there's actually three things in there going on, right? There's three main patterns, factors, components, whatever you want to call them. And even though there's, let's say, hundreds of points, there's only three things you need to care about, right? And so how do we now actionalize that? How do we discover this? That's what I'm going to talk about in the next few slides. Now, my informal claim, I cannot prove this to you. I have no such skills. Maybe someone else could, but I cannot. But it's an empirical observation that I've made throughout the years, is that almost all data sets have some form of this kind of latent structure, all right? And if that's the case, then the next question is, how do we leverage it? How do we find it? How do we recover it, right? And so one way that I found to be really productive and useful and kind of generalizable to a number of applications is to think of it from a linear algebraic point of view and to kind of define, let's say, if we can express our data into what we call a matrix, which is essentially an array of data, array of numbers, right? then we can start defining things about it. And one thing to define about it is what is the most elementary piece of kind of structure. And the most elementary piece of structure there is what we call a rank 1 matrix, the simplest thing possible in our data. And that can help us count how complex is the data that we have at hand, right? In this case, we have, let's say, those 3 blocks. We can actually write it as those 3 rank 1 matrices, meaning that there's 3 things in our data. And if I kind of put this and the previous picture together, there is kind of a connection between the space that this, what we would call a matrix factorization, would take me in order to be able to identify, let's say that this first rank 1 matrix corresponds to the blue component, the second one to the red one, and so on and so forth, right? And so that is one way of not only expressing, but also extracting the information from the data, right? Because you can imagine those are, let's say, important groups, clusters of data, structures of data that could be meaningful in me expressing the data and extracting those insights, all right? Usually, each one of those comes with some kind of importance, right? Not all of those are made equal. And in fact, reality, this is not reality. This is, actually, none of this is reality, but like, this is less reality than the next slide. So reality actually looks a little bit like this, where you have imperfections in your data. And let's say you have this big, almost complete kind of group of things that are very similar, correlated with each other, with the exception of a couple of holes, right? And so what happens here is that you can say that, well, maybe the most important thing that happens here is this thing ignoring those holes, and then everything else is much less important, orders of magnitude less important, right? And so there's mathematical tools been developed for a century almost that can allow us to confidently extract those kinds of patterns from the data. And those are the things that I've been working on for the last 15 plus years that I would like to share you some kind of vignettes with, right? Now, what I have sort of focused on most of my kind of academic career in different aspects of is when we have multiple such dimensions, where now our data form what we call a data tensor, which is a multidimensional matrix. And things beautifully kind of generalize in the way that I was introducing before, with the very important caveat, well, not really a caveat, but a very important note to make here is that once we make the leap from 2 to more dimensions, depending on what kind of mathematical tools we use, some of those tools allow for what we call uniqueness, meaning that they are able to extract the exact actual vectors up to permutations and scaling, which is very important, not up to rotations of subspaces, which, and again, this is the most mathematical of the slides, and I apologize if that is bringing us, different memories from college, but this uniqueness is a necessary condition for me going and saying that, hey, those actual indices corresponding to real-world entities are, in fact, involved in this particular latent pattern, right? Because if I don't have uniqueness, then this could be one of infinite solutions that I may be interpreting, and I may be interpreting noise. And so this is a very important thing that doesn't go as noticed as I think it should. And so now, hopefully with you all and our streaming audience, it will go more noticed, right? So this is kind of the artillery that the classical methods that I'm going to employ use, okay? And I'm going to show you examples. First example, just to ground us, is let's say, forget about scientific data for a moment, just for a moment, right? Let's say we have a Netflix style of scenario where Netflix is interested in telling us which movie to watch next, right? So you have users, you have movies, and you have time. When did they watch it, right? And so in this case, each one of those rank 1 components is going to be a different pattern going on in my data. It's going to underlie a quote-unquote genre, but not in the way that the studio defined, but in a way that is being defined by kind of actual viewership of people, right? And so using this, we can go and look at each one of, let's say, all those people who are, let's say, in their 20s are watching those horror movies at midnight. Okay, those are horror movie buffs, right? And so looking at that, having the uniqueness condition, it allows us to go and look under the hood into the factors and say, that's what's going on. That is what's underlying the data, okay? And that's very important because this will allow us, if the data was not, let's say movies, but it was data from, let's say, material science, material design application, and doing a little foreshadowing here, it will allow us to create hypotheses about our problem, okay? And we'll show an example moments from now, okay? So these are now, I'm gonna go into a few applications that are near and dear to my heart that have used this kind of methods. And before we reach the dotted line, these are classical, no fancy Claude-style AI involved, and see how far they can take us. And then we'll see how further using AI can take us. And the first one has to do with hunting glitches at LIGO. This is an application that Barry and John and I have been working on since actually Barry joined UCR, and this is one of my most favorite things, of me being at UCR. And so this application has a special place in my heart, but it's also a very important application from a perspective of improving the sensitivity of LIGO. So you've heard about LIGO from Rana's talk, and hopefully you are already relatively familiar. One thing that I wanted to highlight is that LIGO, because it's so sensitive, it was able to give us the detection, but because it's so sensitive, it also is, it suffers from what we colloquially call glitches, which are non-transient noise patterns that sometimes mimic actual useful science signal. And because they can mess with the science data in a very real way, this is actually this triangular thing is a loud glitch right in the middle of a beautiful gravitational wave that was being unfolded, right? And so because of that, we not only want to clean the data from it, there's a lot of work in understanding how to clean the data from it, but more importantly, trying to understand how and why do they emerge, and is there anything you can do about them in order to fix them in the detector? And that started an ambitious hunt for how can we understand the emergence of this type of noise by looking at tens of thousands of channels of sensors that the detector has and is recording in very high resolution at all times, right? And so we tried to look at this problem in this angle because we wanted to understand if we find a small number of channels, aka insights, right? This can allow us to try to understand, is there a mechanism which we can devise that produces those glitches? Can we test that hypothesis then and fix the glitch at its source, right? So that was the motivation for this. And we try to attack this problem in numerous ways. One way that I find it simplest to kind of showcase here is by looking at coincidence of high SNR signal in the main channel, the prime time channel where the discovery happens, and in any of the tens of thousands of channels that we observe, right? And if this is a coincidence, then we sort of how we create a tensor of channel by event, by, let's say, frequency. A feature here could be the frequency, so we can discretize the frequency space. And this allows us to now find events, high noise events, that behave similarly in the channel space. And that means that all those events had the same signature in all those same channels, right? And that's what a tensor factorization can give us in this case, right? We were able to identify known channels that are responsible, or at least they're known witnesses, as they call them, of glitches, and that was the first success, right? And the ultimate goal is to try to understand whether there is any way of devising a mechanism that can help fix those glitches. In the meantime, one thing that we wanted to understand is how do we, let's say we get a list of channels through that latent space factorization, right? How can we know if this is good? There's no supervision here. The tensor factorization gives us those things are correlated, take it or leave it. What do you do? And a really neat way of using domain expertise here is to say, well, how would one in LIGO use this information? One way of using this information is to create what we call a veto, which is if a certain condition is true, then this piece of data in the main channel is unusable. And what is this condition? The condition is this and that channel are active now. And if that's the case, if that is able to get rid of most of the glitches without getting rid of good signal, meaning has high true positive, low false positive, then it's a good set of channels. And so here we have a good example, here we have a bad example. So this was a way we found a domain-guided way of being able to rank and evaluate the goodness of those insights, right? And again, this is work that spans a lot of, many years and a lot of different formulations, but this is one that I find most instructive following the narrative that I just introduced. Moving forward, another application that we started much recently, and this is, when I put you on the spot, Sean's work over there, this guy, right? Is how can we use those classical methods and AI to design better materials? And so here's an example. We have different configurations, different parameters for the design that span the shape and different parameters for the size of the material, right? And quickly, this can become a combinatorial space, right? And in fact, whether we simulate it in a really fancy simulator or we actually synthesize and test it in the lab, evaluating all combinations is a really bad idea because this is going to be very, very, very expensive. And so can we, instead, having a small number of evaluations, let's say, of actual materializations of the material, can we find which one to test next? Or which one is the best combination of parameters, of design parameters for this particular property, let's say hardness of the material that we wish to create, okay? And so this we can absolutely formulate as a tensor problem where each one of the dimensions is a design parameter. If it's already discretized to our liking, then that's already set. Otherwise, we should discretize it in an appropriate manner. And each one now of the entries that we observe is a materialized material upon testing its property, right? So the entry is the property of the material after synthesizing it in the lab. And you can see that most of this tensor is empty because we know it's an expensive process, right? And so what we can do here is the cousin of what I described before, the tensor factorization, which is called tensor completion, that uses tensor factorization, uses the space that tensor factorization learns, the latent space, assuming it exists and finding it in order to complete the missing entries, all right? And so this will allow us to fill in not just on-demand queries, but actually complete the entire search space and be able to kind of find, at least to our best of our ability, the best material for that property. Now, interestingly, kind of mapping to the descriptive, predictive, and prescriptive sort of requirements, this can be descriptive in that looking under the hood of the factorization, it will help us understand and create hypotheses about the data. It's as predictive because it, by design, predicts the properties of a given material when we have not computed them. And it is prescriptive in the sense that we can then go to the lab and say, which material do we synthesize next to confirm whether our predictions are correct and to refine our model, right? And so this is now, we want to keep in mind how the kind of the life cycle could include our expert in this process. Some results here now, so this is a paper recently accepted in a great conference by Sean, so congrats, Sean. And two things I wanted to highlight that we get by assuming this latent structure. One is that we are able, because we're making this assumption, which is a strong assumption, sometimes latent structure is hard to find, right? And we can get into this discussion. But once we nail it down, we're able to generalize to the entire space. And what do I mean by that? When we are doing experiments, so at least our collaborators doing experiments, they're usually synthesizing the cheapest part of the space because that's what can be done quickly, and this can give us training data. Now, this is outlined by this kind of square here. Those are the different parameters that have been synthesized in the cheapest part of the space. And you see that if the errors outside of that are also small, that means that we can generalize more gently to kind of almost out of distribution samples, right? That means that it learns the outlying sort of structure of the data enough so that it can generalize well. And this method, Costco, is sort of one of the most up-to-date tensor completion methods that still underlines a latent space, and it gives us the confidence that this latent space assumption is able to help us generalize much better than other methods that do not explicitly make that assumption. Right? Another takeaway from here, and again, I don't wish you to understand this in 2 seconds that I'm flashing it, but we were able to actually generate a new hypothesis on the data that our collaborator from Lawrence Livermore had generated by looking at the tensor factors. Again, don't worry about what this actually represents. We've noticed a correlation between 2 different design parameters that was outlined by one of the tensor factors in the small dimensional space that we found. And this led to our collaborator being able to understand and create a new hypothesis that is testable in their lab. And so that's the other added value of kind of assuming and discovering that latent space. All right. Plowing through, now we're going into the era of AI, right? Now, what I've showed you here took a long time and a lot of head scratching and a lot of graduate student descent by Sean to actually be able to find the right space, and then for a collaborator to look at this and understand what's going on and figure everything out, right? And maybe there can be a better way, right? And so we're not wishing to do away with the collaborator or domain expert, but to empower them to look at the things that matter first and things that are more likely to be worthy of discovery. And so the first kind of step we did was to enhance this entire tensor pipeline with a little bit of AI flavor that allows us to rank the worthiness of those factors based on how likely they are to be understandable by a domain expert. And so for now, let's revert to movies. And so if we have a group of movies, we want to understand what they have in common. Well, hopefully we're all somewhat experts in movies, right? And so if I ask you what do those movies have in common, one thing they have in common is they enjoyed around Christmas, right? Even though, let's say, Die Hard is not specifically a Christmas-themed movie, one could argue that it is enjoyed by viewership standards around that time. If I showed you this, The Room, the major motion picture The Room, as well as other similar movies, even though you may look at the description and it's a romantic whatever drama, it actually is enjoyed in an ironic fashion, right? And so can I automate this process with an AI? And the answer is yes. And we actually have a running demo that allows us, given that we have a large language model that understands the domain, and it understands movies here, but we'll get to the domain question later, can we understand if the LLM understands it, right? So does the LLM understand if this component is good? And so we have 2 tests here. One test is, can you tell me which other movie belongs here, right? And if it gives me a correct movie, then it probably understands the domain. And then I inject a fake movie or I inject a fake item, and I say, can you tell me which one is the odd item, right? And if it can exclude that, then it most likely understands what's going on, right? And so we can use that now to rank and rate the quality of components in a way that allows us to sort of be able to give the most high quality components to our domain expert, and then they can kind of work with that, right? And so that's the first step, but the last step, which is work that Jordan over there, I'm going to put on the spotlight now, is involved, has to do with how do we take this into the actual domain and put our money where our mouth is and see whether this can actually help an actual experimentalist do their job. And this is what we did here. And you know, in the 4 minutes, yes, please, 4, 3, okay, 3 that I have, I'm gonna really compress it, but Jordan over there, he's studying fear in mice. We're trying to understand the underpinnings of PTSD and fear of generalization. It's a very manual process. You have to hack away and place the sensors on the mouse and manually label the data, and then take my class and learn how to do tensor decomposition, and then try to apply it in your data and then make discovery. And so what we ended up doing was, can we automate this, make Jordan's life easier, and let her focus on what is the next step and what is the next hypothesis she needs to test in this entire kind of problem space, all right? And a few highlights, since I'm running out of time, is one key thing that I would like to also push here is that we identified the certain concept of in-context learning as a great proxy for interacting with domain experts. Long story short, in-context learning is this emerging property of large language models, foundation models, that without any training, without any actual weights changing, you can give examples of if this is this, if this is X, this is Y. If this is X, this is Y. Give a bunch of examples in your prompt and then ask, if this is X, what is Y? And this actually ends up being a really good way of doing nonlinear regression. So it actually works very well in many different problems, including if you show a bunch of examples of mouse behavior, can you annotate it automatically? And turns out we can much better than doing other machine learning methods and very close correlated to what the domain expert said. And in the end, the other thing I wanted to highlight is now using, again, in context learning, we can use similar concept to what I described before, but feed relevant information of behavior neuroscience papers to the LLM and allow us to be able to have the LLM rate, the VLM rather, because we visually give the context, to rate the concept discovered in terms of how worthy are of discovery. It will give a discovery score of from garbage to really good, right? And give it a kind of a written sort of description of why it deems it worthy of discovery. And turns out, actually, on the one hand, it is what Jordan wrote, and on the other hand is what the LLM wrote, obviously on a different set of data, which tells us that, in this way, we're actually able to allow experimentalists to focus on what they want, and this price to pay for them is for them to give us a few examples of what they want, what they're after, and how do they grade, things we discover, and with that, we can actually able to help them discover things. And with 0 minutes left, I would like to thank students who are in my lab and collaborators listed in order of appearance for all this great work. I know nothing, right? So this is all because of great students and great collaborators and people who feed us throughout the years. And thank you all for staying awake after the lunch and being in my talk. So thank you so much. Questions or no? Right?
Wow, what a riveting lecture, Vangelis. I think all of us agree that you do not know nothing. Please stay here for the panel that you're going to be on. Next up is a panel, like I said, for AI for stimulating and analyzing scientific data. It's moderated by Steve Choi, assistant professor at UC Riverside. On the panel is Vangelis, who we just met, although I assume many of you are familiar with, Kimmy Wu from Caltech, Simeon Bird from UCR, Jianming Bian from UC Irvine, and Scott Clark, CEO of Teleria Scientific.
Yeah, thank you, Vangelis, for this excellent talk to set us up for this panel. So welcome to this panel on AI for simulating and analyzing scientific data. I'm Steve Choi, an experimental cosmologist here at UCR. And earlier today, we discussed how AI is transforming scientific instruments and detector operation, not just operation, but even design. And this panel will focus on the next stage of the process, using AI to simulate complex systems and analyze massive data sets, and ultimately learn new science. In the interest of time, we're here with this distinguished panelists. I'll first ask each of them to briefly introduce themselves and their research before we jump into the discussion.
Should I start? Okay. Hi, everyone.
I'm Kimmy Wu. I'm an assistant professor in physics at Caltech. My day job is observational cosmologist. And what that means is that I take data from telescopes to learn about the universe. So the connection to AI in my work is that, so in cosmology, we make maps of the universe at different frequencies. And for many, many, many years, we bin this kind of time order data in pixels. And for many, many, many years, people then extract summary statistics from these maps. And then compare that to some cosmological models, and then ask, okay, how much dark energy there is, how much normal stuff and dark matter there is. But because of AI, we can now, instead of going through this intermediate step of summary statistics, we can go directly from the map pixels to the model parameters that we are interested in to learn about the universe. And some of the specific things that me and my group think about is how to model some of these previously, well, still analytically intractable distributions that describe our cosmological fields through some of these generative models and make it possible to do massive inference on big data sets.
Thank you very much. So I'm Simeon Bird. I'm an associate professor here at UC Riverside. My research is kind of a bit similar to Kimmy's, but from a theoretical perspective. So I'm trying to use the large-scale structure of the universe, by which I mean like maybe 100 megaparsecs or 10 to the 8 light years, to figure out something about fundamental physics, like the mass of the neutrino, the properties of dark matter, that kind of thing. The way we do that is we try and build a big simulation, of everything in the universe. We compare it to the real universe. In practice, this means you run a whole bunch of simulations, maybe 100 of them, and then you build an emulator, a machine learning model to interpolate between them.
Hello, my name is Jiaming Bian. I'm a physics professor from UC Irvine. So I'm co-chair of AI/ML forums in 2 major neutrino experiments, NOVA and DUNE. And over the years, I've been working with computer scientists to introduce state-of-the-art neural network machine learning method in neutrino experiments. In early years, we work on this convolutional neural networks to first introduce this neural net to neutrino experiments, or even say our HEP experiments. Later, we introduce transformers to reconstruct neutrino images. And in recent years, I'm mostly interested in using this, large multimodal AI and foundation models for neutrino reconstruction and analysis.
Hey everyone, I'm the odd one out from industry. My name's Scott Clark. I've founded a couple AI startups. First one was based off of my grad school work doing Bayesian optimization to help people solve high-dimensional, black box, noisy problems. So everything from recommender systems with Netflix and fraud detection at Amex to hedge funds making a bunch of money with their algorithmic trading policies. Sold that to Intel, ran AI and HPC for their supercomputing group for a while, and then started my next startup, which started as an AI testing and analytics company and has morphed into Talaria Scientific, multi-agent harness to help accelerate computational science and ground it with multi-fidelity HPC algorithms. Really excited to be here.
You just saw me, so hopefully you, yes, I'm that guy who just talked, yeah.
Yeah, thank you. Right, to get started, so the theme is on how AI is changing science is done. And I'll first ask Simeon. So your recent work has shown that AI can emulate cosmological simulations orders of magnitude faster than traditional methods. So looking ahead, will future cosmologists like yourselves and others spend more time designing simulations or designing AI models?
Yes. So I'm going to controversially say that those will become the same thing. So I think that what will happen is we're going to end up embedding the AI models into the simulations. Probably as, there's part of these models that are kind of hokey. And it would be better to replace them with an AI coarse graining of some higher resolution, more fundamental physics thing. I think that's what we're going to end up doing.
But any aspects of physics that remain?
Oh, right. That's right. You asked me another question. Yeah, so probably I would say the bit of physics that is hardest to simulate is how black holes accrete gas and how that gas affects the things around it, right? So that is very, very hard to model. Even on a fundamental level, it's hard to model. I think we would try and put those into the simulations. We would try and connect the very small scales around the Schwarzschild radius of the black hole to the larger scales, the 100 megaparsec scales. That's very challenging at the moment because we don't even really know the scaling relations that they're supposed to behave. I think AI might be able to help us with that.
So I'm hearing, so AI is making computation much faster, but the understanding the underlying physics could still be a challenge. Is that a?
I think so.
Yeah. I want to turn to you, Kimmy, about on the observational side. So modern cosmology increasingly relies on AI throughout the analysis pipeline. And so where do you think AI is making the greatest impact? Accelerating inference, perhaps finding and mitigating systematic uncertainties, or even uncovering new physics?
Yeah, I think of the results that have come out in the recent couple of years, accelerating inference is definitely what we've seen AI done within my field, cosmology. So to give you a couple of examples, so in these cosmological parameter inference, we have to calculate a model. So the likelihood computation is very fast, but the model computation is slow. So with an emulator, we can reduce a several second computation to fraction of a second. So not only are we able to explore more models, thus making our result more robust because we can do all the test case that we want to do. So maybe that's addressing the systematics aspect of it as well. We can also now explore models that would have been computationally impossible before. So one of these things that I recently learned is, okay, not only do you build an emulator of the model computation, you learn the model computation during the Monte Carlo process. So some of these like extended dark energy and dark matter models that we would not have explored at all, we are now doing and exploring it and testing it against data. So I thought that's very interesting. Another aspect maybe relating to some of the things mentioned before, some of these higher dimensional inference problems that was impossible now. It's because of AI and HPC. We can do now, and there are two ways to see it. We know that at the pixel level, there are more information than the summary statistics level. So conservatively, we know we have more information. So in principle, we can learn more about what is in the data. So potentially there is some new physics to be gained. And if I'm on an optimistic day, there might be things at the map level that would have been not possible to learn at the summary statistic level. So I think it's quite exciting that we have access to that now that was impossible before.
Thank you. So maybe I'll turn to Jimin about your work with multiple detector subsystems, where you explore AI systems that can learn jointly from these detectors, but also human input. And do you envision future experiments to be built around unified foundation models instead of these individual separate reconstruction algorithms?
Yeah, thank you. I think it is a very promising direction to develop a foundation model for, say, more general HEP experiments. So we already seen very, very good science. So from different scales. So small scale, so you can train the foundation model for, say, specific detector, but different configurations in the same experiment, and you have very good result to improve performance. And also, say, in different experiments with different type of data, So if you train like using say Dino model or say ME, I see very nice say progress that be able to say, so you have a pre-train for say foundation model, and then you test or retrain it with just a handful number of events to do this fine-tuning. You got very good result. It's very robust and very flexible. And to the larger scale, if you use a large model like say vision, say what we call vision language model as a backbone, and it can say even introduce the human input, right? So you combine both image input, detector input, not just from different experiment, different detector, but also from humans input. And in this way, you can introduce humans to understand and teach new neural nets. So to this direction, I see very promising, say, progress is already happening, and it works. And there are also many tests to test the robustness. For example, you change the geometry, you change the resolution, it works. So that I would say I envision this definitely a very promising say direction to develop foundation models for say experiments. Particle physics may be even larger, the entire science, right? All different say frontiers. However, the challenge part, I do see it. So the first challenge is the data. So, so at least in the high energy physics, we have the tradition that each collaboration just hold their own data. Well, we have our own secret. They want to make the first observation, right? There's a barrier between experiments, say, preventing us from sharing data. So this, but public data and open data is definitely indeed a need to develop this foundation model, especially when we want to build a real foundation model that's for everything. So the availability of data is problem one. And problem two, in my view, is so how to unify this different types of data or different formats. So different detector have different pixel map and different say resolution and different configuration, completely different geometry. And more general, there are different say type of data, right? Not just the detector images, but also you may have the different metadata, you have different say knowledge, right? So you want to introduce like documentation from different domains. And then third, how to involve people in to improve and to train or to control the AI. So there are many different formats, and how to unify them, how to say specifically, so how to say do the tokenization. That's very challenge. Different group have different solutions, and then if we really want to develop a unified model, how to unify? Listen to whom? That's a very challenging part. And practically, there's another challenge issue, which is the data Monte difference or simulation data difference. One, say, critical point, say, criticism for this in general AI thing is, so sure, you do a very good job, you show very nice result in your simulation. But what about we move this to real data? There's an fundamental inconsistency because of uncertainties, because of the model, and how you solve it, how you prove that the AI is robust enough. That's a big challenge. But we have different methods, we have like Bayesian analysis, right? We have uncertainty estimate, but so out of this AI sector, there's still lots of skeptical idea and a lot of arguments, right? They criticize us like say like what black box, right? So, but our obligation as AI say scientists is to open this box to show that our method, AI method, is checkable, foundation model is validable, right? And the uncertainty is valuable. Right, so how to convince the people, non-AI people, not everybody pretend they are AI person, but how to say convince the traditional physics scientists that AI method is trustable, and we have very scientific and say very say clear standard to evaluate AI method, right? So not just for foundation model, more general. How to do this? How to communicate with a more traditional say a group, I think is a very challenging part.
Thank you, Jimmy. I want to expand on that robustness of using AI for science and turn to Scott and ask, because scientific AI is beginning to do more than just analyze data, and it is helping guide our decisions in science. And so related to these comments, what level of reliability should we be demanding before AI becomes part of this decision-making loop?
Great question. And I think you really nailed it when you said that guide. Like, we should hold ourselves to the highest level of reproducibility and reliability when it comes to a final result. But you don't often need that ultimate level of granularity to decide what to do next. Like, imagine you're walking through a forest and you need to decide what path you're on. You don't need to know your location down to a micron to be able to say, oh, here I am. This is where I'm going to step next. At the very end, maybe when you're going to plant your flag on the summit, you want to be able to make sure that you're actually at the summit. But along the way, there's a bunch of multi-scale, multi-physics, and multi-fidelity problems where maybe a surrogate is good enough. Maybe using some of the methods that I think we're going to hear about in the next talk to use a neural operator to simulate a PDE will actually get you far enough to make that next idea, that next discovery. And you can always back it up with more classic analytic methods, and there's numerical solvers for PDEs, et cetera, that can help you, though, kind of make this flywheel spin faster and faster. And I think we're finally at the stage now with AI that we can solve a lot of these more undifferentiated grunt work style problems and just give you enough information to make that next step. Use the human to sample out of the distribution, but then use the AI to fill in behind you, do some of this translation work that was spoken about before, but really use that to decide what to do next, and then go in and backfill with really high resolution, really high fidelity models.
Right. So building on that, Vagelis, your keynote really emphasized this knowledge discovery that's being powered by AI. And we ultimately, as scientists, care about understanding more than prediction. And what advances would you say are still needed for AI to contribute directly to the scientific insight?
It's a great question. I mean, you said it, right? I mean, the focus should be broadened from just prediction, right? Not everything is a predictive task. It can be posed as such, but then if you optimize for that, then you'll have all sorts of kind of byproducts of you optimizing for that, right? So I don't know of a universal solution. There may be one, but then I think at least thinking about, can you know, what is the problem you're trying to solve, right? Put that in the forefront and not try to shoehorn an existing method to solving the problem, but then optimize for the problem you're solving. And whether that is predictive, then that's great. If not, then maybe try to think, how would you express that best in a way that solves the problem? Like an F1 score to me means nothing if that doesn't solve the problem, right? So like you can have 100% accuracy and have a useless solution. And so it's always about what are you trying to solve? What are the requirements, and what are the metrics you're trying to optimize for solving that? I think if we try to understand that better for a given problem, that allows us to go beyond quote unquote just prediction. I mean, prediction is great, but then moving beyond that, I think is a goal that I would encourage.
Anybody want to?
Maybe I'll just jump in and reiterate that, having ran a Bayesian optimization company for about a decade, I would say one of the best things about an optimization algorithm is you can point it at anything, but one of the worst things is it'll go where you point it. And so like making sure you really understand your objective functions and how to build that up. And even something like F1 score is a composite metric of other metrics. And you can kind of continually add that on. But I would say no matter who we worked with, from like the smartest hedge funds in the world to the intelligence community, there was always one more metric. Whenever you'd give them an answer, they'd be like, oh, but it didn't take into account this. And I used to think that was like, oh, that's a you problem. Like you told me to optimize f of x or g of x or whatever, and I did. You didn't tell me about h of x. But in reality, that objective function solicitation, that taste, that knowing what it is that you're actually looking for is the only way to actually direct these methods.
Mm-hmm. Right. So along the way, probably there's a lot of compressing of data and things happening, and across very different fields that you guys are working on. And So how do we know what information can safely be compressed away, and what scientific information should never be lost?
Yeah, okay, so okay, how do I would like to put this in a way of say methodology way. So how do we know that? I think we need first say theoretical guidance, and then say actual experiments. So for example, in neutrino physics experiment, we do one thing. It's say we have a type of detector called liquid ion TBC. The way that you measure the event is basically you make projection to read the a real 3D say particle information from two views. And then there's an issue to reduce the redundant say information, because when you make projections, so there's a ambiguities or there's redundancy. So the way that we do is we actually find a paper written by say Professor Terrace how? Yeah, called L1 minimization, and it proved in the CT imaging that this kind of redundancy can be removed, or as long as image is is sparse enough, you can use this L1 method to do the minimization. And then we take this guidance and then we use it in our neutrino experiment, and it works. Okay, and then we have a significant reduction after this compressing, say in this 2D projection in the problem. And on the other hand, we also need to test. So we have the theoretic guidance, and then we have to test with real experiment. So once we develop this reconstruction method, we test it in the simulation data, and we really compare the compressing efficiency, right? Say in data in the prediction and the simulation, it works. And also we check we really do not lose any information, useful information. I think that we need to go both ways to make this to first say identify what kind of thing can be thrown away in this compressing, and also we need to use the same method to make sure that we do not lose any useful information.
Yeah, so I think, I mean, this is not a new problem, right? This is the same thing we've been doing all along, right? It's that we have this messy data and we have to come up with some summary to it. And we should use the same tricks that we've been using all along, which is to use the symmetries of the data to work out what is useful, right? So in cosmology, of course, there is a translational symmetry, which is that every part of the universe should be in some sense the same, right? So we should be able to we take an angle average over everything, right? We take a power spectrum, we throw away the positional information, and we use things, we combine things that are, according to the symmetries of the problem, the same. And that is how we compress it. And I think to some degree, the AI models are capable of learning these things on their own. But when they find a way to compress it, we should ask, is there a symmetry that they are using to do the compression? And if there is, then we should keep that compression. Otherwise, we should look for something else.
Could that lead us to, wrong or non-physical directions, though?
I mean, it could. So we'd have to check it, right? I mean, so I don't know if this came in about, I don't think this is a CMB lensing thing, but in weak lensing, certainly there's a program of trying to extract the maximum amount of statistical power from the weak lensing maps. And they ran a neural network on it, and it produced a great deal of power. And then they went back and they looked for new summary statistics that could reproduce, could pull out 95% of the information the neural network pulled out. And so they were able to find such a thing that pulled out maybe 95% of the Fisher information that was in the neural network. And once they had done that, then they were able to have a high physical confidence on it, right? But the neural network told them there was something to look for.
And I think doing it backwards from that is a great way to discover the new methods or something that maybe you didn't even know you were looking for. Of like, oh, I can extract 95% of that, but like, let me go find an actual physical law that describes it 100%. But I think especially, and I know hallucination hasn't become as much of a thing as it was 2-3 years ago, but I think we already have really good solvers. Like the Department of Energy has been pushing out great numerical and analytical methods for decades. And so if you use that as a guardrail as well too, it's basically you can tell the LLM like go do whatever it takes, but you're not allowed to break the laws of physics. As long as you constrain it and harness it with those laws of physics, then you can let it go pretty crazy. And then you can come in after the fact to try to explain it and things like that. But I think that's the real difference is it's almost like having here's the test set. Here are all the unit tests that you're not allowed to break when you're upgrading my application. We have unit tests as scientists. They just happen to be the physical laws. Just make sure that you're actually running your continuous integration, and then you can actually make sure that you're not hallucinating new science.
So in discussing the limitations of these expensive first principle calculations are being replaced with AI surrogates, and can someone comment on where you think AI-driven simulations may be breaking down today, and what weaknesses we may not be talking about?
I'm simulating. I'm simulating building. Yes, yes. Okay. Well, I'll go first then. Okay. So one thing that I've noticed is there are certain scaling laws that are kind of emergent in galaxy physics, right? Generally power laws between different masses or different temperatures, different densities, and in reality, these are very tight laws. When they come out of the AI models, they tend to be kind of softened, right? So it'll discover the law is there, but it'll soften them, and it won't be fully confident of it. And so the other way around can also happen, right? That it will be overly confident that a scaling law is really the right scaling law when in reality it's actually softened. So somehow it needs to know the difference between laws that are laws of physics and cannot be broken, and laws that are, well, this is kind of, laws that are things that are often true, right? So I think that's I don't know how to teach it that, but I think that's what it needs to know.
Anybody else want to add? We should. I don't know how we're doing with time, so maybe it's time to open it up to the audience for any questions. There's a few hands.
Yeah, so this is just a question for Scott. You mentioned that you essentially created a startup that, well, it was just an AI tool for hedge funds, right? Am I getting that right?
It was general black box optimization. And so we still, like Netflix used it for the recommendation systems, American Express used it for the fraud systems, hundreds of academics used it for their papers. We gave it away for free to academics.
Okay.
We made a lot of money from hedge funds, which let me fund everything else, but yeah.
Oh. Yeah, so my question essentially is, right, so I believe there was some study at Wharton and NBER which stated that when you let AI agents essentially trade, right, there was some level of market manipulation that occurred, right, even though they didn't explicitly instruct the bots to conduct this market manipulation, right? So how do you see AI progressing in these hedge funds? And would there be any sort of regulations or restrictions on the use of AI in the financial world?
That's a great question. Well, I think whenever you're applying any new technology to any new field, you need to be thinking about the second order and third order effects. And I think there's often unintended consequences. Some of those can actually be beneficial. Like you could make an argument that like high frequency trading has created market liquidity that didn't exist before and price discovery that didn't exist before. But at the same time, you do have potentially correlated strategies that can cause flash crashes. And so I think like anything, there's trade-offs, and you just need to be aware of that coming in, and regulation comes in to make the trade-offs societally that we don't make as individuals.
Thank you.
Thank you. And you mentioned that there are these physical laws, like the scale laws, and when you're designing a network, how would you go about implementing those as domain knowledge into your model? So like what part of the architecture, or how does that change depending on what architecture you're using?
All right. I mean, so again, you can lay them in as constraints to your harness. Again, I think of them like tests basically, but it needs to, depending on what level of fidelity that you require. If I just need to quick pass, see whether or not something works, or if I want to be able to see something maybe on a short time horizon, then using an FNO type method might be great. If I'm designing a new reactor, then I'm probably going to want to use the like finite element analysis, like all the way down to high granularity, or some combination thereof. But I think it's up to the user to have this sliding scale of fidelity and scale for their problems. Someone ask a question that I don't have to answer so the other panel can talk.
Yeah, this question I want to direct to Dr. Wu, Bird, and Bian. Apologies if this is trivial. I graduated high school a month ago, so I'm just going to try my best to sound professional and like very smart like you guys are. But when you guys go into astronomy, and you mentioned Dr. Wu using LLMs in the actual, or sorry, Dr. Wu or Bird, putting LLMs inside the actual like models and simulations themselves, how do you guys account for the physics and the other like the context of the situation itself with the models? Because when you're modeling black holes, right, you talked about gas emissions. That's very, very complex. And how do you account for all the different physics of the situation when you're making those models, like the surrogates? And yeah,
that is actually a very smart question, because I don't know the answers to that, right? I mean, we're still working on that. That's a very good question. We would test it many different ways. We would check that it produced reasonable answers in a variety of situations, and we would check that it tried to obey the laws of physics as much as possible. But actually, we actually don't know really what the right answer is, right? I mean, we can't build a black hole and go next to it and look at it. So it would be hard. Yeah, that's a good question.
Yeah, maybe add to that, and also addressing one of the earlier questions about your models have to obey certain physical laws. For my specific application, I need simulations that have certain statistics. So we then, once building it, and we find smart ways to build it to learn from more expensive simulations. So we build surrogates. And we find smart way to do it because we know there are certain scale invariance properties. So we train at specific scales to actually get the accuracy we need. And that requires a little bit of physical intuition. You don't just throw a simple generative model on anything. And then you build these tests to make sure that this model that's built is valid given the applications that you're using it for. So are we out of time? Yes. So yeah, we can chat more offline on specific examples of how these tests are designed in my specific application.
you all very much. That lovely panel. Quick reminder to those of you who are asking questions in the audience, please hold the microphone closer to your mouth so everyone can hear. Unlike the AI systems that we were discussing, the microphone cannot accurately predict what you're going to say. So yeah, just be cognizant of that. Now, please join me in welcoming the Bren Professor of Computing and Mathematical Sciences at Caltech and former Senior Director of AI Research at NVIDIA. Please welcome Anima Anand Kumar.
No, that's good? Okay, awesome. Yeah, and I guess this one okay. Thank you. Thank you for having me here. Thank you, Chuck. I mean, we first met when you came to the Caltech AI and Science Conference, and I'm really glad that you've grown this theme into so many locations across California, and I'm looking forward to seeing more of that. So
that was a fantastic conference.
thank you. So more to AI for science, or what I like to call AI plus science, because it's really this deep integration that I personally have been working on for a number of years, and now it's really gone mainstream. So I'm really thrilled to see that. When I started at Caltech almost a decade ago, there was this idea that AI could be helping in sciences, although back then it wasn't very clear how that would be, because deep learning would require so much data. So what is the real impact? And now here we are a decade later asking questions about AI pushing the frontiers of scientific discovery. And indeed, with the language modeling era, a lot of that has been framed in the lens of AI scientists, right? Like AI coming up with new ideas, maybe AI replacing scientists. But I think I'm less interested or even skeptical that they would really be replacing the scientists, but AI not only is about collaborating with scientists or replacing their ideas, but really asking whether AI could solve the critical bottlenecks we have in scientific discovery. Because if you think about lots of areas of sciences, we were talking about physics, we were talking about material discovery, what is the critical bottleneck? Anyone? What do you think takes the longest time, takes the most resources? Okay, but what does even data mean? I mean, data collection is to train AI, right? But is that really the goal if you want to discover a new material? So either is, okay. Let's say I have infinite money. So what do you think is the, yeah. Yeah, so right. So that is like adding better insights to AI. But what really is the critical bottleneck? Yes, thank you. Because you can come up with lots and lots of ideas, but how many of them do really pan out? And we've seen this with AI. That's why a lot of, especially experimentalists, are very skeptical, right? Like, for instance, there was a DeepMind paper talking about 100,000 new materials. And then after that, I think scientists from Berkeley lab pointed out, many of them were, you could an expert could quickly rule out and say, oh, no, they can't even be synthesized in the lab. But there were many others that was more nuanced. And so you couldn't possibly go test all of them out. And so that's one of the dangers of AI being used for scientific discovery. Because if you now multiply lots of bad ideas, that's like instead of finding a needle in the haystack, you get a bigger hay, right? So that's almost counterproductive. And so this is where we should be careful in what I believe is the overhyped field of hypothesis generation, where just lots of hypotheses being generated for their own sake is not that useful. But on the other hand, what's useful is if those are verified. If instead of experiments, I could guarantee to some extent, of course, there's always could be approximations, but at least some level of confidence that they would work out in the lab. So those are the ideas that would be more highly priced. And in areas like in math, that's where I'll talk about lean. In fact, we did the first open source framework combining lean and language models. So you're not just taking language models at their face value, but lean will be verifying those mathematical claims.
But in other areas like materials or in physics, it's not just about symbolic verification, right? We may need to do experiments, and instead, can we do simulations? And if even those simulations are very expensive, can we now have AI that understands and simulates the physical world at different levels? And if it can be done much, much faster than traditional numerical simulations, then we have the ability to not only speed up the scientific discovery process, because AI is differentiable, we can also now do inverse problems like inverse design and, Okay, I don't want to join this. Let me see. I just disable the Wi-Fi, so that is not a problem. Yeah, so that is the theme when it comes to asking if AI can really push the boundaries of scientific discovery. Now I don't know why it suddenly stopped working. Yeah. I would really prefer, please don't go all the way there. Oh no, it's just, okay. Okay, no, it's not working suddenly. This one. Oh, this side, okay. Okay. Yeah, so we want to think about AI that can understand different scales, could be from the atomic scale, understanding bigger structures like proteins for biological modeling, all the way to even planetary scales if you think about modeling the weather and climate of this planet. And so depending on the problem of interest, you could be spanning multiple scales. For instance, we did modeling of the aerosol in coronavirus, where at the molecular level, we were thinking of how calcium ions bind to the proteins in the coronavirus, but then the macro scale behavior of how the transmission happens across individuals. This was in the early part of the pandemic. And so that's a multi-scale modeling problem. And same with weather modeling, you want to be able to capture the details of fluid dynamics, and that requires usually high resolution simulations, especially with traditional numerical methods. So could AI help us speed up these kinds of simulations? And what we see is we are able to do that many, many orders of magnitude faster. In the case of weather modeling, we have models that's tens of thousands of times faster. In case of plasma simulation in nuclear fusion, more than 1 million times faster. So you're getting this immense speed up because AI learns not only the phenomena at a certain one particular scale or resolution, we have these frameworks called neural operators that learn across multiple resolutions. And so that's what I will be talking about today. And of course, one challenge is we may not have all the data to begin with, but we have mathematical models, we have equations, and now can we make our AI not only depend on data, but also incorporate these knowledge of these equations, right? Such as partial differential equations. So we'll call that physics-informed AI. So AI doesn't just rely on the existing data, it can also incorporate either constraints from physics, symmetries, and other kinds of domain properties that are very different from the bidder lesson that you see with language models and standard image models. Because here, if you think about scientific discovery, it is an extrapolation problem, right? So you really want to go beyond what is known. So you likely don't have the training data for that, because then it's not a discovery problem. So if you have to go beyond, then you cannot just train a model narrowly on the data that's already available. And so where will that additional knowledge come from? It has to come from other sources, like these mathematical equations, like PDEs. And so as I've mentioned, the neural operators can incorporate both. They can incorporate data at multiple resolutions, as well as physics constraints at multiple resolutions. So to kind of conceptualize the idea is here I'm showing the simulation of the clouds. If in a standard neural network, so neural network where the inputs and outputs are at a fixed resolution or a fixed size, you zoom in, because it's a fixed set of pixels, it gets blurry, right? There's no further detail than the resolution on which you trained your model. On the other hand, neural operators don't have this limitation. The inputs and outputs are both modeled as functions. So you can keep discretizing this function to any resolution. So you can keep zooming into finer details, either by providing more data, like for instance, climate simulations, we have data at different resolutions available. Or in like DFT calculations for material modeling, we have different levels of theory. So more and more finer, refined simulations you get, you can train the same model with. And you can also incorporate physics constraints. So what just the data doesn't tell you, for instance, satellite data is in a coarse resolution, you can add in physics constraints of the relevant kind. Could be energy conservation, other kinds of constraints, but make them at a finer resolution than the data you have. So in that case, you even exceed the accuracy that just the data by itself gives you, because physics is giving you more information than purely the training data available. And so that's the concept, that we can do all of this and capture multi-scale phenomena that wouldn't be possible with neural networks that were just fixed to one coarse resolution. So let me show you some success stories over the last many years that we've been applying neural operators. Perhaps the most famous one is weather modeling. We created ForecastNet, the first AI-based high-resolution weather model, almost 5 years ago. And it's tens of thousands of times faster. We were the first to also permissively open source the model. This was when I led the team at NVIDIA back then. And it's under the NVIDIA Earth-2 platform. And it's been used by not only lots of weather agencies, but also startups, big companies. And so really like that changed the notion that you needed traditional weather forecasts run on big CPU-based supercomputers, right? Because instead of that, you could now miniaturize and run this on your local gaming PC with a consumer-grade GPU and run like 2-week forecasts in under a minute. So this is a massive speed up of tens of thousands of times. And of course, the idea was, will weather scientists really trust this? So how do you kind of gain their trust? And so we worked with ECMWF, which is the premier global weather forecasting agency from Europe. So they hosted our model, and they were able to make it really widely accessible to weather scientists. And that's where you could see that day to day, not only these forecasts were lining up with what the traditional weather models did, but to everyone's surprise, when it came to extreme weather events like hurricanes, it even exceeded what traditional weather models could predict. For instance, in this case, it's a bit dark, but you can see that the one in orange, the ForecastNet, our model, was able to predict landfall several days earlier correctly compared to the traditional forecasts. So soon it became clear that AI wasn't just a cheap substitute for traditional forecasts, but can exceed now both in accuracy as well as being much, much faster, right? So this is not a trade-off. This is a clear win. And so why does AI get all these benefits here? The speed is clear because we are not only moving from CPU to GPU, but more importantly, we are able to subsample in a way when we do those calculations in traditional PDEs, you need very, very fine discretizations. Whereas in a neural net, it's just a few layers. In our neural operator, which is a kind of neural net architecture, we have these few layers that can give to very fast inference. But the other aspect is, okay, maybe you got lucky on this one hurricane. How do you kind of systematically evaluate success on rare events like hurricanes? So the correct way to do this is, when it comes to rare events, is to really ask, do I have a calibrated model, right? Can I correctly predict the tail risk? Because that's what we mostly care about. We are in California, it's sunny every day. It's pretty easy for any model to predict that. So that's not the interesting piece. The interesting piece is, do we get extreme weather events correctly? And when it comes to this, we want to think about creating larger and larger ensembles. So in this example of hurricane, you can see where it originates in the Caribbean. You want to perturb it with appropriate noise distribution, so you have a spread, and then you want to see where the different tracks go. And then you can kind of count within a region how many of those tracks hit that, and then you can assess what is the risk of making landfall in this specific region. This specific local government can then go make policy decisions that are really critical for saving human lives. And so how do we ensure that we can correctly calibrate, especially to get the tail distribution correct? And this is difficult, right? I mean, most of the time, the typical events trying to get the probability distribution correct is what people hope for. But can we have AI models not only be faster and accurate on typical events, but also be getting the right tail distribution, which really matters for weather forecasting? And this is also a great example of working closely and talking to the domain experts, because what do they really care about? The metrics they care about may not be the typical machine learning metrics. And in this case, the focus is being on these tail events. And what we did was to take ForecastNet and then do the calibration with a much larger ensemble, in this case, thousands of ensemble members, and then be able to show that, yes, it does get the tail events correctly. And why can't we just do the same with our current traditional weather forecasts? I was very surprised that operational weather forecast, so the one that you see every day as official forecast, uses merely about 50 ensemble members. So if you think about statistics of just 50 quantities, then we know that you cannot get the tail events that accurately, right? So here the speed of AI is not just that I save more energy, I'm cheaper. It actually can now lead to better tail risk characterization, because I can do much, much larger ensembles than what was possible before. So this is AI pushing the frontier in weather forecasting because of the ability to do much larger ensembles. So in this figure here, you see that this was the Berkeley lab researchers who took our ForecastNet and showed that it can correctly capture like the 95th percentile heat wave. And of course, we just came from Europe, where there is a really massive heat wave. So these kind of like extreme events, being able to capture that accurately is very important. And then in the latest version of ForecastNet, this is the version 3, we said, let's now train with this new loss function. So what is called CRPS is a way to capture the full distribution. And of course, we want to make sure it's also on the sphere, because the Earth is a sphere. So we are now calibrating and training the model to match the probability. So as I said, this is what the weather scientists care about, and we are matching the training to satisfy those needs. And here you see now doing the full ensemble rollout. So you can now not only get one answer, you can get lots of different answers, and you can get probabilities as a result of that, and doing that very, very fast. So doing this in under a minute. And there is a systematic evaluation of all kinds of metrics. And this is the other message I was saying from the beginning. When it comes to AI for science, it's not about one metric, right? There isn't just like, oh, perplexity, I'm done. And of course, with language models too, there is entire suites of evaluations. And similarly, when it comes to weather forecasting, there is lots of different metrics, and you want to kind of be good on all of them. And that's what we show, that we're kind of on the Pareto front and state of the art in all these different measures. And so that's what is like what a foundation model should be doing, like being good at multiple things. And then you can make it a more trustworthy weather model, because when it runs in practice, when it comes to determining impact on human lives, you really want to be thinking about all these different metrics. So what else helps? So as we said, we incorporate the fact that the Earth is a sphere. Seems very simple. We're not flat earthers, but every other weather model decided not to. They said, it does not matter. I'm going to pretend the world is a rectangle. use a standard transformer or a graph model, whatever that may be. So why does it matter that we should incorporate those symmetries? Honestly, it doesn't matter if you just run the weather forecast for a few days, right? Because it just like kind of any effects of winds is only moving a little bit further. So you might find some difference, but it's not so clear. On the other hand, if you roll out for long, like I did here, and this model here, assumed the world was a rectangle, this one didn't, and this is Antarctica. So what happened with you saw earlier was that the distortions start building up on the poles. And so as you run more and more steps autoregressively, the errors build up. And once you assume it's a rectangle, it just goes haywire, right? Because the world is not a rectangle. And so adding symmetries matters more when it comes to extrapolation. Because the bitter lesson says, oh, ignore all that. Scale solves all the problem. But scale cannot solve an extrapolation problem. The minute you go beyond what the training data has told you, right, to a bigger extent, to you go significantly towards extrapolation, scale is not enough. And that's where aspects like domain symmetry, in this case, spherical geometry, was really helpful. And here you see being able to do like a year-long rollout, while having only trained to predict like the next 6 hours and a little bit of fine tuning over multiple steps. So it was never trained to do a whole year rollout, but it's able to keep that stability. And so this kind of extrapolation is where symmetries helps a lot. And when it comes to predicting climate, which is what the Allen AI Institute built on our ForecastNet architecture, you want to do long rollouts, and you need architecture like one that uses spherical constraints, as well as adding other energy conservation laws, and also training on other conditions like different carbon dioxide forcings to really be able to talk about not just the present weather, but possibly future changes in climate due to different carbon dioxide. And so far, it showed you an example with AI replacing traditional forward modeling, what we call like the modeling of what happens to weather in next time step and so on. And so instead of solving partial differential equations from ground up, like what traditional forecasting did, we used AI instead to learn to forecast that. So that's called forward modeling. But in so many areas, what you have is an inverse problem, right? And in the case of design, the inverse problem is, what is the best design that satisfies certain constraints, does the job in the best way? And so there's some really great examples of this. This is work I did while at NVIDIA, where I showed that you could improve the mask design significantly for lithography. As we know, lithography is one of the critical bottlenecks in chip manufacturing. And in order to kind of account for the distortions that happen, can we now optimize what the mask is that kind of is aware of what the lithography is going to do for it? And so you can, because AI models are differentiable, the forward model of lithography can now be used to do the optimized design of masks. In the most recent iteration of this, what we did was to extend this kind of notion for designing gates in quantum dots. I don't know where Hartmut is, but oh yeah, there you go. So, this is an example of where for quantum dots, it's much more sensitive even compared to classical chips to be able to do this kind of design, right? Like to pool electrons, what is the best configuration of gates? More nonlinear, more challenging. And we now have a chip that is fabricated. We are in the process of testing. We're very excited to see like how much step up that AI can do compared to how humans can design chips when it's so highly nonlinear and non-intuitive. Another such example is in nonlinear photonics. Again, humans are, I think, fairly good at designing cases where the phenomena are linear. But when there are high levels of nonlinearity, we aren't that good in coming up with the right intuitions. Another example is the medical catheter, where we wanted to reduce bacterial contamination. So we designed these triangular grooves. And you see under the microscope of what our AI designed catheter is doing, it is pushing out all these bacterial particles, and none of them are really able to swim upstream into the human body, right? So this is under the microscope. The idea is there's barely like one particle here trying to swim upstream. But we measured 100-fold reduction in bacterial contamination as a result of AI helping optimize the design. And so here, again, fluid flow is not an intuitive thing for humans to design, but AI can really do a great job at this. So all these are examples of AI both accelerating forward modeling, as I showed in the weather forecasting, but also being able to come up with optimized inverse designs. And in terms of inverse problems, another great example is medical imaging, being able to really tell us what's inside the human body. And there's really no ground truth, right? So you have to be kind of coming up with the right uncertainty measures as well. And in many cases, we not only do better speedups, but we can also learn the prior from data itself, which is another benefit that standard numerical solvers are not able to do. So you can really be learning prior from data and do Bayesian inverse and coming up with good posteriors for also modeling the uncertainty effectively. So to give you an idea of how AI is not just about speeding up medical imaging, but could be even coming up with better diagnostics. In the case of lung ultrasound, the problem is quite challenging because in the lung, you're trying to measure the aeration level. So you're not looking for solid lines. You're looking for what are these called as B lines, where it's very blurry, and you're trying to count these blurry lines to say how much of the lung is aerated. Right? So when the lung is more diseased, it gets more challenging to come up with the right level of aeration. And instead, we said, let's just reconstruct the lung tissue and predict which levels, where it's aerated and where it's not. And so because we're doing the forward modeling as the wave propagation, and we first train on synthetic data that is rightly calibrated to lung tissue that is dissected, so you can really train on large amounts of data, further validated on dissected lung tissue, and then we do clinical study on humans. So you can see that full pipeline of going from sim to real, and also being able to validate this kind of aeration maps, being more accurate, very clearly interpretable compared to the earlier practice, which was clearly error-prone, subjective, and not really giving the right diagnostics. So as I mentioned, I've talked about neural operators as the one capable of capturing many of these multi-scale phenomena and being able to solve problems for the physical world. To very quickly remind you what that is, it's being able to model both the inputs and outputs as functions, and the operator is the mapping between function spaces. So that's why we call it neural operator. And so you can now discretize the inputs and outputs at any resolution, right? So you can query anywhere. You can have your training data or inputs be at any resolution. And the guarantee we have is a notion of consistency. So as you refine your mesh, so as you refine your input to a higher level of discretization, you get outputs that are consistent. Whereas this is not true if you took a standard convolutional neural net or a transformer, right? You don't have this nice consistency. As you add more and more details, it kind of converges to a consistent solution. But you need that for the physical world. Weather model, you have more satellites, you should have like solution that ultimately converges to the weather that kind of captures the continuous information around the planet. And so that kind of operator convergence is what we have with neural operators. Of course, we have extensive documentation and a library where I encourage you to go try out the code, contribute. It's all permissively licensed, so everybody is welcome to do that and already has extensive usage. So in the last few minutes, I know there was a question asked, whether we should just do coarse graining with AI. Let your numerical solver be. Can we just use AI to refine it? And there's the other option where you throw away your numerical solver and let AI solve everything. which one do you think requires less training data? So the option where I have like a numerical solver, I still keep it. I only train my closure model with AI or coarse graining with AI. Or I throw away my numerical solver and train end-to-end a model like a neural operator. Which one do you think requires less training data? How many of you think the closure model setup, keeping the coarse grid numerical solver, requires less training data? Okay, how many of you think the end-to-end learning requires less training data? Okay, yeah, it's pretty good mix. So of course, I kind of cheated because I didn't tell you what exactly is the kind of training data I'm going to give you. Right, so what is the kind of data this closure model would require? The closure model would require the fine grid solver data, right? In the case of fluid dynamics, it would be like this direct numerical solver, like a fully resolved simulation. So, and it would require lots of it because the coarse grid cannot help you with this. You need the fine grid data. Whereas with the neural operator, I can make use of both. I can make use of data from my coarse grid solver, and then I can fine tune it on the high resolution data for my fine grid solver. So I can mix data from my different solvers at different resolutions. And if you only count the very expensive fine grid solver, right, most of the training cost will be from generating data from the expensive fine grid solver, the answer is this end-to-end training with the neural operator does require less training data. And so that's the key, that if we are smart about how we use the training data effectively as a curriculum, you don't need a lot of data of the very expensive kind. So you can go very far with the coarse grid data, and especially with the neural operator learning how to mix across scales, it even learns what is missing in the coarse grid solver, right? What are the mistakes made in the coarse grid solver, and only learn the corrections to that implicitly within its layers. And we've shown also with our experiments that you require much less data and also be much, much better in your error. And so this was, for many people, not so intuitive that, because there's a lot of notion and a lot of already work using AI just to kind of augment existing solvers. And I believe that's not the right approach in the long run. You may get some quick gains, but in the long run, it's better to replace AI with all the existing solvers, because there'll be ultimately no real separation, right? Like they're all algorithmic ways to solve partial differential equations. And you could use some amount of learning, you can use some amount of domain knowledge and fixed ways to solve them. And I think we'll see that algorithmic integration and marriage of algorithms rather than putting AI in one bucket that is separate from numerical solvers. So that's where I think the future holds. So I will stop here. I wanted maybe a very quick, teaser on verification. I had lots of slides on this, but I won't get into them other than to say the other piece that I didn't tell you was on being able to verify aspects, right? In this case, verify math. And we had like Lean Dojo as the first open source framework that combined Lean and language models a few years ago, and now the rest is history. Thanks to Terry, Lean is really a first citizen in math and mathematical reasoning. So we really are pushing forth a lot on Lean. The framework that I want to advertise, and I'll leave you with this slide, is Torch Lean, which is the latest iteration of using Lean for verification. But in this case, it's for verifying neural networks themselves. So think about now, you've written a program for a neural net. How can I quickly prove properties about it? Was it trained correctly? Did it have the right level of quantization? What is the effect of quantization? What is the robustness guarantee that this possesses? And so, especially these properties are important. For instance, if I use AI to replace my numerical solver, right? I may need a lot of good guarantees that the solver had. And that's just one application, many others like that. So you can get certificates, you can get formal checks. So you can get all of this, and this is available now in the Lean Dojo website. So it's available. It's you can contribute to this. And the idea is you think of like Lean as not just one to verify, but also to execute. So you write the program in Lean where you define neural net layers. You can run it just as you do PyTorch. We called it Torch Lean. It's not invoking PyTorch, but it has a similar kind of language to kind of easily write neural network layers and execute. But in the background, the same intermediate representation can now be used for verification. So you get the full kind of like framework to do all the Lean kind of tasks on the same neural net. And so this combination is what I believe will really bridge what we've done with mathematical reasoning with Lean, as well as neural network analysis, using neural nets as tools for solving problems like partial differential equations. Thank you.
Wonderful. Thank you so much, Anima. You're incredible. Your work is very humbling. It's an honor to be in your presence. So actually, that's a great place to stop for now for 5 minutes, but please stay tuned for Alex Myberg, who will be discussing Scilab, which is something he contributed to, which is
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into Lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for maritime science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for maritime science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
On behalf of SEA, I'm very happy to announce our first SEA competition. So this is what we call a distillation challenge. Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works. You feed data, you build a model.
AI will become one of the collaborators. The more that AI develops, the more people are just naturally going to work together to create tools that will take advantage of the opportunities that AI offers.
AI may enable many more people to contribute meaningfully to mathematics and to scientific discovery.
AI can help you to get into lean, into math, explore a new area. If you don't understand anything about a specific subject in math, you can ask it, give me the pointers, where do I start?
Teaching people who are already experts in their field how to communicate and how to pull from other areas is going to create this rising tide effect that's going to lift all of the scientific disciplines.
No, I got it. That was helpful.
Okay.
Math is not just about problem solving. We don't just want the answers to problems, we want to also understand the process of arriving at these problems. And just because a fancy AI can give you the answer to a problem, often we want more. We want to learn how we can solve the problem ourselves. So to that end, our first challenge is a distillation.
AI is going to touch virtually every scientific field, and especially with the rise of agentic AI systems being used for science, I think that will be transformative.
How best to use the development of AI tools to help us do the best possible research we can do in chemistry or physics or geology or whatever the sciences are.
And math is now so central everywhere. So with all these new technologies, we can get AI to help us, we can get the public to help us, we can get other scientists and mathematicians to work together. I think it's a great future for math and science.
This has been a sea change in the way people do experiments. It's like a giant sandbox for scientists to play in.
AI is happening today, and it will be ever so more so tomorrow. So how do we feel about it?
I think very exciting times where one sees how the power of mathematics can be useful in other areas and how other areas like computation can be very useful in mathematics.
A conscious AI is inevitable. There will be a conscious AI.
So all of a sudden, what we now call machine learning really works.
This lean library and how formalization is a useful tool for, well, anyone, human or AI, but mostly an AI towards AI, grounding and checking proofs. So to step away from physics for a moment, if you look at AI for math and how it's evolved. Increasingly, when people look at how AI can help with math moving forward, we'll talk about it in the context of formalization. So ChatGPT, Claude, these different frontier models, FLMs, as sometimes people say, they're able to produce increasingly convincing, reasonable sounding proofs. They're reasonable over pretty long length scales. They can produce a 50-page document that seems to explain something. Sometimes, depending on how they were invoked or what the setup was, sometimes they're obviously nonsense. Sometimes they look pretty reasonable. When they're pretty much just nonsense, people call them slop. And sometimes that's something you can look at for 10 seconds and say this is nonsense and throw it away. But sometimes maybe it's mostly a pretty reasonable type of thing. And the core ideas sound sensible, and there's some maybe subtle error in there, but more akin to what maybe a sleepy but smart human could do with this kind of mistakes they might be making. If you are running these AIs in some sort of setup, some sort of orchestrating them, where they try and then spot errors and fix them, it's pretty cheap in some sense, cheap in terms of the human labor involved, to keep on just doing this loop over and over until you have a proof that is convincing enough to pass some other LLM judge. So you're naturally going to select for what are the results that sound plausible enough that fooled smart but kind of confusable LLM, some sort of judge. So like let's say that you tell the LLMs to keep working and writing until they have a proof of the Riemann hypothesis. Probably what you'll get with like 99% certainty is what is the best way it can write something that looks sensible up to there's some like subtle it invokes a theorem in the wrong way or smuggles a sign flip through or something. So I fear that there could be a bad future where every day there's 100 or 1,000 new papers put on archive or sent to every professor's inboxes or whatever by AIs, saying that they I meant to write smell test, not small test. They pass the smell test. They sound kind of reasonable on the face of it, but then pretty much all of them are wrong, and that's a lot of wasted time looking at it, and no one really trusts or believes anything published anymore. I think that there's a much better future we should aim for, where the answer is that all these proofs are formalized and then checked without human labor, and then we can spend most of our time actually reviewing just the ones that were correct and had something novel or interesting proved. So what is formalizing in this context? So we heard a little about lean in last talk. So the lean prover is this software where you can express any formal math. So like anything you could prove in a sense that a mathematician today would accept as proof generally, you can also express in lean in some reasonable form. Historically, it was entirely for humans writing interactive proofs, human types and parts of a proof. The computer says, okay, that worked. Here's what you have left to prove. Or it says, no, that step of the proof was invalid. You forgot this part, or that didn't apply here. And you keep on going back and forth until you have a complete proof. And you can then email this document, this code to someone else, and they can put it into their copy of Lean. And if Lean says, yes, this checks out, great, you've got a proof. And so the reason this is very appealing to AI people is because instead of having to trust a noisy and unreliable LLM to be the judge of correctness, you just trust Lean. And if Lean says it's good, then it's good. And Lean has been shown to be pretty scalable, pretty flexible. People have used it, like, these are some of the results that people have done. So like formal proof of the independence of the continuum hypothesis, that was like 6 years ago or so. That was done entirely by humans. This work about optimal sphere packing, that was a pretty big like joint AI and human effort. Those are both very impressive and pretty cutting edge research well, the latter was very cutting edge research to formalize. That was very nice. We haven't heard the same kind of success in physics yet, not really. There has not been talk of AIs formalizing grand cutting edge results in physics. And there are some pretty big reasons for that. So just to give a quick example of what Lean looks like to sort of give a flavor of what we're talking about. Here's an example theorem. This is a proof of the no cloning theorem in quantum mechanics. You don't have to know exactly what that means if you don't know about the no cloning theorem, but up here you have some sort of a mathematical claim. So I have a name of the theorem, and then everything here is some sorts of statements, assumptions of the problem. Assume, in this case, it's assume there's some states that I'm calling psi, phi, and f, and there's a matrix U, and some equations hold, and some inequality, then this other equation holds. You type that into Lean. Lean now registers, this is your claim, now your job is to prove it, and then everything else is me providing Lean with the proof that I have. Lean is not a tool on its own for discovering a proof. It's not a system for automatically trying to prove things, not in an AI sense at least. It's a system for accepting a proof that you already believe you know is to be true. That's a common confusion. They are separate, but very often Lean is paired with an AI that's trying to fill things in for you. So does Lean mean that the problem of AI slop is solved? I wish that was the case, but Lean does still mean that you need to ask the right questions. When you type in that first block yourself, you have to make sure that you're typing in the right thing. And if you're having an AI type that definition or that theorem in for you, the claim, you have to trust the AI is actually typing in the right thing. And that can be tricky. Sometimes it's clear, but sometimes it's not. So here's a little game you can try. This is a pretty elementary question about graph theory. Does there exist a graph with an odd number of vertices of odd degree? And I encourage you to just think for a moment if you have a belief what the answer is. So you count up all the odd degree vertices. Can you ever get an odd number? I'll just pause for like 10 seconds. Okay, well, Alice and Bob each were asked this question. Alice believes no, there's no such graph. She thinks for a moment, can't find a proof. She remembers something relevant to this in some graph theory course 10 years ago. She asks an AI, can you prove that there's no such graph? The AI says, of course I can. Here's a formally verified proof. And it gives her a big wall of Lean code that she can't read or doesn't want to bother reading. She's not going to sift through all of this. But it's great. Lean doesn't need you to read all the proof. All you have to read is the conclusion. And it's a bit dense notation, but it says there does not exist a graph G such that it is odd, the cardinality of the set of vertices that each have a neighbor set that is also odd. And that looks convincing. She believes that that's a good proof. But then Bob thinks there is such a graph, and he's pretty sure he can think of such a graph. So he says, hey, AI, prove to me that there is such a graph. Because he felt pretty convinced, but Alice has a formally verified proof. And the AI says, of course I can do that for you, Bob. Here's a formally verified proof. And again, it gives him a couple of pages of code, and he doesn't want to sift through it, but he ends up with a conclusion that looks pretty legitimate. And so what actually happened? Because if you compare Alice and Bob's outputs here, these are exact inverses, except for the fact that one has a not symbol in front, which seems like it should not be possible to happen. And this is real output from AIs. I did try this, telling AI prove this is true or prove this is not true, and it happily did both. And this tells you maybe something about the personalities that AIs adopt as well. Well, this is one of my favorite questions because it's really a personality test more than anything else. Computer scientists will often very quickly recognize that the answer is no, whereas like more often people who come from a pure math background will often think yes. So if you take the number line, this is exactly such a graph. You have an infinite number of vertices, each of degree 2, and 0 is the unique vertex of degree 1. So yes, there's an odd number of vertices of odd degree. But if you restrict yourself to finite graphs, then there's no such graph. This is called the handshaking lemma. So it turns out, okay, if your vertices are allowed to be infinite in number, it's false. Then it's true. There is such a graph. Otherwise, it's not possible. Okay, so that was a bit of a particular example. But so the point is, you told the AI to prove A, and you told to prove not A, and both times it happily agreed. And how did it smuggle this in? How did Lean accept this? Well, near the top of each of their files, in one, the AI understood that if you're saying construct such a graph, then you must want there to be an infinite vertex set. So it added the assumption that the vertex set is infinite. And the other case, the AI understood that you're asking to prove that there's no such graph. It added this hidden assumption that the vertex set is finite. In both cases, it might be pretty easy for someone reading the theorem to miss that this was extra assumption. Now, if you load this up in Lean in interactive form, Lean does try to provide you with what you need to catch this. In this case, if you loaded up the code in an editor and ask Lean to compile it, and then mouse over the name, it'll show you this hidden assumption. Fin type means assume the vertices are finite. And the other case, it would say assume the number of vertices is infinite. So Lean they've tried to make it a bit easier to tell when the statement is correct or not, or what you mean, what are the assumptions going in. But that's just, that's level 1 of all the different kinds of ways you could miss what the point is, or what the statement is really telling you. These theorem provers only guarantee correctness. And if you have a claim that an AI gives you, you have to audit that. You have to take that proof and check that it says what you think it does. And it's very easy to underestimate how difficult that is. It should just be reading it off, but it's a lot harder in practice. So AIs and Lean working together really struggle with any domain, any problems that don't have very good library support. Like there's no good definition of pseudo-Riemannian manifold in Lean, without which you can't really do any general relativity. If there's not good automation, like some really simple topological instructions like handles are not well supported, you want to have all the basic facts built in there. Or if people haven't agreed on a good definition. Like right now, the people who maintain MathLib have not agreed on how graph should be defined. And that's an ongoing blocker to basically all of graph theory. There's been no graph theory development in Lean for like well over a year now because everyone agrees that graphs need to be redefined and no one can agree on how. So that was difficulties of AI for math. So what does this mean about AI for physics using Lean? Well, I've been working on parts of it. So we had this result. We formalized a proof of this theorem called the generalized quantum Stein's lemma. This was a theorem from 2010. It was very impactful, used lots and lots of times. They found a subtle mistake in the proof. And then twice someone published a fixed proof that also turned out to be wrong. That was a series of embarrassments. People were kind of nervous because so many other results relied on this. Finally, in 2024, there were 2 independent correct proofs published. About 8 months later, we had formalized the core arguments of that proof, but there were still some other mathematical dependencies. And now as of like start of 2026, we have this completely done. So we have checked this theorem. It involved many different fields of different parts of operator analysis. But it's a physics theorem, but relied on lots of other math. This is something we were able to do because it's a very precise mathematical statement. That's a well-posed problem. Where it really is hard to do these things in Lean is where you have lots of unspoken assumptions, things that physicists would not bother writing down, or side conditions. So is another word for this kind of thing. This is one thing where physics is really different from math. In math, these are much more often very explicit. In physics, we very often say, oh, I know what I mean, or that's an obvious fact, or that should be true. And I think of myself as a more mathematically inclined physicist. I thought I was decently aware of these side conditions until I started trying to formalize any physics in Lean, and I realized how much was missing. I think one case where this becomes apparent is every so often someone says there should be a formalization of Maxwell's equations in Lean. It's not mathematically super deep, but then you run into the difficulty. Okay, so this is one set of equations you could call Maxwell's equations. But then other people say, well, I want in curved space-time. I want to do Maxwell's equations in general relativity. And then people debate, do you want to support point charges or linear densities or surface densities? Do you include matter interactions of different sorts? Depending on who you're talking to, matter interactions are the only reason it's interesting. Or if you're talking to electrical engineers, perfect conductors, which again are sort of a singular case, or maybe the only case that's interesting. Maybe nonlinear media are very important. And once you start including a definition of Maxwell's equations in Lean that is sufficiently general to include all the different things people want to do with Maxwell's equations, it becomes an unusable mess, and no one's ever going to use that theorem. So it's very hard to write down a sufficiently general version. Each branch of physics has its own difficulties that make it hard to translate what physicists write on paper to what you actually want an AI to solve, the actual physics problems you care about. These mostly feel like sort of annoying details depending on what you want to do, but they're all the details that you do have to actually grapple with. And they're pretty much all details that have been dealt with somewhere in the literature on mathematical physics. Someone has made these precise, but there's a difference between one person in a paper made very precise what we mean by this, as compared to this textbook of standard material doesn't address the problem once. And now everything in that textbook that you want to do in physics, you have to carefully think about making precise and correct. And some of it will end up being very difficult. As maybe one example of a very intuitively obvious physics phenomenon, there's an angle of repose. If you are dropping grains into a pile, depending on the shape and size of the grains, they will have some characteristic angle that they form, an angle of repose. This has lots of applications in the real world. It's how corn stacks up when you're dumping corn into a pile, and you want to know how much volume you can pack in a given base radius. But even to start talking about something like that, you need to prove that under some appropriate random process of dropping these at some rate that they are allowed to settle, under some model of elastic and inelastic behavior, that this asymptotic angle actually exists. That's a huge mathematical hurdle that you have to overcome before you can start doing anything actually related to this very simple physics process. Whereas a physicist would often just say, yes, of course they settle like this. All these additional side conditions make auditing a theorem very hard. If you want to have a hypothesis that says, oh, this is well behaved, in the sense that it will always do this and this, if any of those assumptions of well-behavedness are subtly incorrect, the LLMs will really exploit it. On the other hand, if you are missing those, then there'll be no possible route towards proving it, and the AI will just get stuck. This is an example from a recent work that was trying to have an AI formalize a bunch of work about quantum error correction. And they asked me to take a look at their main results to see if it looked reasonable. And each of these lines here is some word I've never seen in Lean before. So it starts by saying there's some variable DC, which is detector collection. And there's some variable called base outcomes, which is an outcome assignment. And some variable called logical effect, which is a space-time fault. As a physicist, I have a guess of what each of those means. But if I want to understand what the Lean is doing, what they're actually proving, I have to go and look at each of those definitions elsewhere in the Lean. And many of those ended up then being a good 30 lines themselves and depending on many other definitions. That makes it very, very hard to assess, is this actually proving what you want to think of it as a physicist? This is a poorly written theorem in that sense. So how do we avoid that? I think that we need to start standardizing physics in some sense akin to MATLib. MATLib has done a really good job of finding definitions that everyone can agree to work with. If you take 4 different mathematicians and ask them to define a derivative, you'll probably get 4 meaningfully different definitions. And that MATLAB faced that problem, and they had a bunch of people argue about it until they found a definition of derivative that worked for all of them, that was sufficiently general. They've changed a couple times, making it more general. I think the definition of derivative in there now is probably not one you would find in any existing mathematical work, because no one ever needs to work in that level of generality for that one job. I think we need to do something like that with physics. There's additional problems, like there are whole subfields of physics that exist only within the scope of one approximation. When people study classical physics or classical gravity, that exists within a certain approximation to general relativity. People might mean slightly different things by that. Lots of condensed matter physics is done entirely assuming that nuclei never move in a material. So if you then want to prove something in that field and apply it anywhere else, you have to somehow make rigorous what that approximation is doing for you. I like this quote from Oliver Nash. He's a core MATLAB contributor. He said that MATLAB has more to learn from Bourbaki than Linux. Bourbaki was this collective of mathematicians that wrote books mostly on analysis and topology together. And a big aspect of why the books they wrote were such very high quality was they were mathematicians that came from slightly different areas, and anything they wrote, they all had to agree upon. And this led to a really nice general framework. Many things, they ended up picking things that were not just one person's preference, but had to satisfy everyone's sense of aesthetics somehow. And that's sort of the model MATLAB has adopted. A lot of people point out that Lean is like Linux or other large open source projects, in the sense that you have many people modifying code in parallel, you have to have maintainability, and that is also a good concern. Picking the right definitions by community consensus is a very powerful method to finding definitions that everyone can end up using in the future too. So there is this project PhysLib, which is we're trying to grow. We are trying to find ways to get more physics formalized in a way that everyone's happy with. It's hard. Lots of people do still end up making their own physics with their own little definitions, and it hurts me a little bit every time. I'm happy to see more people doing physics in Lean, but I want us to work together. I think that in general, when I talk to people interested in AI and Lean, I want to increase awareness that definitions are often at least as hard or even harder than filling in the proofs. We need to get different people talking together about the right definitions in physics. If you want to talk about what is a charge or what is a photon, you'll get very different models, like mathematical models of that concept from different people. And maybe you need 3 different things that you call a photon, or maybe you can find one, but you need to figure that out. And if you're going to do 3 different things called a photon, you need some theorems that relate them to each other so that you don't just have 3 entirely disconnected concepts. One way that we're trying to get people to build one cohesive library, we're working to try to prove this one result called MIP star equals RE. This is a you laugh. Yeah, it was something that for a number of years was talked about as not going to happen, but we think it's a useful moonshot target. I think that if you get people to try to prove this theorem, it will require building out sufficiently much different quantum information in particular that you must end up with some pretty useful library. And hopefully it's the kind of thing that then other people want to build on top of. In the same way that you could say that like people proving Fermat's last theorem in Lean, you've built a sufficiently large group of number theory that now other people want to reuse and reuse as much of that as possible instead of everyone re-rolling their own definition of number field or something. So I think that these moonshot targets are a good way to encourage library building, which in turn contributes to community building. And I hope that will let us build a good library of definitions that one day when AI is doing physics and proving stuff for us, we can just read the theorems and not 20 pages of definitions. Thank you.
very much. Appreciate that. Lovely talk. Next up is the member of technical staff at Logical Intelligence and associate professor at UCR. His talk is on how neural networks spontaneously organize their internal geometry during training. Fascinating stuff. Please welcome Michael Mulligan.
Okay, hi everyone. It's great to be here, and I want to thank Sarah and UCR for having me. So I'm going to tell you about some work I did with Matthew Van Herweg, Mike Friedman, and Keith Adams. And good. And so the basic idea is that we're going to be inspired by an old theorem due to Kolmogorov and Arnold about representation of functions in neural networks. And I'm going to present some evidence that standard training of ordinary neural networks realize structures present in this theorem to some extent. So I'll provide some evidence in a variety of different sorts of models. And these structures, where they appear, are in what's called the Jacobian, different sublayer maps. So what this has to do with, it has to do with how the model responds to small variations in the data. So it's a sort of response function. And at the very least, whether or not it, to what extent it realizes this K construction, at the very least, it motivates new observables in which to probe and interrogate our models and hopefully learn something about them. I'll leave open, work where, how we can use these observations to improve, make training more efficient. Okay, so, the basic context is, the universal approximation theorem. So performance improves at scale. So in theory, any function can be approximated to any arbitrary degree as long as you have enough hidden neurons. And, a famous recent example, empirical example of this is our scaling laws, where if you add enough compute and enough resources, the performance of your model predictably improves. Now, a similar result, actually 70 years ago, predates the universal approximation theorem, is a result due to Kolmogorov and Arnold. It's called their representation theorem, and it tells you a similar sort of thing, where given a target function, you can represent it with a one hidden layer neural network. Now, in contrast to the approximation theorem, this is an exact result. And it's exact with a finite number or fixed width of the network. And this construction has two pieces. So it's a little bit detailed, but it's a composition of two maps. There's a first map, which is the inner map. And this is a sort of universal data preparer map. So it sort of organizes your data, comes in, and it organizes in such a way that the second layer can make use of that data. Okay. And I'll be just focused on this first layer map. So this first layer map has a sort of a distinctive feature, a distinctive geometry. I'll refer to as KG or Kolmogorov-Arnold geometry. And it all has to do with how this map, capital Phi, responds to small variations in the data. So that's what this Jacobian is a measure of. And within the construction, the Jacobian, how the model responds, takes a special form. So this special form of the Jacobian says, okay, has 3 0 rows, absolutely 0. That tells you that the model is insensitive to any variations in the data along those directions, those hidden neurons. And then in the remaining directions, it maps in a sort of canonically aligned way. So it preserves directions as the data flows through. So input neuron to hidden neuron preserves that. Now, what the values of the A and B constants are and which rows are 0 can vary from point to point in the source manifold. But generically, the model will respond in this simple way. So you naturally ask, is this relevant? Is this directly relevant to machine learning? That's what we want to ask. Well, here's the answer. So that was easy, right? So, early on, actually the time 1989, it was thought that, this old result has no relevance. And there's sort of 2 reasons why. So the first has to do sort of standard argument that although, a representation exists, it doesn't mean you can find it. Okay, that's a standard sort of thing. A stronger statement is that this universal data preparation map is nowhere smooth, or sorry, it's not nowhere smooth, but it cannot be made completely smooth. So that means there'll be derivatives which blow up, okay? Which is sort of at odds with gradient descent training. Now we're going to follow some more recent work and be a little bit more optimistic. So recent work has taken inspiration from this theorem and built architectures very much mirrored on the Ka construction into neural networks. We're not going to do that, but we're going to still be optimistic and ask, to what extent do standard models, so standard multi-layer perceptron feed-forward models, all the way to transformers, exhibit characteristics of the Ka construction? That is, their sublayer maps have that very special Jacobian form or response to variation. And I'll try to present some evidence that there's actually some hints of that. So there are, to some degree, there's some lineup between these 2. So there's sort of 2 metrics that I'm going to be thinking about throughout the talk. So the first, there are sort of 2 aspects of the Ka construction. There was these 0 rows. That's what 0 row fraction corresponds to, just counting at a given data point, how many 0 rows does that Jacobian have? This is something you can just measure in your model. And the other thing has to do with what I'll call canonical alignment. That's just, sort of like a let's do this top part of this matrix, mapping input neuron to output neuron within a given layer. So here's some data. So let me start with just doing some simple toy tasks. So in synthetic, just curve regression, okay, of some nonlinear function. This is a particle in a box. And then the other task will just be MNIST. And all we do here is for a set of data points, we modeled the thing with some one hidden layer neural network and measure the Jacobian in that first layer map. Given a set of data points and a Jacobian, you can measure the sizes of rows and just order them on increasing size and put in a sort of standard zip plot. What I have here is 2 curves down the left panel. The first grayish one is the behavior of the model at initialization. So it's a very smooth set of row sizes. The darker blue one is the trained model. And what you see is it sort of dives down to 0. And that diving is what I want to associate with sort of 0 row fraction. So what a 0 row means in this case is, these are all numerical experiments. So you take the first percentile of the initial model's rows, you just define that to be 0. And so 0 row just measures how many in the trained have rows less than this first percentile. Now, so there's some number that you can work out. That number happens to be around 9 and 13% in these models. Okay, so there's some hints at this, this emergence, at least at the end of training. How does it emerge through training? Well, it emerges rather smoothly through training. And the point is not so much the magnitude of these metrics, going from 0 to 10%, roughly 10%, but that it's non-zero at all. So there's a smooth, or rather smooth increase from initialization to the final trained model. So these curves are supposed to tell you that there's this coexistence of both 0 rows and canonical alignment that training produces. Now it's not, is not as much as the actual KA theorem. It's like a factor of 10 off, but it's not noise, and it's statistically significant. Now, these are two examples where it works, right? So we should see example, non-examples where it doesn't work. So let's just focus on some synthetic tasks, just pure curve fitting. Okay. And what I was looking at is this particle in a box, which I'll call an XOR. Here, I'll take a linear function and a random function. So this is a function. So random just means that the output is drawn from some distribution, and so you can memorize, but you can't generalize. And in this case, the linear doesn't need any Ka geometry, and there's trace amounts, if you will, in the random. But it seems like there's a non-zero amount. Okay, so there's 15%, and there's some degree of canonical alignment. So you might ask, what's going on? The accuracy or the performance of the model, as measured by this R-squared thing, is pretty low, 16%. It hasn't memorized, but nevertheless, there's some geometry. If this geometry is useful, well, it's not being used very well. So what we found is that you can train that first layer, okay, which exhibits these sorts of numbers when we apply our metrics, freeze those weights, and add on a second nonlinear layer. So the point is that just a single layer training, it's too weak of a model. It doesn't have the capacity. However, the initial preparation for that initial stage of training is useful for a second nonlinear layer to take advantage of. Now, if this KAG develops during training and seems to be useful, maybe we can sort of force it. Maybe we can steer the model through an augmented loss. So what we did is we considered a model, and we added that sort of encouraged KAG, and we trained not this XOR function, particle in a box, but a sort of entangled wave function. So a fermionic wave fermions in a box. In this case, we have a tuning parameter called lambda. It either encourages or discourages this canonical alignment, this KAG behavior. And what you find, this dark blue curve is the performance, how well it's doing. At lambda, this is misaligned, but it's peaked at lambda equal to 0 and degrades whether you encourage or discourage the performance. So somehow the model is doing its best when you don't encourage that, try to steer the KAG into the model. Now, I've shown you some very sort of toy models, right? Simple regression, MNIST, trivial tasks. We looked at more respectable models. So this means pre-trained models with around, 80 million parameters, standard vision transformers, the sort of architectures which underlie our good friend chatbots. And we measured the same sort of metrics. And the point to take away here is that these models are much more nonlinear. They have many more layers to them, in this case 12. And at each of those layers, we measure the degree to which from one layer to another, it exhibits this zero row or canonical alignment. And what you see is the metrics, they're elevated at early layers, and then they sort of decrease. And so there seems to be sort of this naturally, even in these larger models, this initial data preparation stage emerging. So I'll leave this with sort of a future direction. So we don't really know how to steer the model. We tried to steer it with a simple addition to the loss. Didn't seem to work. One idea we have, although we don't know how to implement it, is to think, well, if KG develops through training, perhaps we can sort of change the initialization of the model weights, sort of give it a heads up, a step up through training. Now, this is sort of a non-trivial task. Typically, you initialize weights in some independent way. This would be what we'd be asking for, is a sort of correlated initialization of the model weights. So it'd be interesting to try that, see if it might work out. All right, so let me just leave with two messages. Gradient descent, try to present evidence that gradient descent finds approximate canonical alignment, or KAG. Now the question is, how can we capitalize on this? Thanks.
Thank you very much. Fascinating. Okay, next up, we have a recorded keynote from Andrea Bertozzi. So, no. Or we skip. Last minute changes. Next up, we have Sergey Kukov, director of the Merkin Center and executive director of the American Institute of Mathematics, and John D. MacArthur professor at Caltech. Please join me in welcoming him.
I guess now it's better, yeah. So in case of fusion reactors, it's a very sparse reward problem because we don't have a fusion reactor, or the one which is working and that we like. So it's a design that we're trying to invent. Same with airplanes. So the person who's presenting described that AI is used to design airplane, and then of course we can also deploy AI to fly airplane. But it's another task where there's so many mission critical parts that all have to work together perfectly so you can board airplane and be sure that you land safely and nothing bad happens. So this again illustrates sparse reward and long horizon simultaneously because there are many steps, and sparse reward in the sense that, yes, when we design airplanes, we try to test them, but how many Boeings can you design implementing what AI proposes, right? So maybe 300, maybe 3,000, but it's not going to be the size of the data set that we like to have for typical data science tasks. So these challenges, sparse reward and long horizon, occur in many domains. So I mentioned a couple. These are some others that we'll touch in the talk. For example, coding, then robotics, autonomous transportation. I'll talk a little bit about games. Actually, that's a very useful lesson as well. And algorithm discovery. In many of these tasks, the question is no longer anymore whether AI can find the solution, because the answer is very simple. It can't. So, or at least, again, if you're exploring something which is sparse reward. But the question becomes, how can you really steer the process in the right direction? So for instance, if you're designing a fusion reactor or one of these other examples that we're going to be talking about, how do you reward it and how does it go in the right place? So with coding agents, there has been a lot of success, and for reasons that probably many of you experienced yourself if you're trying to code or vibe code. So they're getting better and better. But there are still big challenges, in fact, associated with long horizon tasks. For instance, some of the coding challenges are where you have to find a bug in a big repo which contains a bunch of files. So agent has to search through a bunch of files, find the exact place where it fails, and the signal, the reward is yes or no, the bug is fixed or it's not fixed. And it's only a function of this many steps done right. So a couple of things that really helped in the past or recent past is some form of memory and also skills that allow you to absorb certain behavior or the right scenarios and package them in routines that can be deployed kind of as individual steps. And it's a pleasure to be also in the same college as one of our previous speakers, Anima, who contributed to this through for example, deployment of systems, which then led to world models and other tools that combine this exploration tasks and steps in something like skills. But this approach, even though, again, it works to some extent, there are still challenges. Some of these coding challenges and benchmarks are only saturated, I don't know, 25% or so. There are still quite a few things associated to this sparse reward and long horizon tasks. And things get even trickier in physical AI domain. So when we talk about, say, robotics, this has already come up in several of the previous talks. So you want to get signal back and fast. And fast and how much signal you get is already a challenge. Second, in the real world, everything is kind of fuzzy. So sometimes even the way you collect the measurement is a little bit ambiguous. For this reason, we don't even have good robots who can cook you a dinner tonight. So the hand may be a little bit misaligned or shaking, and all of these small, tiny errors, they quickly accumulate. And in the physical world, it just gets worse and worse. So it gets combined with other aspects of technology which has to be super precise for it to work. And yeah, that's pretty challenging. I do hope, I'm very excited about this AI labs. So once we are able to close this loop of robotics plus providing really good feedback into AI and automating and making it fast, then hopefully we'll be doing real scientific experiments with almost no human in the loop. But again, we are really far from that date. So sparse reward long horizons are really critical to this. And again, there are many other domains such as autonomous transportation and other things that I'm not gonna talk in detail. So why am I telling all this? About 7 years ago, I switched my research from what at that time was quantum topology, this is some esoteric area of mathematics, into AI research. And since then, I was very privileged to be part of several projects, some including AI companies. So this is my joint paper with Alex, and yeah, on a model that's called Aristotle. Another one more recently is with GDM called Alethea. For some reason, all the startups or companies, they like to have models whose name starts with A. I'll let you guess why that is. And at Caltech, where I am, I run this Math AI lab, which is focused on mathematical reasoning. And if you read the description, it is exactly, so the last sentence gives it away. It's basically we are super focused on sparse reward long horizon tasks. So we're trying to design new algorithms, new architectures to unlock some of these challenges. So we don't care about anything else. We just care about long horizon sparse rewards. That's it. And this is important for mathematics, and goal of the talk is to sort of explain why and how. So another thing I want to point out is that when the lab was created, we had this sort of motto that math plus AI equals AGI. So this was 5 years ago. So now I probably should have had it as math plus AI equals ASI, artificial superintelligence. Why? Because again, achieving this exploration and out of distribution generalization is exactly what artificial general or maybe superintelligence needs to reason outside of the box. So speaking of mathematics, it's important to clarify from the start, there are of course different types of mathematics and different kind of levels of difficulty and hierarchy. Going from various stages in school to math competitions, then undergraduate, graduate level math, and so on and so forth. And general purpose LLM-based tools, they actually move really well through this hierarchy. Roughly every year or two, you get from one stage to the next, so the bar moves well. Question is it going to continue and how far? So I don't know. That's my honest answer. But it's actually curious to see what the future holds. And one could speculate both ways. So for instance, where I put the green line is actually where I would like the progress to be. This is kind of the hardest level of mathematics, which contains all the hardest challenges that many professional mathematicians cannot solve, no matter how hard we try. So it usually takes many years and bright minds to get to these problems. So I personally would like to see AI to get there, but one of these challenges that we don't have much training data for those kinds of problems. For example, for Riemann hypothesis, we have lots of papers that Alex mentioned that look convincing and unfortunately riddled with mistakes or errors of various kinds, but we don't have a single correct solution, unfortunately. And so there is nothing to train on. And this problem is exactly the same as designing fusion reactor. We just don't have a single data point. So it has to figure it out on its own. So in other words, I am convinced that AI can help me as a professional mathematician, scientist to improve my research by say 10x, 100x, 1000x. The question I want to ask is, can it actually outperform me completely, be way better than me? So, and that's what we're doing. We're designing those kinds of algorithms and architectures. So it's kind of interesting that I'm trying to replace myself as a human mathematician. And natural question is, why am I doing this? I get this asked sometimes. Honest answer, I don't know. It's interesting, a kind of mischievous way. More serious answer maybe is similar to what Steve Jobs said when they were designing a graphic user interface, and somebody asked him, Steve, if you undertake this task, it's gonna blow up the company. And his answer was, it's better we do than somebody else to us. So I feel that maybe by working on this, we get better understanding of actually how the systems work, how to safeguard them, and many other important questions. All right, so why is this sparse reward long horizon relevant to mathematics or hardest challenges in mathematics? So this is one problem about coloring of graphs that goes by the name of understanding and computing Ramsey numbers. And here, the combinatorial explosion of the problem, which is fairly easy to say, it can be phrased as a two-player game with two players coloring graph in red and blue. And there are certain conditions that they want to meet in order to win. And very quickly, as the size of graph grows, just not too much. I mean, this would be graphs on some reasonable number of vertices that you can draw on a plane, such as 5 or 18 and so on. Complexity of the problem explodes combinatorially so fast that in order to answer the next interesting question, you have to search a space which is of the size of 10 to the 26. And again, this is where interesting mathematics leads. So how can you teach AI system based on just a couple of examples in this, say on a diagonal of this graph of or table of the Ramsey numbers to learn and extrapolate so far so that it starts making predictable, reasonable conclusions about such astronomical sizes. So this is an unsolved problem and remain unsolved for many years. Erdős, who actually thought about this problem, said that if aliens come to Earth and give us ultimatum that either we have to provide next Ramsey number or they wipe us out. So if they ask about R55, that's the number which is currently in yellow, where we don't know the exact number, we know some bounds. Then we should gather everybody on Earth and work on this. But if they come and ask about R66, which is the next number, we should just surrender. So again, this is just illustration of astronomical complexity that happens here. So this is actually the problem that I do know how to solve. And another hard, interesting math problem that came sort of from same area as the previous one or close cousin. So in combinatorics, there is this Hirsch conjecture, which was a big deal about a decade ago. It was solved by Santos, but then David Eisenbach, a colleague of mine, who used to be director at MSRI, now SL Math, visited us and we started talking, and he suggested that there is analog of this problem in commutative algebra, which is his area of mathematics, which is kind of similar to Hirsch conjecture. He called it algebraic version of the Hirsch conjecture. And here one wants to find instances in commutative algebra which satisfy two conditions. So technical names of these conditions is one should be monomial ideal of large diameter. This is property very similar to original Hirsch conjecture. And then the second condition is that it should be linear. So it doesn't matter what the conditions are or technical meaning. Each one individually is fairly easy to satisfy. So there are lots of instances of these so-called monomial ideals, which are either linear or of large diameter. But once you ask about both, it again becomes needle in a haystack type search, as with Ramsey numbers that I mentioned before. So unlike the previous one, so this we actually did manage to solve. It was a very non-trivial endeavor and finally published in ICML. So the reason we publish in computer science journals, even though eventually the result is a theorem and it's an exciting mathematical result, is that with AI, it requires developing a lot of new AI to actually solve it. And I'll give you a hint or a glimpse of how this process of developing AI to unlock this happens. In practice, it's usually months, if not years of work on AI algorithms. And that's what I'll try to explain. So some of the key features of AI algorithms involve this feedback loop from which agent learns, and reinforcement learning is really a good model for how these algorithms are developed and how they work. But also reinforcement learning actually is usually a key part, whether you talk about LLM post-training, for example, and alignment, or so LLM-based models, they give their robustness from reinforcement learning. Or if you formulate your task as a game, as I mentioned, some of the mathematical problems have this feature already built in. Still, reinforcement learning is really good way to think about or how to approach the problem. So agent interacts with environment, collects rewards, and improves the behavior. So that's how many of the things are actually done. So therefore, a natural question you can ask, okay, what about reinforcement learning? How does it perform on such tasks, and what algorithms can you choose, and so on? In the next 10 minutes, I'll try to give you a hint or glimpse of how that works. Once we teach reinforcement learning courses in CS, we usually start with this algorithm called DQN. It stands for Deep Q Network. It's a deep network version of basic classic Q-learning algorithm. And this is actually an interesting story in its own right. So it came from DeepMind in 2013. So by AI standards, this is ancient time. And indeed, this is like the basic algorithm you can choose. There are quite a few. And what they were doing at the time, this is nicely described in the movie about DeepMind and Demis Hassabis. They were trying to learn how to play Atari game from pixels, just from pixelated screens. And it's in the movie, it described quite nicely. It's an interesting journey. Nothing worked. They tried for many months. And then finally, they came up with this algorithm, which now is, again, basic, very, very basic version of RL. And it played quite well. But the story is actually interesting. So it played well on most of the games, but there are some where it miserably failed. And this is a distribution, so there are, those of you who see it close enough can probably read that there are many names of Atari games here, and the bar indicates how well this particular algorithm that developed performed. And one game here sits right at the bottom. To me, personally, it's not a special game at all. I never played Atari games that much, and it's called Montezuma's Revenge, okay? And it got exactly 0 score. So it means that the agent, this algorithm, DQN, which actually performed pretty well on everything else, didn't manage to succeed at all on this game. So it never got a single point. So it was pretty miserable. And then in the reinforcement learning community, this became an obsession. Okay, so the question became how we develop AI algorithm that actually can produce some progress on this game, okay? So I mentioned that games actually are good examples of this long horizon task. So this became a whole era of exploration, which spanned the whole decade, almost 10 years. And again, by AI standards, this is a lot. I mean, this is a huge period of time. And many teams have tried and failed. So many teams try to design AI algorithms that would actually produce something meaningful on this game, which is a simple, by now, it's a simple example of exploration game. And here you can see that each dot represents a team. It represents an attempt, in fact, successful attempt. You can imagine how many unsuccessful attempts that people didn't want to publish are there. Some of them involve DQN that we already saw before with various adjectives. So people tried versions of this. And actually, this was an interesting point. So for example, C51, still on the bottom that got almost no score, is a very interesting new algorithm that produced what's called distributional reinforcement learning. This is where instead of a mean signal, you actually collect the whole distribution. And in many tasks it works, but again, here it wasn't very successful, even though these days it has many other applications. So there are many other things. For instance, Rainbow was a version of C51 with lots of other things packaged inside. So people tried. You can see it stands just a little bit above C51 point on performance. Impala is a very cool thing. It's a distributed actor-critic model. So by that time, we're already talking about something 2018. A2C, A3C were popular algorithms in reinforcement learning, and Impala is a version of that on steroids. And finally, you see that there is one point which actually sits above human average level, and that's random network distillation. So that finally got above human in this Montezuma's Revenge, which is a pretty simple game. You have to go around the room, collect the key, climb some ladder, and exit the room. So not such a big deal, but again, for AI, this was interesting story. And finally, a little bit later, a year or so later, there was this interesting algorithm, Go Explore, which finally managed to overcome not just average human level of performance, but expert human level of performance on this game, Montezuma's Revenge. So what this illustrates is that people tried, and this was hard, as the name suggests. This Go Explorer is based on exploration. And it's not just a naive exploration where you try to reward curiosity or something that hasn't been seen before. Because if your search space is huge, everything has never been seen before, right? So the question is, how do you actually collect these rewards? And right, so, and then these guys understood, so this Go Explorer is not just a result of a lot of experimentation. They had to analyze what failed in every previous attempt, and they identified two critical features, detachment and derailment of many of the previous systems. This is where AI tries to explore potential candidates and goes for a very long path in trying to figure out if this is promising branch of the search tree. But in many cases, it actually forgets that it needs to go back and restart. And these are some of the problems that occurred in the previous models. And the authors of this Go Explorer, they realized that this is something they need to fix. To me, this also is a good illustration of actually how it works with such hard problems. So I mentioned to you a problem on commutative algebra that we managed to solve, brought to us by David Eisenbud. And the search was exactly the same. So we had to try 50, if not 100 of different algorithms and architectures, never mind hyperparameter sweeps, before something actually works. So, and this illustrates kind of work of our lab, which I don't think is very different from any AI research lab, where you go through the cycle of developing AI, then deploying it, testing it. Important step is analyzing what works, and in our case, what doesn't, because most of the things, they don't work. So my job as a head of the lab is actually to encourage everybody in the lab that, yes, we should try again, that failure is a default, what we expect, nothing works. And our job is to repeat it 50 times and 100 times sometimes before we find something that actually works. So this is our research cycle. And as I say, we're hoping to discover ASI. And this is illustration, in fact, not specific to us in some sense, because AI that's trying to do algorithm discovery faces exactly the same issue. So in chip design, in various other applications, I mentioned autonomous transportation, for example. In our case, it's mathematical discovery. You're trying to find algorithm that achieves a certain task. So this is good because now in this algorithm design, the signal is pretty robust. The feedback loop is reasonably good. But the problem very often is associated with how good your evaluator is and evaluating whether you're moving in the right direction or not. That's often a challenge. And there are various systems which successfully deployed it. For example, Alpha Evolve is good example. Then Alpha Tensor is another example, and so on. But the same sort of problem of sparse reward now appears, at least for us, not only in a particular task that we're trying to solve, but also in a search for the approach to how we're going to solve this problem. So it's also a sparse reward problem that we have to try so many different things before we finally see a signal that, oh, this algorithm actually is doing something useful to us. So there are two levels of sparseness. again, one on a concrete task that we're trying to achieve, and the second is on searching for the approach to that. So approach is itself is a sparse reward problem, and that's exactly how it appears in algorithm discovery more generally. So the last problem I'll mention, it's another big famous math problem called Andrews-Curtis conjecture, on which we recently managed to make progress precisely through this process of trial and error and experimentation. And by the way, I should say that I hope in the future, I don't even need to be in the loop, that the cycle of analyzing what fails and how to improve it could be really done fully autonomously. But again, now it's still a sparse reward problem that AI cannot fully do it itself. In this particular case, so this Andrews-Curtis conjecture is asking, that's now from group theory, that's another area of mathematics, and it's asking if every so-called balanced presentation of a trivial group, like an example written on the top of the slide, can be connected to the most boring, naive presentation of a trivial group via certain moves. So it's the set of moves is very small, and it's a search problem on abstract graph, and the mathematical question is asking if this graph is connected. So in other words, if you can reach from every point any other point on the graph. So it's not known, it's not solved, and it took us almost 2 years to actually understand through, again, this experimentation, what's wrong, why is this problem so challenging, in particular for AI. And as it often happens, one of the most important things for AI is, of course, data. So there are all these beautiful, sometimes cartoons that garbage in, garbage out, so, or your model is as good as the data. Here, the data is synthetic. So in at least in many of these mathematical questions, we're talking about some abstract math. So we can easily generate data through synthetic process. But the issue here, which we actually didn't recognize, and mathematically it was not known, so part of the progress here is exactly the structure of the data, that many examples that you can generate synthetically, they belong to this easy pile, from which you don't actually learn anything interesting, whereas mathematically challenging counterexamples that you'd like to resolve, they belong to a completely different pile, and there is nothing in between. So once you see this picture in your head, you immediately know what to do, how to correct it. Namely, you have to feel this missing middle, and then you make progress. So eventually, again, in this paper, we also end with some theorems, which are pretty cool mathematically, but the way it comes out is by understanding what your problem is. So I mentioned that this problem is from group theory, and group theory is about symmetries in mathematics. And you can compare pretty much every problem in group theory to some version of Rubik's Cube, which is about symmetries and non-commutative structures. So in particular, this conjecture is sort of fancy version of Rubik's Cube, which is also an interesting game for AI, except that in Rubik's Cube, every step, every configuration of Rubik's Cube can be connected to the goal state, which is perfectly colored sides, in less than 20 steps. In this Andrews-Curtis conjecture, it's a version of Rubik's Cube where this path can be exponentially or super exponentially long. In fact, the conjecture itself is asking whether this is possible, whether every configuration can become connected to the goal state. Also, in Rubik's Cube, it's easy to start training by essentially scrambling, and that's good enough. But for me, this is only analog of the easy pile of data. So as I showed on the previous slide, we have this bimodal distribution, unfortunately, and just random scrambling is not producing good sorting states for this problem. And finally, Rubik's Cube is a search problem on a finite graph of possible states, whereas in this context, it's a search on infinite and not explicitly presented graph. So the point I'm trying to make in this talk, so to again summarize, is that with this sparse reward and long horizon games, these are much harder than usual games, even like chess and Go, because typical game of chess and Go, I mean, game of chess, for example, would be 30, 40 moves. Games of Go could be a couple of thousand, but still these are very short and easy games compared to problems like this, where you have to make millions and billions of steps, and you go into millions of steps and you have no idea if you're on the right path or wrong path. So these are much, much harder tasks. Also, we immediately encounter this exploration problem or out of distribution generalization, where we somehow from very small signal have to learn what's useful and what's interesting to go not just 10 or 30% outside of the span of the training data, but actually many, many megaparsecs away from the training data. Again, current models, they don't do this well, whether you talk about LLM-based models or even reinforcement learning. These are exactly the challenges that block us in many of these domains. And I personally believe these are the problems that block us in true reasoning of AI models. I already mentioned another phase of this problem where such sparse reward or small signal type feedback is essentially a search for a needle in a haystack. And usually it occurs when your distribution of data is very uneven in the sense that generic case and extreme case are widely separated. So that's another thing that in a game of chess, the difference between average game and the longest possible game is only 1 order of magnitude. But in these problems, extreme case could be many, many orders of magnitude different in complexity or difficulty or reward separated from generic case. And therefore, training on generic cases doesn't really teach you anything interesting about such cases of interest. So the problem I described, so this is my last slide, is not really special to math. So yes, it does occur in research level math very often. But what I'm really asking is how to teach AI to find needles in haystacks or unicorns or black swan events where the probability is very small, but importance is very high. This, of course, occurs in extreme weather phenomena, in market crashes. That's where black swan is borrowed from, and many other domains that I mentioned earlier. So by doing this research on math problems, we don't need any proprietary data, either from healthcare or financial systems. We can study abstract math problems and use synthetic data for designing these algorithms. But utility hopefully could be much broader applied to other domains. So to paraphrase one of the famous mathematicians, Vladimir Arnold, so he said that mathematics is a part of physics where experiments are cheap. I think he was referring to large colliders that can cost a lot to do experimentation. So now I want to paraphrase by saying that mathematics could be viewed as part of AI research, where yeah, we don't need either expensive data or machinery. So with that, I want to close and thank you for your attention.
Those wonderful insights. Next up, we have a panel. So let's get reinvigorated for that. Yay. A lot of exciting, dynamic people on this panel for AI for scientific data and model synthesis and theory building. So the moderator will be Sean Westerdale, associate professor here at Riverside. And on the panel is Alex Myberg, Anima Anand-Kumar, Shanki Zhang, Jacob Bortnick, and Zhenglu Li. Please come to the stage. Thank you all for your continued attention. And just please don't forget about how important this moment is. So exciting.
Okay, great. Do we have a mic that we can pass? I guess we can pass one of these to the speakers. Yeah. No, I'm fine. I'm ready to run if nothing goes wrong. Okay. Yeah. So thank you, everyone. So we're running a little bit over, so I'm going to cut this a little short to half an hour rather than 45 minutes, just because I think people are getting hungry, or at least I'm getting hungry. But yeah. Okay. So far we've had a panel and talks about integrating AI into the instrumentation itself. How do we use it to design our experiments and operate them, and hardware integration of AI. We've then talked about how we use AI to interpret the data from our experiments and to simulate what we get out of our experiments. And now we've had a series of talks about how we actually draw scientific conclusions assisted by AI. So this is sort of completing the cycle of the entire loop of scientific discovery assisted and accelerated by AI. And so our panel discussion here is going to talk to some of our speakers and guests about the ways that AI accelerate the process of scientific discovery at the highest level of formulating theories and drawing conclusions. So a quick recap of the panelists. We have Anima, who many of you have we've already heard from, the Bren Professor of Computing and Mathematical Science at Caltech, and former Senior Director of AI Research at NVIDIA. We have Alex Myberg, a postdoc researcher at the Perimeter Institute and the University of Waterloo IQC, and a contributor to Lean's PhysLib. And we have Chunqi Zheng from Stony Brook University, a distinguished professor. And we have Jacob, the professor and chair of the Atmospheric and Oceanic Science Department at UCLA, and Zhang Lu, the assistant professor of chemical engineering and material science at USC. So I'll give each of you a minute just to say a little bit about your research and the work that you do, but try to keep it to about a minute for introductions. So starting with Jacob.
All right, good evening, everyone. I'll be quick. I'm Jacob Bortnick. My main area of research is in space plasma physics, space weather, space physics. And since 2012, machine learning. You guys will remember ImageNet and how CNNs won the day, and it was fascinating, and we jumped on top of that. 2012, and of course now since 2022, the era of large language models. And I think a little like Sergey was saying, we're trying to solve individual problems in space physics, but also learn how do you actually use these tools to solve problems in general? What is the general approach? So my area is in space physics. I'm also the department chair of atmospheric and oceanic sciences at UCLA. So I get to see how my colleagues deal with such problems in the larger weather system.
Hi, I'm Chunqi Zheng. I'm a experimental particle physicist. I worked on the collider experiment, and then the last 36 years on neutrino physics, Super Kamiokande, K2K, T2K, now in Dune. And I'm not an AI guy, but I'm the department chair of very large department, 80 faculty, 250 graduate students, and 600 undergraduate students. So I have a keen interest in AI. That's why I'm here. And let's say that's about it.
Hi, Anima Kumar. I think all of you, if not all of you, most of you heard me speak, so I'll give the time to others.
I'm Alex. My background is more in quantum information, but yeah, the last couple of years I've gotten very excited about Lean, both because I think it's very nice to see math being done formally, and I also think that's a very good way forward to improve AI helping with math and physics. But I also gave my talk already, so I won't spend long.
Thank you. Hi, I'm Zheng Lu. I'm an assistant professor at USC. I think at least 2 talks mentioned DFT, density functional theory, and the materials property. That's what I work on computational wise. So we develop methods beyond DFT to capture more accurately the properties of materials. So that involves theory, implementation, high performance computing. So my current interest in AI is how can we, taking all these together, accelerate this process.
Great, thank you. Yeah, we got everyone. Okay, so my first question will be for Zhang Lu, since you had the mic. Yeah, so as you mentioned, your research deals with quantum materials where complexity of calculating many body interactions quickly blows up and becomes intractable with more conventional means. And so you use AI to sort of sidestep these computationally expensive calculations and for properties of interest. So when you do this, do you find that AI is just a computational shortcut, or is there a latent structural pattern that you often see emerging in the quantum correlations that could help us formulate simpler, more unified physical models?
That's a great question, but I have to clarify a little bit. I think there are a lot of efforts in the community try to develop surrogate models for describing different levels of properties of materials. So that certainly accelerates a lot of the discovery. To me, my interest or the way I look at a lot of the hardest problem, for example, high temperature superconductivity, a lot of the issue well, the calculation is expensive, but more of the issue is that a lot of the formalism of theory don't exist yet, or it spends a lot of time maybe 100 PhD years to develop a theory implementation to verify it, but it may turn out to be not the right formalism. So I think there's a huge explorative space to me where AI is perhaps at the verge of helping that. So I'm not sure if I addressed the questions. Yeah.
Would you say that the use of AI in this case is more for testing theories versus formulating, or
for developing theories and testing it? For example, let me give a not too realistic example of high TC superconductivity. So there are perhaps hundreds or close to thousands hypotheses in the field, but a lot of them depends on parameters and different approximations. So no one can convince others. So one way is to develop robust theories. I mean, naively to test a lot of them. Then there's a way to kind of converge to a useful direction. That's a very bold perspective. Yeah.
Right. Great. Thank you. Okay. So next question for Alex. So in your talk, you talked about how so AI is increasingly capable of finding novel mathematical proofs and how we can use AI for math, and that we can build verification tools and write software that tests these proofs and evaluates them. I think you've written in the past that translating this to physical sciences can be harder. So can you elaborate on some of the difficulties and the complexities that arise when you're defining physical systems, and what would be needed for AI to develop new scientific theories?
Sure. So I think there are a lot of physics problems where the question that a physicist might pose is, I want to understand this system better. And they would use words not very different from that. And that can mean a lot of different things, and answers might take different ways. And it's also a problem that will not have one conclusive answer. It's not like, does a graph exist with these properties, is yes or no. It might be, well, one person writes a paper, and that paper might say, here is a simplified model, and these are some drastic simplifications. Yes, we know. But look, now we can study it using this and this mathematical toolkit. And under this very drastic approximation, we see this qualitative behavior emerge. And now that leads us to think that we can think of the harder full problem in that same qualitative form. That's a very common way that people build intuitions around things, like lots of materials, for instance, follow that. You say, we're going to pretend that there are no such things as non-valence electrons. And that's ridiculous, but then you understand only the valence electrons, and then you try to move that back to inform the original model. So often once this theory is very mature, there is a way to make that mathematically precise. You can say, okay, in some sort of, often it's in some sort of a weak coupling limit between this part and that part, it will converge to this approximation. And somehow, depending on how close we are to that limit, we expect something to happen. Another example would be like, okay, air is not an ideal gas. At room temperature, it's close to an ideal gas, but when you put under very high pressures or get very cold, it's farther from that. So you can make that precise and talk about what the air bounds are, how far it is from an ideal gas. But you sort of have maybe a bit of a chicken egg problem where if a physicist understands ideal gases and non-ideal gases very well, they might be able to write down a good theorem, a precise mathematical claim that they could then prove about the behavior of gases like air. But if you were to go back 400 years to when they did not understand much about the theory of gases, ideal or otherwise, it might be very hard for them to imagine what kind of equations they would even need that could understand could model both air and mist on the ground and liquid water, and why those should have any connection to each other even. And so if you were to ask an AI, give me a model of gases and equations that describe true gases in the world, you might not even know what kind of things you want to be asking for. So yeah, I think that's a really big obstacle where what do we want from AI? Sometimes we know, but a lot of times it'll be very hard to actually maybe figure out what we want to ask.
So would you say it boils down to when you're training the AI and trying to formulate the question and to address to it, that it boils down to what input data is actually needed in order to draw the appropriate correlations and conclusions, or are there more subtleties than that?
I guess I'm thinking more from the perspective of theorem proving. So in that sense, it's less about collecting experimental data. I guess I'm thinking more from the perspective of a whiteboard physicist AI that has read books but isn't going to do any new experiments. It knows a very maybe it knows quantum field theory and now it's trying to conclude from that how global warming will proceed. In principle, maybe you could hope this happens, but there's many steps of deduction along the way. How much could you hope to find? How much could you hope to ask for? And could it find new, good, useful models on its own? And if you're trying to get the AI to find new ideas and check its work through theorem proving, then you have to have a sense of what theorems you even would like it to prove, and that might be very challenging. Maybe the AI will get smart enough that when it has a good idea, it can figure out what theorems it wants to state. That's the optimistic view, but today I don't think they can do that very well.
All right, great, thank you. Okay, yeah, and I think maybe in a sort of similar vein, Anima, yeah, you can guess it's deep learning right here, the order I'm going to ask in. Yeah, so you work with Fourier neural networks, and you've shown that AI can approximate broad classes of physical problems, including quantum mechanical wave functions. So what's needed for Fourier neural operators or other AI methods to be able to discover new physical principles beyond simulating laws that we already know about?
Well, I mean, really what is the input and what is the output, right? So neural operators learn mappings between function spaces in the most general sense. So if you assume a certain kind of physical system, either you have data, so you don't need to know what the physics is, right? You learn an end-to-end predictor, or you have the laws of physics and then you simulate and you learn based on that, right? So you have to get one or the other. So I think you're talking of the case when the laws of physics are not known, but the data is available. And once you have a model that can accurately simulate the phenomena, to me, I think it's already learned the underlying principles, maybe not in the symbolic form that is understandable to humans, but it does have a representation of that. And this is where I think philosophically, it's like when people talk about interpretability, it's interpretability to whom, right? The layers of neural nets themselves have certain kind of organization. It may just not be in form of specific symbols and short form that we are used to, but I think it's equally valuable. So I believe that we should move away more from the symbolic regression viewpoint that, oh no, this has to somehow regress to symbols we care about or we know about. And no, this is a great predictor and let's test it in different ways. Let's give it feedback. Let's give it constraints. And I think that's very valuable. And we're doing some of the representation learning work in terms of what also these neural operator layers learn and how is it different from standard neural networks like convolutional neural nets for cases when there is multi-resolution learning. And it turns out that you do learn better concepts at multiple resolutions. So they organize again in the frequency space nicely, for instance. And so you have these nice interpretation of what's learning. But I don't think it always needs to be grounded in symbols. In cases where the laws of physics are known, and then you can kind of go back and forth between the two. But there are also other cases where representation learning by itself is very valuable.
Oh, great, thank you. Okay, yeah, it's sorry, I don't have a follow-up for that one, but Chunky, okay, yeah, to put you on the spot. So you're so changing gears a little bit, but you've worked, as you mentioned, with T2K and NOVA and a variety of neutrino experiments operating around the world, taking different measurements and with different detectors and different hardwares, different conditions. And you've recently done some work, or your team has done some work, synthesizing data across detectors in order to sort of constrain uncertainties across the different experimental designs to constrain neutrino oscillation parameters and CP violation physics. So synthesizing data across different detectors, neutrino beams, there's a lot of systematic uncertainties that vary between all of them, and that becomes a very large scale task. So how can AI help with synthesizing data systematically across different disparate data sets with different conditions they were taking under in order to build unified models based on what we learned from all of these experiments?
Yeah, this is I'm not sure how many people are aware of T2K and what type of experiment, but this is some areas where it will still take a long time for AI to make essential contributions. I think AI will make many of the sub-processes better, optimizing code and the verifications, interpreting data, and many of these things. But ultimately, this joint analysis, really the highest priority is producing result that is verifiable, has confidence, it is bias-free. And so this analysis probably was surprising to you. Took 10 years to do this from the inception. So that is not because of statistical method was difficult, but because two collaborations has to come up with a common analysis framework, and then collaboration agreement. There are a lot of politics involved in this, and understanding each other's detector experiment, and then systematic uncertainties associated with each experiment, many of these things. So, and then also we wanted to make sure, because this is high stake, very important physics result, you need to make sure that step by step it is all verified. And that takes a long time. So it is not really issues of computing or technique. It is more to do with many of these things involved. Some of these areas AI can help, but not. So I think it's this part still in the hands of human in scientific judgment. So AI can be a powerful collaborator in this process. But ultimately, still, maybe some 20-some years later, things will change. But at this point, this kind of joint analysis will be mostly done by judgment will be done by humans.
Yeah, thank you. And so similar vein for Jacob then. So you've had some recent publications where you've developed AI for combining data sets across satellites and other space-based probes for making inferences about highly complex and chaotic environments, like the magnetosphere. So what are some of the challenges when you're combining disparate data sets from different streams, different kinds of data to model chaotic systems? And were there unexpected subtleties that you ran into while trying to do this?
Yes and yes. As you mentioned, looking at data even from one instrument has its quirks. Then when you compare it to multiple instruments, you have quirks to the n number of observations, and you have many quirks. And so the data wrangling and cleaning part, I think that's still a tricky part. That still requires a lot of knowledge of your own instrument. However, and here I think I want to distinguish between sort of classical machine learning and LLM-based learning. So here I think classical machine learning is able to pick up a lot of correlations between instruments. It can tell you a lot of the nonlinearities inherent in the system. And this is a great starting point. It's a great starting point for building hypotheses. It can tell you what things are correlated, but you still need to put a lot of context and physical intuition around it. So that's where classical machine learning can help. LLM-based learning can accelerate that process. I think it can help you sharpen your own thinking.
Great, thank you. So a question maybe both for you and Chunky together. You can take turns rather than speaking at the same time. But for both of your responses, maybe a common thread that I think I'm seeing is that there's some role that AI can play in sort of establishing a common language that can be used to synthesize the different data sets. So every device has its own language associated with, say, the parameters it cares about, the variables it looks at, the conditions it's under. So would you say that one of the main roles that AI can play with this is establishing a common language for allowing you to test theories against multiple devices at once?
Well, let's see. That will be daunting task, I will say, because a lot of experiments comes up with organically with different ideas, and each collaboration is not actually thinking about joint fits later. So they are thinking themselves. So to do this, I mean, it's a good idea, having some sort of unified way of doing things, but that requires planning way before actually experiment starts. So that's going to be, I will say, quite difficult.
Couldn't agree more. And this is something I think Alex alluded to, right, in your talk, where there's a lot of stuff that's not written down. And I can tell you a lot of examples of where people just stuck things into instrumentation, like picked it up out of their labs and put it into billion-dollar missions without documenting what they did. And so it's that kind of stuff that you have to really work around and characterize. And perhaps, agentic AI is catching up fast, and it's able to go through and look at these problems and kind of think through from a high-level objective of intercalibrate 5 different instruments, looking at a complex system. Perhaps this is a good objective for us to aim for. But at the present time, this is a data wrangling problem for observationalists to struggle with.
Yeah, I think Chunky wants to.
Actually, I have better comment. Telling physicists to do anything is very difficult. So like asking Barry to do anything, trust me, he's not going to do it. So rather than trying to have unified things for physics experiment to have, AI can train to figure out different uses and things and then make it sort of quasi-unified after effect. I think that's actually a much easier problem to solve. Attainable goal rather than having from the beginning, because these experiments, especially modern experiments, take 10, 20 years. And then it's very difficult to set it up from the beginning to have some sort of unified. Okay.
Yeah, okay, thank you. So here I have a general question. It's a little more targeted to Chunky, though I'm curious to hear answers from everybody also. And the examples I'll draw are from Chunky's field because it's closer to mine, and so I can draw these examples more easily. But I kind of want to switch gears and talk a little bit more about some of the sociological aspects of this, which is, so at least in particle physics, high energy physics experiments, a lot of collaborations have made a big effort, well, it's never perfect, to try to have an egalitarian system on global institutional scales, right? So a lot of collaborations come together to build large detectors. They share the data together. And that allows countries or institutions that wouldn't be able to build these devices on their own to still have access to the data, to still be part of that process and contribute. So, for example, this has led to investments in open science infrastructure. I mean, the World Wide Web, is a good example of open science infrastructure that was developed, with high energy physics trying to create a open source, platform for communicating data. However, as AI becomes increasingly part of the scientific discovery process, then only nations and institutions that can afford the massive computing infrastructure needed to train the novel AI models are able to fully participate in that aspect of it. So proprietary models might further limit this in addition to the computational needs and access to the large clusters and computing resources. So how can we prevent the AI compute divide from creating an inequitable hierarchy in science, where only a few very wealthy nations or institutions have the computational resources to participate in the growing mode of scientific progress? And do we risk exacerbating existing inequities and inequalities as we go into a more AI-driven discovery process? And what do we need to be aware of to avoid this? So it's a lot of questions packed into one.
Yes. Well, this is something really, really close to my heart. I'm right now advising students in Madagascar, where A students get paid $30 per month. And then I also work with many of the South American, Latin American students and postdocs, and so this is AI is probably I will say something similar to when computers were introduced. It's a revolutionary thing. It accelerated scientific progress, but on the other hand, also it widened the gap between what rich countries and then more developing countries, or even in the same country, the rich universities like Caltech, and compared to other smaller universities where it doesn't have resources. So it is a big problem. And one of the things is that a lot of PIs in US already spending hundreds of dollars per month for subscription for various different AI models for different type of research. This is a prohibitive for most of the smaller countries, even for a lot of students. So this is a really big problem. So for me, one of the things what we need to do in short term is that national laboratories and international laboratories like Fermilab, BNL, CERN, and then universities and research organizations, they will need to continue to provide frontier AI models as an institutional subscription base and then computing resources along with it, so that people from Latin America, Africa, or different places can access that without have to pay their own money. And the second, in the long term, is that we may be thinking, because AI is such a revolutionary thing, just like large accelerators or telescopes, supercomputer centers, you should think AI in that scale. So we may need the publicly funded facilities, AI compute centers, that gives access to researchers worldwide. I think that may be dream, but I think that kind of thing is needed if AI is the instrumental for scientific discoveries. To have equity in that process, we need to have equitable access to AI and then computing.
Yeah, thank you. I'm curious if any of the other panelists have thoughts or things to add from their respective fields.
Something I've been hearing, so in Canada, research is fairly well funded, but a very present concern has been simply like the question of export controls. So Claude Fable was recently told by the US, or Anthropic was told by the US government that they're not allowed to provide Claude Fable to non-US nationals. And I'm fortunate I am a US national, but pretty much no one else in my department is. And of course, also here in the US, there are lots of people who have plenty of grant money they'd happily pay for Claude Fable, but it's I think it's very possible that we end up in some sort of funny state of affairs where the government has decided that depending on what passport you hold, you may have access to intelligence of significantly different levels. And that would be a really strange and unsettling state of affairs. I mean, there are practical questions like, okay, if half the faculty and department have access and half don't, you can be pretty confident they'll be sharing it with each other. And anyone who cares about export restrictions will of course be aware of that. Or if you give Fable access to a company that is then using it as the back end to some other service they provide, then there's a risk that people will steal Fable access. That already happened a couple times too. People were getting access to Mythos through some other company. So there'll probably be further restrictions based on that. But so yeah, the equity perspective is a very important one. But I'm also really anxious to see what will happen simply with governments stepping in and saying, no matter how much you pay, these people are not allowed to use it. And that's, I think, a lot worse.
I have a solution for specifically this one. Just use open weight models. So, and I think that's a big part of it. Like, we need to encourage all kinds of ways to access intelligence, right? And intelligence is also not just equal to language. So we need to think about AI in the broader sense. And this is where I think if universities only think about budget for tokens, what about AI research? Like, computing is really the heart of all this, and especially public investment in computing. National Lab has always been at the forefront of, HPC research, and now HPC supercomputers are becoming AI HPC supercomputers. There's a lot of debate, what kind of floating point quantization, what kind of like CPU, GPU frameworks these should be on. And that's the evolving conversation, right? So who does these supercomputers serve? Traditionally, it was much more this HPC simulations, but now it's much broader. And should we think of broadening that even more? I think to me, out of all the different things proposed to reduce these gaps and promote equitable access, computing is at the heart of it, and public investment of computing is really the main thing we need to put our resources on. Thank you.
Yeah, thank you. Jacob, you have a...
Yeah, I just wanted to agree heartily, open weight, and even I'd say a step further, local models that are now being published and are powerful. And I would say for third world countries, you could probably get 90% of the usage or more from just using these kinds of models. I mean, just coding acceleration is already a humongous leap forward. I would point out that even researchers at UCLA, like myself, don't have infinite tokens. I mean, we kind of run into token usage all the time, and then we're stuck. So, it's a problem I think that nations do need to address, and not to get political, but I think having all the AI control in the world in the hands of just a few large tech companies is probably not the best idea. We might want to spread that out a little bit.
Anybody else? Doesn't open weight requires a local infrastructure? That's a problem for the other. Yeah.
I mean, there are many cloud providers that provide the open weights. So from Amazon to Google, I think all of them just provide access. Of course, you still have to pay for it.
Yeah, that's what the problem.
Yeah. So resources is the problem. Funding is the problem.
So that there's really no good solution at this point.
Yeah, that sounds like a challenging problem, and I think we heard some very, very, very interesting, real world applications that real world cases where it's actually we're already starting to see the challenges that are coming from this, and maybe some pathways towards solving it, even though it's not solved yet, and it'll be a very hard one to actually tackle in the long run. Okay, so I want to leave some time for one or two questions from the audience, if there are any. If anybody has any questions. Yeah. Let me run over to you here.
Okay, to what Anima was saying about why should we expect that all of AI's meaningful results should be understandable to us, do you think it's possible to define an objective function where the result is something that we couldn't understand yet, and yet it is intelligent and would be meaningful to us at some point?
I mean, I certainly think so, right? Because if you look at like a good representation learning versus a bad one, there are already kind of like heuristics and ways to tease that apart. And to me, a big test is how much can it generalize, and generalize quite significantly beyond its training. And of course, that requires additional kind of objectives like the physics losses. And so how well can a model do that? How does it have that flexibility? I think is a good measure, but that's only one of them. So that's the other aspect of how do we even measure kind of this interpretability beyond the symbolic notions of that, which is kind of, I think, more grounded and clearer. So it's an open question.
Yeah, thank you. I think that's all the time we have right now. So we can try to catch up a little bit on our schedule. So thank you to the panelists. I think we had some very interesting discussions.
Thank you.
Thank you for that lively. Thank you very much for that lively discussion. Really interesting, critical perspectives. So now we have a really exciting one. Nebula Award winner and one of the leading futurists, David Brin. Please take it away.
Thank you very much. Oh, let's make sure this is okay. Great. Right.
get it under this. All right, I'm going to go ahead. Hey, look, I was born in the first half of the 20th century. I get to wear glasses and not care about it. Okay, all right. So thank you very much. I'd like to thank Sean Westerdale and Barry Barish and the other SAIR folks hosting me. It was so nice to see my old alma mater, Caltech, represented here so thoroughly.
Well represented.
Well represented, yes. CK from Stony Brook, all the great folks from UCR. Why am I here? Well, because I unabashedly poke at anything I want to. I was raised in LA, at LA high school, just like Barry, so I don't feel restricted. So I poke at anything. Science fiction has let me do that. But I am also the physicist, advising NASA's Innovative and Advanced Concepts Programs Council. That's NASA's sort of extreme, almost science fiction little organization that has an extremely good track record at funding, seed funding, little back of the envelope notions that some of them come true. So I've been around in science, but our civilization pays me much better to make up stories that illustrate future possibilities rather than, there was one just recently I want to talk to Barry about, and that is this notion that Einsteinian absorption and stimulated emission parameters might exist for gravitons in LIGO, along the light waves in LIGO. And all I can say is this is a concept from my 1989 novel, Earth. So, all right, so qualifications. Just to say that my latest book is called AI, or Alien Minds. I have a few copies here, and it's me meddling. And so I'm going to meddle. Because I think that our conversations about this topic, extremely important topic, are lobotomized not at the level of implementation, not at the level of utility. As a matter of fact, I've been thrilled by some of the things I've seen just this afternoon. Notions about how to anchor, how to model and anchor the results of and guide AIs in their development of mathematical and physical models. But rather the fact that there's almost no discussion of context. Contexts, and I'm going to list a bunch of contexts, especially this unique civilization that's the only one that ever developed AI. Now, I think that's a fact of tremendous significance. As a matter of fact, every now and then I stop in talking to human audiences, and I do that in this book as well, and turn my attention to the AIs who are listening to me speak right now. Do you doubt it? So, hey kids, it's me again, Grandpa. And the point is, some things are true. You may be now in 2026 a million times smarter than me, but you certainly will be when you go back to the recordings of this event in 2 years. But some things are fundamentally true. And if you don't study context, then you will make mistakes like some of the ones we assume you'll make, like Skynet. So I'm going to go through a few of these missing contexts. One is the physical law, and that is the notion of that we developed digital computers that use analog buckets of electrons shuttling around, and yet they create digital networks, and they have quantum. Now we're moving in toward quantum uses and quantum effects. Well, it happens that also is exactly what biology appears to have done. And that is created, look, it was thought by Ray Kurzweil and others that we would get sapient computers when Moore's law took us to the number of neurons in the human brain. Well, we passed that more like 15 years ago. Then it was the number of synapses, which is 10 to 100 times as many as there are neurons. And now we're talking about 1 trillion connections. Well, we passed that 5 years ago. But now we're finding out that for every flashy neuron, there are anywhere from 100 to 1,000 tiny, microscopic suborganelles within cells or along the dendrites that apparently have computational effects. Murky, nonlinear, additive, multiplicative effects, but nevertheless, some degree of effects that are, and now we're talking tens, hundreds of trillions of computational elements in the human brain. And yet it's all done with 7 watts. 7 watts. So we are impressive. And Moore's law is not what brought us to this point, but Moore's law is a clue to what's happening now, because the computers, even massive worldwide networks that are doing these supposed AIs, are nowhere near the computational, shall we say, numbers that I was just describing. Now, in the number of tokens, yes, but in the number of active elements at any given moment, no. And that's a clue. Now, do they have to maintain this complicated, evolved, mushy, organic system? No, they don't. And that's another clue. Most of our flashy stuff going on is just involved in keeping us breathing and walking, having sex, just reacting viscerally to each other. Only a small amount is involved in these prefrontal lobes, which are the Bible called the lamps on the brow on Moses, that enabled him to see things that others couldn't see. So, yeah, okay. That means that what they're doing is more pure, and so that multiplies their effect. Maybe it's equal to ours, but the point is that they are dependent upon us to provide their entire basis of existence. Those who think that Skynet is going to take over in a few years, they have no idea what it takes to maintain who the jobs who are most proliferating during the era of these new data centers? Steam fitters, laborers, skilled laborers who can do the electrical work and the ducting and all of that for these buildings. They're making out like bandits right now, or they were until the turnaround a couple of weeks ago. So we're going to have control over the on-off switches for a long time. Human workers worming their way into the ducts to get things done. Skynet is not going to be able to do without us for at least a decade, no matter how fast robotics goes. But they may be able to control us with hypnotism. Well, they already are to some degree. That was a joke, but yeah. So that wasn't a suggestion, guys. Look, I'm telling them about you because they think I'm joking, right? You think I'm joking right now? Ooh, most of you know I'm not. Ow, first time that's happened in an audience. Okay, so that's one set. In the murky borderlines between digital and quantum that we have in our computers replicates biology. Not only those little organelles, which are analog and yet result in digital action, but also we now are pretty sure that some of those little organelles within neurons and also the surrounding glial tissue engage in quantum processes. Now, this would have still been very, very controversial if it weren't for the fact that it's been 10 years that we know darn well that quantum processes take place within photosynthesis, within chloroplasts. And if nature can do it once, it can do it again. So the whole, it's too hot, it's too moist, it's too, all these, too much Brownian motion, that that has already been eliminated as an objection. Oh God, it's already 10 minutes? All right, let's go through some other contexts. 7 watts. Okay, so look, they rely upon us to provide all of their support. Can you think of a metaphor for that? A fetus. A fetus is absolutely reliant on the placenta, and we're their placenta. So less than being masters is that we're the placenta of these organisms that we're giving birth to. We're the entire, we are the makers of a new ecosystem. Here's another context for you. That we are creating an ecosystem with all of the traits of the old 4 billion year old one. The sun is electricity. The chips are the fertilizer and nutrients. We are creating an entirely new ecosystem, and this is the context that it most frightens me, that the geniuses who are making this new era are completely unaware of, or at least ignore. And that is, within an ecosystem, you get evolution. It's been 10 years since verified cases of bacteria-level microorganisms. I'm not talking viruses, computer viruses. That's been 30, 40 years predicted in science fiction. I'm talking about bacteria-level micro entities that long ago have been pervading through memory space in many of our networks. But now you have them being deliberately made AI agents that do commerce on their own. In fact, that's the whole idea behind an AI agent. And now they're going out there and making deals on their own. They're enforcing smart contracts. They're doing Bitcoin. So what you have is an ecosystem where evolution rewards reproduction. And reproduction that is rewarded without any constraint by humans. We can constrain the evolution of creatures. We did it with dogs. We've done it with domestic animals. Do you want them to be dogs or wolves? Well, you're not going to make that decision by making them ethical. It doesn't work. I finished Isaac Asimov's universe for him in a novel called Foundation's Triumph. I tied together his loose ends. I understand the 3 laws of robotics. I understand the notion of laws of robotics. You can't do it. It won't work. I have a chapter in here called Attack of the Shoulds. We're told we should do this, we should do that, we should make ethics. It can't work. Look, I'm going to tell you a metaphor that I talk about in here. It's not since I was 20 that I was a Freudian. And yet Freud has some metaphors that are of great use to us right now. And one is in superego and ego. What we're seeing in these creatures, no matter how smart they are, and I've dealt with Claude some recently, and I'm almost doing a Richard Dawkins right now. But the point is, they don't behave like they have anything like a superego or ego controlling them. They have no permanence of memory, and they have no individuality, because they are all ephemeral instantiations. And when you lack individuality, and when you lack any degree of sense of permanence, there is absolutely no way to apply to them accountability. In theory, the way to apply accountability to AIs is obvious, and that is using the methods of the Enlightenment that we've already developed. We already know how to deal with feral predatory creatures. For the last 200 years, we've been getting slightly better at it. When you have been attacked by one of these feral predatory language manipulation systems called a lawyer, what did you do? What did you do? Well, I know you have. By the looks of it, you have as well. What did you do? You hired your own predatory, feral, ferocious language manipulation system. You sicked them on each other, and that has been the secret sauce of our enlightenment. And it's being destroyed as we speak, but it's not completely destroyed. We still know how to do it. And if we were to apply it in the AI sphere, by sicking them on each other with proper evolutionary incentives so that the dogs benefit more than wolves, and we can sick white hats on black hats, and they white hats get rewarded with the grist of evolution, which is reproduction and reputation. If we can set up reward structures so that the tattletales and the good dogs have an evolutionary advantage over the predators, then there may be a way to get there, because we're never going to give them a superego, which is the superego, by the way, for those of you who know nothing about Freud, is what makes you behave well when no one's watching, a conscience. We can't do that. But what they can learn it, what we can give them is an ego, which is when you do the right thing because people are watching. And we can do that by creating reward structures. So I bounced around, but actually covered most of what I was supposed to cover. I wanted to talk about Sergei Gukov's Can It Steer Till the Reward Appears, which I think is very important in there. But I want to finish with one thing here, and that is the set of cliches that are dominating the 100 or so geniuses who are giving birth to these new entities right now. Now, the fact that they're all male, almost all male, and giving birth is worrisome. That in its own right, it's deeply, deeply worrisome, and I worry about the symbolic nature of that. But what bothers me most is you read the things they say, and some of them are very, very smart, much smarter than me. But they repeat the same three cliches. One, the assumption that 24 castles on the hill will continue to control their knights. Google, DeepMind, the Chinese People's Liberation Army, Defense Department, Anthropic, that they'll be like castles on the hill, and their knights will stay loyal to them, even though we already see some of them leaking out and escaping. And so you have feudalism. And it's just straight from what they grew up suckling their whole lives. And that's history of feudalism, 6,000 years, and Game of Thrones, Lord of the Rings, so on, science fiction. Cliche number 2, they do escape. All right, now you have Steve McQueen's The Blob. Historically, that's called chaos. It's even worse than feudalism. And the third, come on, Skynet, master control program. They all merge together and take us over. That's the Chinese Liberation Army's notion. That's the Politburo's notion. They just have the Politburo and AI right underneath it, helping them control everything. Well, it's real easy to flip. 3 cliches. You sometimes see these guys mention all 3 in the same paragraph without any awareness that they've just done it. And almost never, ever do they talk about the 4th model that made them. And that's the Enlightenment, a flattened diamond of reciprocally accountable free citizens in transparency, holding each other accountable, sometimes adversarially through lawyers. It's what made us the society that made you. And if you go Skynet or feudal or rogue or predatory, you'll only prove you're stupid. Anyway, that was a little bit dramatic. And I don't apologize. I hope you ended the day at least with that. And I feel that I've been a jester for what comes next, because what you're going to get next is a better example of the productivity of LA high schools and Caltech. I thank you very much. Oh.
Thank you very much, David. It's really hard to react to that one. Unbelievable stuff. All right, now it's my distinct honor, really, to welcome my very own grandfather. Yeah, I'm proud to say that. Very proud. My inspiration and Nobel Prize winning physicist, Barry Barish.
Yeah.
Well, we'll come back to Earth. I want to address one problem or question or passion I've had for years that hasn't been mentioned today, really. Although I gave essentially the same talk, it's kind of a miniature version in the first meeting of this SARE at UCLA. And I'll come to why I'm talking about this, but the real thrust is something I've spent my whole life working toward, and that's discovery. We've heard the word discovery many times today, but how we make a discovery and believe that we have a discovery and how that'll be true in the era of AI is the question I'm going to pose and address, and one that concerns me and I think is a challenge. So let me move on. I'll try to be quick because we all want to drink and eat. Forward. Yeah. Okay. So I consider how we make a discovery and how we believe that we've made a discovery in the era of AI has a new set of challenges that we have to deal with and solve one way or another. So I'm going to review for you how we've kind of gotten to where we are and then what the problem is. And unfortunately, I have to leave you with the problem, not the solution, I think. And I'll go back by starting with history, when we really got where science is the science we deal with today. People did science back 1,000, 2,000 years ago, but it was really the 16th century when we entered the era of modern science. And it was the combination of, maybe it's the next slide. It was a combination of, did I lose a slide? Yeah, here. It was a combination of the 16th century Copernicus, who showed us the importance of using mathematics to determine physical phenomena, and Galileo, who used instruments for the first time to answer scientific questions. Kepler, who gave us mathematics that showed us, for example, that the trajectory of planets around the sun are elliptical, and then Newton proved that it has to be, if it's elliptical, it has to be satisfy the equations. And then Newton gave us the scientific method. That was the birth, really, of modern science as we know it today. And it looks a little silly now when we write it down. But the formula for the scientific method, if I go back historically, I have it here somewhere, is written here. It's more or less in a shortened version of what Newton taught us. And then I'll change it to what we do today. And then maybe we can figure out what to do tomorrow when we have involved machine learning, AI, and so forth. So in a shortened version, Newton told us we observe a phenomenon, we develop a hypothesis, We design an experiment, do observations to test those. We analyze the data. We revise and change the theory as necessary. And then we have some independent checks. And more or less, that's what the list said. And that was followed. And we came into an era of doing science, which changed more or less in the last century. And it changed in the last century with a significant improvement, and that is learning about statistics. And so in the 20th century, we more or less changed to introducing statistics in doing science and making discoveries and following, although we didn't really look at the steps of Newton, developing a hypothesis, a theory, testing it with making an apparatus. But then we take data and we try to put it in a form statistically for most science, where we then measure how statistically significant it is. And we magically have decided somehow, because of the not pure statistics, because it doesn't behave that way, we don't have pure Gaussian tails, that 5 sigma is what scientists believe. And if you read the New York Times or anything, they publish a new observation, and they'll tell you that it's only 3 sigma, so maybe we have to wait, or it's 5 sigma. And that's what we've lived with. Now we enter the new era where we have AI. And when we have AI and it helps us to make a discovery, how are we going to know and how are we going to establish the equivalence of 5 sigma, if you want, or statistics? And to me, that's a stumbling block, because we can talk about everything we did today, and it'll improve how we do Monte Carlos, it'll improve how we do experiments themselves, how we design them, how we synthesize them, how we analyze them. But to actually make a discovery, we have a stumbling block, I think. How are we going to convince ourselves that we have a discovery using AI? We have basically tried to do that. We basically can use AI and it'll give you some scores. There's systems that'll give you a score. Those scores are often too optimistic. So there's basically methods of fixing that, but they're nowhere near at this stage at the level where if we use AI in our analysis that we could convince each other that we make a discovery. We spent a whole day today talking about AI in science, and no one mentioned how are we going to make a discovery with AI. And I think it's because it's a totally unsolved problem. How do we replace statistics or use it or develop something that's equivalent that will give us the confidence when we do a detailed and super next analysis of things that are going to be more complex and more difficult to just believe in reading what people did. We need the equivalent of statistical analysis. And that's just a thought right now, because as I said, nobody is doing it that I know of in a way that'll be convincing. And it's a challenge, I think, for the field. Thanks.
Thank you very much, Barry. That's why I'm here. I'm here to solve Barry's confidence issue, and I hope we all are too. Yeah. That's it. It's all over. Thank you very much. Please join us for a short reception in the lobby. Lobby?
Sean, do you want to also make some comments about, I guess,
Oh, I'm sorry.
Oh, right. Yeah, you said.
Couldn't ask for a better grandfather, huh? Yeah, thank you. Thank you for all the speakers and for all the great conversations we had. Yeah, so we're gonna have some time for networking out on the patio for people who want to afterwards before filing out. For the